everyone, welcome to this course on Applied Data Science with Python. Today, data is everywhere, from shopping apps and social media to healthcare, finance, even entertainment. Data help businesses make smarter decisions every single day. But raw data alone is not enough. What really matters is knowing how to clean it, analyze it, visualize it, and use it to solve real-world problems. And that is exactly what this course is all about. This course is designed to help you move beyond the basic Python and start using it in practical data science workflow. You will learn how to work with datasets, create meaningful visualizations, build machine learning models, process text data, and understand network relationships using Python tools that are widely used in the industry. First, we will learn about how to clean, organize, and prepare data using Python libraries like Pandas and NumPy. Next, we will explore data visualization using Matplotlib, Seaborn to turn numbers into clear insights. Then we'll move into machine learning with Scikit-learn and understand how predictive models are built and evaluated. After that, we will look into the text mining using NLTK to work with unstructured text data. And finally, we'll be exploring social network analysis with Network X to understand connections and relationships in data. Also, if you're interested in mastering the future of technology, do not forget to check out the professional certificate course in generative AI and machine learning, which is the perfect choice for you. This is offered in collaboration with the ENI Academy and IIT Kanpur, and it's an 11-month live interactive program providing you hands-on expertise in cutting-edge areas like generative AI, machine learning, tools like ChatGPT, DALL-E 2, and even Hugging Face. You will be gaining practical experience to 15+ projects, integrated labs, live masterclasses delivered by esteemed IIT Kanpur faculty. Alongside, you'll earn prestigious certificate from IIT Kanpur. You'll also be receiving official Microsoft badges for Azure AI courses and career support through Simplilearn's Job Assist program. So what are you waiting for? Hurry up and enroll now. The course link is mentioned below. Now, before we get started, here's a quick quiz question for you. Which Python library is commonly used for data cleaning and manipulation? Your options are Pandas, Seaborn, Network X, NLTK. Let me know your answers in the comment section below.
So what is data science? Okay, so what is data science? We had to put a definition to it. It is a multidisciplinary field that uses scientific methods, processes, algorithms, systems this is the big part of it, derive meaningful insights from structured and unstructured data. So that's the big part of it. Is obviously data is in the name, data science. So our goal with data science is to derive meaningful insights from data. And so that can involve many things. That can involve building models, which we will learn how to do later on when we get into machine learning. That can involve building out visualizations. That can involve doing hypothesis testing. That can involve many different things, but we're deriving some type of insight or finding out something interesting about our data that we have through different methods. So it's kind of, I always like to say it's the science of working with data, which is kind of a weird way of saying it because that's obviously the name data science, but it truly is the science of extracting insight from data is this field. And there's a lot involved in it that blends a lot of different disciplines together. It's why we say it's multidisciplinary because we kind of bring together multiple aspects of math and stats, computer science, domain expertise to be able to derive those insights. So there's there's ideas and concepts borrowed from science, like doing hypothesis testing. There's obviously math and stats, a lot borrowed from there. There's a lot borrowed from visualization and analysis that we use in data science, but we kind of blend that with technology, right? With computer science. So being able to use Python is a big deal. That will be our language of choice for doing anything data science. That's why we kind of reviewed it in the beginning. So we'll certainly use Python. we'll certainly use different tools within Python to process data. Those are data processing tools. So we kind of blend those together to form the field of data science. So those scientific methods, along with tools working with data from technology like Python, blend those together, we kind of get data science. So where do we see data science today? There's a lot of different applications, and we'll try to describe some of them to you, which is, for example, like wearable devices. So think about like Fitbits or Apple Watches. They're always crunching data from their sensors, right? So there's some type of biometrics that are captured and sent over the internet, essentially, um, to basically allow us to do some type of analysis or some type of derivation of insight from that data. And then we can kind of visualize that with some graphs or some meaningful metrics, so that the person wearing that device can make some sort of decision. So there's some type of insight derived, and usually some type of algorithm being applied to that. Maybe a model's being built, working with the data that's captured from the wearable device, or we're just plotting that data, or we're summarizing it in some way, but making it really useful to the end user to make a decision off of. So we're deriving insights there, from all of the data collected in the wearable device. So that's kind of one application. Search engines use data science to personalize results or offer recommendations as people type in their queries. So essentially, like, you have suggestions, right? Like, and these could be based on your previous browser history, all kinds of data, like your cookies or your what's trending in the world, or like your region. Though you probably have noticed this, right? When you're searching on search engines, you get these suggestions. Those recommendations are kind of powered by data science, right? So data is going into that to derive some insight that, hey, this is what we should suggest, and that's it gets surfaced there. One of the things that we'll look into down the road when we get into machine learning, which is the next course after this, will be recommendation systems. So how do we actually build those models that do recommendation? But in order to build those, you really need data. So that's where we got to start, is working with data to get in a position to model off of it. Finance, we see usage of data. For instance, there could be like some type of model that's built to determine a loan decision. So there could be the application, and then there could be additional data that's gathered via the details in the application. And then all that data can be brought together and kind of analyzed through the use of a model that could predict, yes, we should give this loan, or no, we should deny this loan. Um, so again, you're deriving some type of insight from that data, um, to make a decision, right? To make some sort of loan decision in finance, or like we see a lot of fraud decisions made as well. Like, is this transaction fraud or not fraud? That's another big use case of data science. So based on the data of transactions, are they fraudulent or not fraudulent? Okay. A lot of other applications, those are just a few. And as we go along throughout this course, we'll really study a bunch more and get into some more use cases as we go along. This is just a preview. But what I want to go to next is kind of the process by which we attack data science problems. So we know that we should be deriving insights from data. That's what data science does. And the question is, like, how do we go about doing that? What is a good systematic way of doing it? So we're going to describe that in the process. Uh, Good question. Differences between data science versus data analytics versus data engineering. Yeah, so um, The difference with data engineering, let me start with data engineering. Data engineering is mostly centered around building like pipelines and building systems that can collect data. So it's more about engineering systems to like collect data and house it and store it and facilitate data um, transfer and data availability. So it's more about working with the data to make it available and collect it. And it's a lot more engineering heavy, as the name suggests, because you're building pipelines and building systems that will like scrape data from sources or pull data from APIs or do those kind of things that um, will collect data for you. That's a little bit different than data science. Data science, remember, is going to be generally like building models or doing visualization or both, derive some sort of insight, find some sort of pattern, or find something interesting about the data that's not already or hasn't is not readily known um, just by looking at the data. Um, so with that being said, there's a lot of overlap of data science and data analytics, but I would say analytics is a little bit more static in the sense of a lot of analytics are just doing basic rule systems or basic visualizations. Data science usually goes a step further and builds more sophisticated models to make some sort of prediction, make some sort of decision off of. So data science generally involves more modeling than you would see in data analytics. Whereas data analytics goes a little bit deeper on doing like visualizations and doing more like experimentation, um, statistics gathering. Does all that make sense? Like data science is going to be more heavily on the modeling side to derive insights. That's a big deal about how to derive insights is from building a model. Yeah, that's a great question. I know there's a lot of those overlapping terms. This is a really good question. Any other questions? Okay. All right, let's talk about the process. Okay, so the process is outlined roughly here, but I'm going to take us through every single step. But if I had to break this down into basically a handful of key steps, it mostly starts at here, which is kind of initial problem formulation, which involves collecting data. So usually you have problem formulation. So you need to know like do we want to build a recommendation system for movies? Do we want to figure out if transactions are fraud or not fraud? Like we're coming up with some problem that we want to solve and then going out and collecting data that might help us analyze that problem further. So we'll talk about that. Then comes the kind of data preparation phase, I would call it. So data prep, meaning that we are preparing our data for modeling with that goal in mind. Is our goal is to actually build some sort of model to tell us something, to help us make a decision or derive some insight, right? And so we will do a couple steps. I'll describe what they mean in a moment of doing some data preparation in order to get ready for modeling. Then comes the actual modeling phase. The actual modeling phase, which involves building, training, evaluating, all of that. Um, and so then comes the modeling phase, and then comes the actual deployment of the model, meaning that we use it in the real world uh, to bring our insights into an actual system, integrated into actual systems, so that those decisions can actually be made and used by an end user. Let's say, I believe you can call a data science process even if no model is built. Step 4, 5. Um, you can, but so I think that's fair is to say like if even if you're not building a model, so you're thinking just steps one, two, three, four. Yeah, that's true. Um, or even just one, two, three. I think that's fair, but most of the time in this course or in this program, we're really going to be building models. So I want us to have this in mind is like even if we stop here and don't do any model building, this is what we have our eyes to is the ability to model if we want to. Okay. But I think it's a fair point is that it could be um it's a fair point that you could just imagine getting your data together as really like um kind of a data science process. Is feature engineering the feature that will use feature I'm going to describe what feature engineering is in a moment. I'm going to go into that in further detail in the next couple of slides. So just hang on we say feature engineering. We'll talk about it. We'll talk about it. I was thinking for A/B testing and probably where there's no model, would you call this a data science project? Um, it, that's up for debate. A/B testing, sometimes that falls under analytics. Sometimes that falls under data science. I, yeah, sure. We'll talk about doing A/B testing. So even when there is no model, so I think it's fair to say it's part of data science, which would kind of just be steps one, two, three, four. So yeah, I see where you're coming from. I see where you're coming from. Yeah, traditionally A/B testing is more like experimentation analytics. I agree it's not traditional data science, but we will cover it because it's an important aspect of data science with the idea that the the part of deploying a model and seeing what the results are would be like an experiment, right? It would be we think of it as an experiment where I build some model, see what the results are on a different group than a kind of a baseline control group that's not exposed to that model. So it's important for us to know what it is. You could argue the actual process of doing A/B testing is not really data science, but if you add in that context of usually people are interested in using it in conjunction with building a model and exposing it to users as an experiment. Um, does that make sense? Yep. Okay. Very good. All right. All right. Let's go into each of these steps and talk a little bit more about them. Okay. So, excuse me. Usually things start in the beginning with a problem definition, which is a goal or a question that will be addressed through collecting and analyzing and deriving insight from data. So that's the very first step, and usually this is actually something that you would work together with other uh, colleagues usually to come up with. So usually you may come up with this with like a product manager or with another engineering group or something like that to come up with a problem like, hey, we need to build a recommendation system for our users to get better recommendations for their movies or for their shows or for the products on our website. So there usually is going to be a question or a goal, or hey, we want to come up with a sales forecast for the next 3 quarters, given the data we already have for this quarter or the previous quarters. So usually you have to start with a problem. So you have to start with a problem definition that you want to address. And honestly, that goes hand in hand with the next step, which is once you have a problem in mind, you then have to collect data around that problem. So you have to gather the relevant data sets, which could also involve working with external partners to do that. So maybe you have to work with data engineers to help you go out and collect that data or make that data accessible. You may have to work with, you may have to do it yourself and go and gather historical data that can help answer that problem. So it sometimes this is up to you. You have to go and go out and collect that historical data or that data that's relevant to your problem. That is totally possible. But sometimes you're also working with external partners, like a data engineer, to make that possible to go and collect the data. But of course, the key word here is relevant, right? The data needs to be relevant to the problem that you're solving, and that can be a challenge. So I know these are listed as the first two steps, and they seem pretty straightforward, but they can be the most challenging at times, is defining the right problem and collecting the right data, getting that available. It's not always trivial. But in this course, we'll usually assume that we have these two things. We'll usually assume that, yes, there's a problem we know we want to address. For practice purposes, we have that. And then we also have data already available for us. We don't have to go out and fish for it and collect it and scrape it from somewhere. We'll assume that's already been done, and we're just using the data that we have available. So in this course, these two steps will usually be done for us, uh, mainly just for so that we can practice all the other steps. But in the real world, that would usually be, someone you're working together to formulate a problem with external stakeholders, and you're also gathering data either by yourself or with the help of maybe like a data engineer or someone like that. Okay. So again, these two things we'll usually have uh, in this course. Which leads us to the next phase, which is that data preparation phase. So this is where I said we need to clean the data and explore it a little bit. So usually this process can take some time. So it can be a very time-consuming process. But the typical tasks we're doing here are getting a handle on any missing data. So figuring out a strategy to handle missing data. We'll talk about that. How to identify and handle outliers. We'll talk about that. Maybe duplicate data, inconsistent data that doesn't make sense. We can identify that. We can get rid of it or have some strategy to handle it. So getting a handle on cleaning up our data is going to be an important task, and that might take some time. That might take some time to work with our data and kind of do some. We have to learn how to do the proper code, clean it up, get it to a good state. And then once we do that, we can start to explore it a bit to gain insights. And this is where we'll usually use visualization at our disposal. So maybe we'll build some graphs to quickly visualize, get some patterns, see what the data looks like, figure out if there's any relationships in the data. That's what we'll learn about visualization that will really help us. So when we say explore, we're mostly talking about building graphs to help us kind of tell a story about what we see in that data, assuming that it's been cleaned up, right? Assuming that we have it cleaned up, we've removed all our missing values, outliers, inconsistent values. We now have a clean set of data. We can start to explore it. So usually doing visualizations. It could also be, it's not only visualization, but it could also be summaries. So maybe it's really useful to tell a story like what is the average for all these users, or what is the average sales for the last few weeks? What is the median sales? Like those kind of statistics might be really useful summaries to tell a story about the data. Okay. Okay, so we have our steps here: problem definition, data collection, cleaning, exploration, first three steps. Any questions about those first three steps? Good? Okay. All right. And again, we're gonna like as we go along, we will deal with these problems. We'll have actual examples that will deal with this process. So we'll see this process from end to end many times as we get into our examples later on. Bronze, silver, gold. So usually those are like data engineering terms to refer to the basically how clean the data is. So like bronze is kind of like the rawest form. It's usually like data that has not been aggregated in any way. It's usually pretty raw. It hasn't been cleaned up in any way. Silver might be cleaned up, but not really aggregated. So silver might be like we've removed missing values. We've removed outliers. So silver is a bit cleaned up, but it's still kind of raw. And then gold would usually be like our final transformations have been applied to it. Like maybe we've done some averaging, we've done some transformations. So usually those are terms that you see to refer to the different like stages of quality. Gold being like the highest quality, like the final data set. Yeah, model will run on gold. Yep. Yes, that's true. By the way, we don't really use those terms too often. I think you see those terms a lot in like data engineering. Don't really see them that much here, just because the assumption is that we're always going to clean up, like our models aren't going to be good unless we get to a gold state, right? And unless we clean up our data, unless we do the right transformations that make sense, like our models really aren't going to be useful until we reach that state. So we're always going to be pushing to like clean up and get to a good state. Okay. So we have one, two, three. Let's look at the next few steps. So once our data is clean and we've explored it a little bit, this is step four, which is feature engineering. So this is the other kind of data preparation step that I talked about. So feature engineering, what is that? It is a creation or transformation of new features. So you might ask, what is a feature? A feature is just a variable that is an input to a model. Okay. A feature is just an input. So I want you to think of like in an Excel spreadsheet, a feature is something like a column. It's an independent variable, like a column that we would use to build a model off of. Like that will be one input. We would call it a feature that's going into the model as an input. Okay. So feature engineering is the process of kind of building new features. And those can be by doing simple transformations. Like maybe we do some scaling, like dividing by 10, multiplying by 10. Those are simple scaling we can do to features. We could do more complex transformations, like doing a linear transformation to it. We could take a square root, we could take a logarithm, we could take an exponential. Many different transforms we can do to our data to create new features. And sometimes that makes sense to do that. Sometimes we don't need to do that much feature engineering, but that's something we will get a feel for as we start to do examples. Is like when does it make sense to do feature engineering, and when do we not have to? So feature engineering will be more of an art than a science, honestly. And we're going to do plenty of examples where we do feature engineering to see what kinds of transformations we typically will do. It's part of the current data. Yeah. So everything we're talking about will be part of the current data we're working with. Is it always performed? No. We don't necessarily always do feature engineering, but it is a step. Like we can and we should evaluate if we should. Okay. So will we always do it? No, but we have the ability to do it, and it's a step worth calling out because it can be very valuable to do. So again, we haven't learned how to do that yet, so it may not make that much sense to us, but I'm calling it out as a very important step in the process. And as we start to do examples later down the road, we're going to come back and spend some time on feature engineering because it is an important step. It is an important step often to do it. Okay. Yeah, I see how it can be a little confusing. Yeah, feature is in data science, feature is just a variable. It's like an independent variable that's an input to the model. Yeah. It's a little bit different of a meaning than like a feature, which is kind of a new piece of software you're adding to existing software, right? A little bit of different uh, terminology there. Okay. So this was step 4, and this was data prep. So draw a line here because this is all like the data prep, and then these couple of steps here are all modeling oriented. So once we have our data prepared, we've cleaned it up, we've done exploration to determine what we should keep. We've done some engineering to do some scaling or transform the features that we have. We can now build a model. And so this will all be something we will learn in our next, we will learn how to build models in our next course on ML, but just calling it out as, that would be the next natural step is once we have our data cleaned up to derive an insight from it, we may want to build a model off of it. And so that will involve kind of defining a model, training it on this data that we've prepared as step number 5. And then step number 6 will be kind of an evaluation step of determining if we have a good enough model by evaluating it. By the way, this process isn't necessarily linear in the sense that we may iterate here and go back and repeat these steps. So we may go back and forth and keep repeating these by building a new model, determining if it's good enough, repeating and repeating and repeating that process. And we may even go all the way back up to here and build some new features if the model isn't doing that well either. That may be possible. So by no means is this process always linear. We may repeat, especially this model training and building and evaluation steps. We definitely can repeat these back and forth until we kind of converge on a good enough model. That's something we'll discuss when we get into modeling. I don't want to go into details now, but that is suffice to say, like we can iterate those steps quite a bit, and we can spend a lot of time on it for sure as a data scientist. Okay. And then, oh, by the way, there's one more. So there should be a step here on deployment, which is kind of mentioned here, but I would argue it's its own step. But once we have the model done, then we can kind of deploy it. Now, deployment means a lot of different things. There's a lot of different ways to do that. We won't get into that till much later in the program. It's not really going to be a focus for us at the moment. We're mainly going to focus in on all of the data preparation steps and then all of the modeling, and then leave this part till kind of the very end of the program. Okay, but it is important part. Like we need to make you once we build a model, we do want to have it be useful in the real world. So we need a way for it to be integrated into existing systems, which can be different. There are different ways to do that. Um, what is the percentage of the model has to see for? Oh no, that's not a silly question at all. It's really like your tolerance for if you think it's good enough. So for instance, I've worked with people where we've deployed models that have been like 70% accurate, and that's okay because we just want to get something out there to test with and to have results. So yeah, like the target percentage is different depending on the problem. That, by the way, that's something we'll talk about when we get into our next course on models and evaluation, because it turns out there's different ways to evaluate the accuracy. Like sometimes we care more about, it's not about overall accuracy, but more about like, are we limiting our false positives versus false negatives? Because sometimes a false positive is going to be more costly than a false negative, or vice versa. Like a false negative may be way more costly than a false positive. So we're going to have different ways to evaluate our models, and that can lead us to different thresholds. But like it doesn't have to be perfect. I've seen a lot of models deployed at the like 70% range, 60% range. That's okay. Mainly the reason to do that, by the way, is to get something out there so that you can iterate on it, right? You get something into production and then you can iterate on it after the fact. So you don't want to spend forever waiting for it to be perfect. Okay. All right. Any questions about that process? I know we haven't covered all the details of it, but just remember right now it's, we formulate a problem, gather data, we do data prep, then we do modeling. And the data prep is going to be something we will focus heavily on in this course. Okay, for the moment, the data prep will be something we really key in on in our last couple of lessons. Okay, things like data cleaning, things like feature engineering. Any questions? Will we cover precision recall? Yeah, we will, just not now. We'll cover that later in machine learning when we get to model evaluation. Yeah, really no need to cover it now. So we're not building any models yet. Okay. All right, so let's go back and circle around to Python. I know, we spent some time on it already, but just to reiterate that Python will be our friend here when we're doing data science. So it's going to be the preferred programming language for anything data science, and that's true in the industry. Um, Python is widely used, mainly because it has so many great packages to help us work with data, namely NumPy and Pandas, which are the first two we will look at. And then it has many others to help us build models like Scikit-learn, uh, which we'll get familiar with. And then it has others to do visualization that we'll study. So it basically has packages that do most of the tasks for us that we're interested in doing. So that, that's why we'll stick with Python. It's really great for data science. So we've talked about this before. Why people prefer to use Python is because it's open source, interpreted. It has so many great packages that are oriented for data science and can help us do data science really easily. Um, a lot of people used to use R to do data science, but it's been a shift over towards Python because of its flexibility. Python can integrate with other systems pretty easily, whereas R is more difficult to use. Um, yeah, R is like it's like a scientific um, analysis language. Um, you know, it's it's used in a lot of like statistics. A lot of statistics people like using R, but for doing data science, it's almost exclusively done in Python. So there's really you don't see R too often. I've really never seen it. I've only seen Python in the industry. So no worries about the R. Historically, R has been around. R has been around for a while, but Python is by far and away the most used data science language. I've for sure. Okay. So I want to briefly tell you about some of the packages that we are going to study in our course that are in Python that we will use to do data science. So I just want to briefly talk about them, and then of course we're going to have a couple of lessons dedicated to going into those, like NumPy and Pandas, and all the visualization libraries. So the first one is NumPy. So NumPy is short for numerical Python. So that's why it's called NumPy, the numerical Python. And it is a Python package for doing computing, basically scientific computing, using these array structures that NumPy has created, and so many things are built off of NumPy arrays and the ability to operate on these NumPy arrays. So NumPy came around and created these multi-dimensional arrays, which are essentially like matrices, and also had a lot of different computing tools around the matrices and arrays that so many other packages are built off of. So we're going to learn Pandas. Pandas is built off of NumPy. So is Matplotlib, which is for plotting, and so many other packages are built off of NumPy. So it's a really foundational package for working with data, because data will be stored in NumPy arrays. The NumPy array is the kind of foundational data type of NumPy, and so many things work with NumPy arrays. Okay, so we're gonna have a whole lesson dedicated to NumPy coming up next, but NumPy is going to be the first place we're going to start, just because it's so important for working with data. Its multi-dimensional arrays are so useful for storing and manipulating data. Um, so it's pretty important. What is a Fourier transform? It is a transformation of data into like a signal, basically like a signal transformation. So you go from like basically like a time series into like a frequency series. It's used in signal processing. Yeah, analog to digital. Yeah, pretty much. Analog to digital. Yeah, it's used in signal processing. Okay, so the second package that we will study, so we'll start with NumPy. We'll start with that today. So right after this lesson, we'll dive right into NumPy and start working with examples of the NumPy arrays. But right after that is the library Pandas, which we'll spend a lot of time with. Pandas is a library built off of NumPy, so it depends on NumPy, and it basically comes around and provides a more structure to manipulating data. So if you're, like I said earlier, if you're familiar with Excel, Pandas has a lot of functionality that mimics what you would do with a spreadsheet. Basically, like structured row column data is what Pandas excels at. So Pandas is going to be a really fundamental package for us to manipulate data that's structured in kind of a row column matrix format, but it's built off of NumPy. So it uses NumPy under the hood to do all the manipulation, but Pandas provides its own data structures to kind of put data into almost like a spreadsheet format that we can manipulate. Okay. So really, Pandas is going to be really, really powerful for us to manipulate data, and we'll use it all the time. So if anything coming out of this course, you guys will be Pandas experts, if anything else. Yeah, I mean, of course, you'll learn more than that, but I think you'll come away as being really, really good users of Pandas and NumPy for that matter, but certainly Pandas. So we're going to study NumPy first, and then we'll have a lesson dedicated to Pandas right after NumPy. So we'll have a lot more to say about it, but I just wanted to kind of preview that, it's a really important package in the data science ecosystem because it helps us manipulate that structured data that's in like a row column format, like a table. Okay. Then another package is the SciPy package, which is short for Scientific Python. It is another open source library that's built on top of NumPy. So it uses NumPy arrays as its underlying data structures to do the manipulations. SciPy contains a lot of scientific formulas and a lot of scientific computing tools that we'll use, especially when we get into hypothesis testing. So it contains a lot of like z-test, t-test distributions, things like that. So it's tailored for that. It also has things like the Fourier transform as well. It has different linear algebra manipulations as well. So SciPy will be really useful when we get into our hypothesis testing and A/B testing. It has those kind of those distributions that we'll need to do our tests, like a student t-test or a z-test or those kind of things. We'll use SciPy for. So really important package. We'll see later when we do hypothesis testing. Another one that is going to be useful from time to time is the stats models package. So it is one that basically has a lot of statistics oriented things. It has some basic models in there, like linear regression or logistic regression. Um, we will generally favor a different package to do those kind of models, but just calling it out that stats models does have some useful stuff when it comes to doing statistical testing. So there are some like chi-square tests or ANOVA tests that we will borrow from stats models that SciPy doesn't have. We can borrow from stats models. So we will use it when we get into hypothesis testing as well. So these last two, so SciPy and stats models, are two packages that we'll use when we get into A/B hypothesis testing. Okay. So that brings us to Scikit-learn. Now, this is going to be our primary package for doing machine learning. Um, so this will be one that we'll build all of our models and machine learning off of when we get into our machine learning course. So we won't really use Scikit-learn in this current course, but when we get into machine learning, it will be our go-to package to do all of our machine learning with. It is a fantastic, fantastic library that's been developed over years to contain all the basic models that we would ever want to build. Scikit-learn is really awesome. So it can build models for so many different use cases. And it's a really easy package to use. It has a really nice interface, really easy interface. So we will see that later on when we get into our next course on machine learning. But just calling it out, that is a very popular data science library, Scikit-learn. So when we get into our modeling, we will use Scikit-learn. When we do our data prep manipulations, we'll be using NumPy and Pandas. Finally, for visualization, we will be using a library called Matplotlib. So it is kind of the foundational Python plotting library that borrows inspiration from MATLAB. So if you guys have ever used the MATLAB plotting, it's actually very inspired by that, hence the name Matplot from MATLAB. But it's going to be our main tool for using for building graphs. Okay, so it's a foundational library for building graphs. Almost every other library that does visualizations is built off of this one, built off of Matplotlib. So when we get into our visualization course, we will come back and talk a lot about Matplotlib and practice with Matplotlib quite a bit. Excuse me. What is that course called? Machine learning. The next course is called machine learning. Okay. And then another visualization library that we will lean on heavily is the Seaborn library. This is one that is built on top of Matplotlib. So Matplotlib is kind of like NumPy. It's the foundation, and then a lot of things are built on top of it. Seaborn being one of them. Excuse me. Um, Seaborn being one of them, and it basically has just better aesthetics. It provides better, not only like better aesthetics than just basic Matplotlib. It also has more scientific kind of plots and more interesting plots than the regular ones you get out of the box with Matplotlib. So it has really interesting histograms, file implots, heat maps. It can do statistical error, like confidence interval bars. Um, so it just builds better plots than basic Matplotlib. Matplotlib is very basic. It's really easy to use. You know, you can build a lot of plots with it as we're going to learn. But Seaborn is really nice. It makes things aesthetically pleasing, and so we'll also use Seaborn from time to time. It's another plotting library that we'll get some practice with when we get into visualization. And another one of those is Plotly. So we have Seaborn and Plotly both built off of Matplotlib in order to do plots. Now, Plotly's specialty is for building interactive graphs. So when you build a Plotly graph, you can actually, it'll pop up in your web browser, kind of like Jupyter Notebooks do. And you can click around in the graph and mark down points. You can zoom in, you can zoom out. Excuse me, just getting over a cold here. So don't mind the coughs. But you know, you can zoom in, you can zoom out, you can do a lot of interactions with Plotly. So if you want to build an interactive graph, Plotly is a good package. Again, it's built off of Matplotlib. So we'll get some practice with Plotly. So these three we're going to practice when we get into visualization. Seaborn, Matplotlib is the basic foundation. Seaborn and Plotly both build off of it. We'll get some practice with all three of those when we get into visualization. Um, so the rest of these slides just go through some plots that we will be building later on when we get into our visualization. So just wanted to briefly go through those just to show you some of the different types of plots we'll do. So the easiest kind is basically a line plot that connects different points. So this would be like if we were plotting out something over time, like a stock price or a sales value over different quarters or weeks, temperatures over time, something like that. So basic kind of plot, we'll be able to build that, no problem. We can even mark different points on those. That'll be easy to do with Matplotlib or Seaborn or Plotly. That'll be really easy to do. So again, we'll show you how to build these with code later on when we get into visualizations, but just showing you the possibilities right now. Scatter plots will do these, which have different points kind of scattered throughout on two axes here. This is usually helpful to figure out how the data is kind of maybe clustered together or figure out if there's relationships between two variables, like if they tend to trend the same direction or in the opposite direction, or if they're kind of just distributed all over the place. So we'll be able to build scatter plots. That'll be helpful. Area plots that show like cumulative areas on top of each other, we'll be able to show that. That'll be pretty easy to graph for different, maybe tracking total sales over successive quarters. showing different contributions of categories we'll be able to do. So we'll be able to do an area plot, basic bar plot we'll be able to do. Again, all of these examples were built using Matplotlib, so we'll be able to do that. But they have equivalent versions in Plotly and Seaborn, so again, those are built off of Matplotlib. So we can even put grids in the background to show to kind of assist the viewing of it, to give an idea of where the different points are in the grid. So that will be easy to do. Histograms. Now, histograms are going to be extremely useful for us. We'll build histograms a lot because they will help us visualize how data is distributed, which is extremely important to know. Is it kind of distributed like this in this picture, which is kind of like a bell curve, or is it flat? Does it have kind of two peaks to it? Knowing this distribution will be extremely useful to us. So that we will often build a histogram that kind of looks like this. So histograms will be extremely useful. We can build pie graphs, which show different percentages. There may be certain situations where that makes sense. We're telling a story of our data. It makes sense to use a pie graph. That'll be easy to do. Again, these are all just examples of what's possible. We have to show you how to build these, and we will when we get into the data visualization lesson, which is what this kind of note says at the bottom. Once we get into that lesson, we will show you how to do the code to build these. Okay. So just to wrap up this first introductory lesson, we have shown you what data science is, which is kind of the extraction of insight, deriving insight from data. And we have a bunch of different packages that are going to help us do that. We also have a process, which is going to help us do that, which is usually defining a problem, collecting data, doing data preparation, and then doing modeling after that. So, basic foundations at this point. What we're going to do is now go into NumPy. So we're going to start with NumPy and then go into Pandas after that. So we're going to start studying these packages. They're going to help us do some of these different tasks in data science. Any questions at this point? Okay, I'm going to open up our next lesson then, which is actually going to be, so if you guys notice, the next lesson is actually going to be, lesson 3 is broken into several different notebooks. So we're going to be transitioning into notebooks for some of these guys. Do you guys have those notebooks, the lesson 3 notebooks? I can try to share them with you guys if you don't. Or does anybody have the folder and want to share it for those that don't have it? It should be a collection of several notebooks. Yeah, let me download it. Okay, so give me a moment. I will upload it. I have it right here. Um, okay, I just uploaded it. Okay, so you guys should have it. So you want to open those notebooks. Again, you can open it wherever you want. You could do it in your own local Jupyter. You could do it in the lab environment. You could do it in Colab. I recommend Colab just because it's so easy to work with, right? So I recommend opening them up in Colab. That's what I'm going to do. I think it's just so easy to work with. So that's what I'm going to be using. All right. Can everybody see the screen? I'm on the first notebook. The 3.01 notebook is the one we're going to start with. The introduction to NumPy. Okay. So if you have a moment, you want to open that one up. Again, if you're working in Colab, you can upload the notebook. So you can like once you've extracted that folder, you can upload the notebook into Colab using this like file upload notebook. That should work. Or if you have Google Drive, you can just upload that folder into your Google Drive, and then you can just launch it through your Google Drive, and it should open it in Colab. That works too. Are people able to open the notebook? Yeah. Again, it doesn't matter where you open it, just as long as you can, and you can run some of the cells, because that's we're going to be running them. Good, good, good. Okay. All right. So let's talk about NumPy. Now, remember, NumPy is the open source library that is used for doing, um, that is used for doing math and scientific computing on basically these arrays. So we are going to take a look at the NumPy array object as the first thing that we'll look at. Now, the NumPy array object behaves very similar to a list. So we learned about lists in our previous course, and the NumPy array is very similar to a list. We can slice it like a list. We can access elements like a list. It's ordered like a list. But it's a lot faster to do mathematics with the array, and it comes with a bunch of built-in functions like mean, median, mode, all these special things on the array that we don't get with a list. For instance, Python lists do not have a notion of an average. You can't calculate the average of a list without doing a manual calculation. So, but a NumPy array has a mean function that comes built in that we can take the average. NumPy has like an average function that we can take of an array or a median or a mode. So arrays are really advantageous to work with inside of NumPy. Um, so uh, let's take a look at some examples of a NumPy array. So in the first cell here, I want to point your attention to two things. One is that in order to use NumPy, we import it. Do you see how we import NumPy? And we do this thing called as MP. Now, what this is we do an alias. This is called an alias NumPy as NP. We basically shorthand it to NP, which is an industry standard. So anytime you're looking at code and you see NP dot something, that is short for NumPy. So in the industry, if everyone is going to shorthand NumPy to NP. That's just what people do. So as is the way to alias and import so that when we use NumPy in our code, we don't have to type out the full word NumPy. We can just do NP. So that's why you see NP here is because, and really throughout our code, we use NP. You see it all over the place. It's a shorthand alias for the NumPy package that we're using. So we are importing this package, meaning that we are going to use it in our code, but we are aliasing it to NP. This is the industry standard to do. Most of these packages have a nice alias to them. Like Pandas will have an alias, Matplotlib will have an alias, just to make it shorter. Do you have to import it in VS Code? if you're using VS Code to run your notebooks, yes, you have to upload it there. You want to open in a VS Code? Yeah, you're gonna have to open the folder where it exists. But that's if you're using VS Code, like you don't have to. But yeah, if you want to, yes. Okay. All right. So the next thing I want to point our attention to is building a NumPy array. So notice that we can build this NumPy array by doing np.array. So np.array builds a NumPy array object. And what we're passing in is just a list of data. Okay, so we have a list of integers that we pass into this NP array, which will build a NumPy array out of this list. So NumPy arrays can be built out of lists, they can be built out of tuples, they can be built out of other NumPy arrays. There's many ways to build a NumPy array, but the most common is to pass in a list, to convert a list into a NumPy array. So here we are building a NumPy array from a list, which is pretty typical. By the way, you guys remember I said that I'm going to be writing a lot of comments. I'll share these notebooks in our Slack after the classes. But I encourage you guys to do the same thing, is to write comments in your notebooks. Okay, try to write comments in your notebooks to outline what the code's actually doing. How do you install NumPy? You just need to do, so inside of a cell, you can run this command like pip install NumPy. Try running that inside of a Jupyter cell. Yeah, this command is not going to work for you because this is like a generic. This is on Windows, like a generic Windows command. Um, but if you're inside, are you inside of a notebook, Mariel? If you're inside of a notebook, just run this inside of a cell. It should install it. Yeah, that works too. You can open your terminal and do pip install. If you do that, you'll probably have to restart your kernel. No, so Colab comes with NumPy already installed. Yeah, so that's another advantage of Colab, is it already has that installed. We don't need to worry about it. Yeah, so if it says requirement already satisfied, which is what this is going to say if I run this, it's because it's already installed. So this means that I already have it installed. Yeah, you already have it installed. Yep. Yep. So in Colab, it already exists. This one, new cell in this command. If you can't get it to work in your VS Code, I really encourage you to do collab as much as you can. Just to get something that works. Because NumPy is already installed in Collab, so there's really nothing you need to do extra. Thanks, Tim. That'd be great. That'd be great. Okay. All right. So this builds, going back to this builds a NumPy array off of a list. So if we run this code, what's happening is we are building an array and storing it in this array variable, and we can print the array. Now look at what the array looks like. It kind of looks like a list when we print it, except the way we can tell this is a NumPy array is that it does not, when we print it, it does not have the commas. Notice that the data in there does not have the commas, and that's because it's being treated as a NumPy array. So it doesn't have the commas. It's not, at that point, it's now an array, it's not a list. So it looks slightly differently. And you can even see when we print out the type that this array is actually a NumPy n-dimensional array, which is the foundational data type of NumPy. So this is an NumPy ND array, which is the foundational data type of NumPy. So we have created a NumPy array, and now you can see what its type is this MP ND array. Okay. Were you guys able to run this first cell if you run it? It's not going to do anything but show this. You should see this, and then you should see it's printing out the type. You should see those two things. And do we see how that this is creating a NumPy array? So np.array is that's the function we use to build a NumPy array. And we're passing in a list of data to build that array. All right. Yeah, it might take a moment to start up the kernel. All right. Any questions on this so far? What was ND array? It's short for n-dimensional array. It's the NumPy array object type. So that is the data type that we are working with now is a NumPy n-dimensional array. It's a generic NumPy array data type. And you can see that because we do type, and we can see that we get a NumPy ND array as the type of this thing when we create a NumPy array out of it. So ND array is short for n-dimensional array. Okay. What I wanted to do is go to the next cell and talk about how we can create some matrices, essentially multi-dimensional arrays. So this array that we've created so far is actually just a one-dimensional array because um, it only has one dimension to it. It basically has one list of data. But of course, we would be interested in working a lot of times with multi-dimensional data because that's typically like what a spreadsheet has, right? Rows and columns. So just to give you guys an example, like NumPy actually supports 0 dimensions, which is basically a constant. So a single number, a single value is considered a 0D array. So a single value is considered as 0 dimensions, is just a single value. So if we built a NumPy array and just passed in a single integer, or it doesn't have to be integer, it could be float like 24.6, whatever it is, that would be considered a 0 dimensional array. But we've already built a 1D array, which is just a single list, basically a flat list with, so just if we use a list with a list of, I should say a single list of values is a 1D array. So we've already seen that. It is a scalar. Yeah, we would call that a scalar. Yes. Good. Yes, that's true. Scalar. Perfect. Perfect. So a single list of values is going to be a one-dimensional array here. Now, what gets interesting is now when we do a list that has list as its elements. So this is a list of lists is now a 2D array. So I want you guys to see that how we're building a NumPy array out of a list, but look at what the elements of the list are. They're actually lists themselves. So you see how within this overall list, the first element is a list that is 111. That kind of mimics basically like a row. So you think of it as like each list is like a row in a matrix. So this two-dimensional array is really like a matrix, right? So this is an interesting use case where, of course we could have more than just these two. So we could have a third list here that is like 4, 5, 6, and that would be valid as well. So this would be basically a matrix that has 3 rows, and each row has basically three items in it. So we would think of it as basically having 3 columns, right? So it's like a 3 by 3 matrix, but it is 2 dimensions. The two-dimensional array. It has rows and columns at this point. So it has rows and columns. The two-dimensional array. Let me ask you guys, do we see how this has 2 dimensions to it? It's a list of lists. So it has 2 dimensions. Does all the lists need to have the same rows? What do you think? What do you think would happen if, let's try it. Let's try making this a smaller dimension. Do you think this is going to be allowed? Is this what you're asking? Like can this be a shorter dimension? Let's see. So yeah, this gives us an error. So yeah, you're exactly right. This will give us an error that the dimensions do not match. So this is not allowed, but let's see if I add in the 6, this should now be okay. And there it is. This is now okay. No more error. Okay, no more error. So yeah, it's still going to be an error if the shapes do not match. So again, if we made this a smaller one, that's going to be an error. And it's going to tell us that we have one dimension that is inhomogeneous, meaning it doesn't match. It's not the same. We have one dimension that's not the same. Its shape doesn't match. It's not correct. So therefore we should correct that. and make sure it is matching. Okay. So that is a two-dimensional array, list of lists. And by the way, that doesn't have to stop there. We could keep going. So now we have a three-dimensional array, which has lists of lists of lists. So it basically has one of these matrices as each element. So see how this has basically an overall list. So this has it has a list where each element is a 2D array, right? Each element is a matrix. So here is one of those matrices is the first element, and then here is another 2D matrix that is the next element. And this forms a three-dimensional array. So if we print this out, we can see that we get this 3D array where this matrix is the first item, this matrix is the second item, and on and on and on. Didn't understand how 2D is different from 3D. Do you see how, okay, so do you see how with the 2D, basically we take this whole thing and that's just one element of the 3D. This 2D matrix is one element, and then we have another 2D matrix as the next element. So we have matrices are now the elements of the 3D array. Whereas look at what's the elements of the 2D array, they're just lists. It doesn't have to be two. That's just the example we have. It doesn't have to be two. But by the way, one thing that gives away the dimensions is how many of these brackets we have. So you see how we have two brackets and see how this has three brackets? Yeah. Oh, you guys got it. You got it. Roberto, perfect. Yep. You guys got it with the brackets. So what's an example of using a 3D array? Yeah, so something that uses a 3D array would be like a batch of images. So let me give you an example. So an image is like a 2D array because it has pixels, right? It's basically an image is broken down like this that has pixels with whatever resolution. And so if we have a collection of those, it's like we have a collection of these guys is a 3D array. Like if we have 100 of those, it's like a 3D array. Does that example make sense? Like a collection of images would be a 3D array because every image is a two-dimensional matrix of pixels. Yeah, a 3D array is a collection of matrices. Yep, exactly. Does this example make sense though? Like this is a good one, I think. I'm glad you asked it because I think it's a good one for thinking about what a 3D array is. Every element is a 2D matrix. What is the maximum 2D element in a 3D array? I'm not sure what you mean by that. Maximum 2D element? Oh, how many can you fit in a three? You can have unlimited as much as the memory will allow, basically, as much as your memory will allow. You can have unlimited. You can have as many matrices in a 3D array as you want until you run out of memory, essentially. Okay, perfect. All right, perfect. So just to recap this, we have the NumPy array. So we're able to build NumPy arrays using the np.array, and we're able to take a list of data and populate it into an array. Um, and then what we're going to do is just build off of this to learn how to manipulate that array and do different things with that array coming up next. All right, so let's go to the next notebook. Let's go to 3.02. Before I do that, any questions, any other questions about this building an array? Okay, perfect. So let's go to our next notebook. Okay, do you guys have the 3.02 notebook? Do you have it up? That's the next one we're going to do. So take a moment to pull that one up. Yep, I see some thumbs up. Nice. Okay. So we're going to build off of that NumPy array by taking a look at some attributes of arrays. So assuming we have an array, no matter how many dimensions it is, what are some attributes of this array that are useful to us? Okay. So let's take a look at an example where, again, here we import NumPy and we're initially making a 2D array, right? So we make a 2D array. So then what we're going to do is print out a bunch of the attributes about this array. And we're going to explain what they do. So the first is, if we ever want to know how many dimensions an array has, there's actually an attribute for that, which is called ndim. So if we just do dot ndim, by the way, let me call that out here, is we access attributes of an object by using the syntax object dot attribute. So in this case, we have our array is our object. So it would be like i.e. array dot shape would be an attribute. Shape is an attribute of the array. Array is our object here. Okay, so that's our syntax to access different attributes. So the first attribute we're going to learn about is called ndim, which gives us the number of dimensions. And so when we print that out, you can see what it's going to be. It's going to be 2. And that makes sense. It's a 2-dimensional array. Could the 2D array be, yeah, that's fine. That's fine. You could use that. That's still 2-dimensional. Yep. Okay. Um, so the first is ndim, which gives us the number. This gives us the number of dimensions, which equals 2 in this case. Okay, and that makes sense. We know it's a 2-dimensional array based on the fact that our elements are 1D lists. So we have a list of lists. It's going to be 2 dimensions. Now shape gives us the uh, quantity. So it gives us basically the number of rows and columns. So in this case, what this is saying is we have 2 rows and 3 elements in each row. So shape is giving us an idea of how many elements we actually have, or what the shape of this matrix is. That's why it's called shape. So in this case, we have a 2D array that kind of looks like this, right? Where we have 1, 2, 3, And then in this example, 4, 2, 5. So we have two rows, and we have 3 columns. 2 rows and 3 columns. Hence, we get a shape of 2 by 3. Does that make sense? 2 by 3. Yes, Roberto, that should be true. Yes, that should be true. Yep, that should be true. Okay. So shape is going to be incredibly useful as we go forward because there's a lot of times where if we have an array, we actually just want to know how many rows and columns it has, which is the shape. So the shape is a good attribute to know. Um, does the bracket define it as a 2D versus 3D array? It's the fact that it's 2 brackets defines it as a 2D array. It has 2 brackets here. It's a list of lists. This is 2D. It can. So sorry, yes. A 2D array can have more than 2 rows. Yes. It's the fact that it has so I meant to say that in this shape we're going to see 2 entries. Sorry, in the shape we're going to see 2 entries. Yeah. Let me correct that. So the dimensions will match how many entries we have here. So if we have two entries, because it's two dimensional. That's what the truth. That's the thing that. Um, so sorry, Roberto. I was wrong on what I told you. It is when we have 2 entries here. That's because it's 2 dimensions, not the fact that this is a 2. It's 2 entries in the shape. By the way, how can we get a third row? We could just add in another list here, right? So if we add in another list that has 3 elements, like 7, 8, 9, this is still a 2-dimensional array. But what I want you to notice is that it's going to turn into this shape is going to turn different and this size is going to turn different, but it should still be 2D. So see how this shape went from 2 by 3 to 3 by 3? Yeah, the size is going to be the product. That's true. That's true. I was going to get to that next. What is the shape with 3 rows? It's just 3 by 3. Do you see that now, Mario? Do you see it? It's 3 by 3. With this has a third row. It's now a 3 by 3. Yep, 3 rows. 3 rows with 3 elements each in a 2D array. Perfect. Yep. So now I want to talk about the size. The size is the total number of elements in the array. So in this case, we have in this case we have 3 by 3, so we have 9 total elements. So this will always be the product of the shape, right? Lots of questions. Let me see. I'm trying to keep up. Yeah, you can have as many rows, columns as you want. Yep. No limitation. Do you have a real world example of a 3D array? Yeah, it's the one I gave earlier. It's like a batch of images would be, which we're going to work with images quite a bit when we get into deep learning, is a 3D array because it is an array that has as its elements these matrices that are pixel matrices, right, of different resolutions. That's a 3D array, is a collection of images. Because these are each 2D. That's a real, so images, these are all images, usually are in a 3D array. All the arrays in the same dimension needs to be of equal shape. Yeah, they do. So yeah, we saw that example earlier. Like if we try to change the shape, like even in a 2D sense, if we got rid of this would be an error, right? This gives us an error. We need this to match the size, right? We need this to match the size in order to build the array. Yep. Okay, do we see what size is? Size just gives us the total number of elements. Okay, total number of elements, which is really just a multiplication of the shape. There's 3 rows, 3 items in each row. So a 3 by 3 is 9 total elements. Okay. So that's the total number. The size is the total number of elements. Now the D type is telling us what every member's type is. So maybe not that interesting, but this is kind of the default. So this gives us what element, each element's data type. So we can grab, in this case, they're all integers, but they're in int64. So we can also grab how many bytes each one takes up, which is the item size attribute. This is each element's memory footprint, each element's memory size, which is going to be 8 bytes. And we can also get, if we want to, very rare we would actually need to access this, but we can actually get the memory reference for the array data. So array.data, we won't really ever need to worry about this, but this is actually really important for Pandas to be able to access later on because everything in Pandas is built off of NumPy. It needs to manipulate the raw memory often in order to do different calculations with that data. So it typically will need access to that data attribute, but we generally will never need to know what that memory address is. Okay. Any questions about these attributes? I think the one that we'll use the most is probably going to be shape. We'll probably worry about the shape the most when we're working with NumPy arrays. But any other questions about them? Okay, perfect. Okay, let me show you a couple of functions. All elements in a 2D array must have the same data type. No, they don't have to. Just like a list, they don't have to. When we're working with data, they typically will, but they don't have to. Yeah, you can have that. Try it out. Try it out for yourself. Yeah, you can definitely have that. All right, I want to show you a couple of functions we can do to manipulate the shape of an array. So the first one is we can actually reshape an array using the array.reshape function. So this is a function that we can pass in. So we can do array.reshape, and then we put in the a tuple with the new shape. So in this case, we're putting in 4 comma 3, which is to say we want to take this existing array that is a one-dimensional array. So notice this is a 1D array, and we want to turn it into a two-dimensional array, right? That is 4 by 3. Okay, 4 by 3, meaning there should be 4 rows and 3 columns. But first of all, let me ask you guys, do you think this is even possible? What do you think needs to be true in order to reshape this properly? What do you think? If I want to take a flat 1D array and put it into something that's 4 by 3, how many elements do I need to do that? Perfect. You guys are right on top of it. 12. Perfect. Yep. I need 12 elements. So what happens if I don't have 12? Do we think this is going to work? Yeah, let's try it. Error. And look at what the error tells us. I cannot reshape something of size 11 into shape 4 by 3. It even tells us directly we can't do that. So yes, that is definitely a prerequisite to using reshape, is that you need this total number of elements to match the number of elements that you start with, and then it will work. So if you're going to use reshape, you can reshape into any shape that you want to. So we could even reshape this into 3 by 4. That would be okay. We could do 3 by 4 because that totals up to 12. We could do 2 by 6. That would be okay. But could we do 2 by 7? No, we don't know how to reshape something that is 14 uh into into a shape 12. We only have 12 items. 2 by 3 by 2? Sure, we could do that. That'd be a three-dimensional. We could do that. And now we have a 3D array because we have each element is 3 by 2. And we have 2 of them. So each matrix is 3 by 2. And we have 2 of those. So we could do that. So that's what reshape does, is reshape can take an existing array and move it into a new shape, assuming that the shapes align properly. So reshape can do that for us. So that's actually incredibly useful. We'll use reshape from time to time. And then we can actually do the reverse of reshape. So we can always take something and flatten it out into a 1D array. Okay, we can always do that as well. So the flatten function can take something and put it into, so this will always give us a 1D array. So no matter what shape we start with, we can flatten it out into a one-dimensional version of it, okay, by using the flatten function. So this does a particular reshape that will completely flatten the array. So you can see it takes this three-dimensional array here and goes ahead and reshapes it, or basically flattens it right into this exactly flat one-dimensional array. So flatten always returns a 1D array. Pretty straightforward. Is there any benefits? Yeah, sometimes we want to take something that is in one shape and move it into another because we're going to manipulate it. We're going to assume it has a particular shape to manipulate it. We'll see that later on when we get into deep learning, especially when we work with images or text. It's going to be important to reshape things from time to time. So maybe not this second, but we get into deep learning, we'll go ahead and reshape. Okay, one more I want to show you, and then we'll take a break. Is that there is a transpose function. Now, what this does is it swaps rows and columns. So it transposes this into whatever was our rows. So this 1, 2, 3 now becomes the columns. And so this was a 2 by 3 matrix. It now transposes into a 3 by 2 matrix. So transpose swaps our rows and columns, and that's going to be useful down the road too for different algebra calculations we may need to do. We may need to transpose from time to time. Okay. Any questions on any of these functions? Hopefully they're not too bad. They're straightforward. They're just different reshaping. We have reshape, we have flatten, we have transpose. They just change the shape of the array. So we're going to start with doing some arithmetic operations. So just to show you guys that when you have data in NumPy arrays, you can do element-wise operations, meaning that we can do operations that go element by element, match them up, and do some type of mathematical operation between them. So things like addition, subtraction, multiplication, division, we can do those between elements. So for instance, we have these two arrays of the same size, the same shape, and we can go ahead and add them together, meaning that like this position is going to be added to this position is going to be added to this position is going to be added to this position. Okay, so when we do that, we get basically 40 in every slot because we get 30 plus 10 is 40, 20 plus 20 is 40, and 10 plus 30 is also 40. But look at the syntax of it. There's actually two different ways to do it. You can do the numpy dot add, and then you pass in A and B. So this is this is one way to do it. One way to add is to use np.add, and then you pass in your array 1 and array 2. So you can do that. And so we add those two and store it in the result. And notice that the result is a same shape array, but just with each element added together from the original arrays. So that's one way to do it. The other is you could just do regular arithmetic. So you could just do A plus B. This is an alternative. Alternative is to just use standard arithmetic operations. It doesn't really matter which one you do. I've seen both. Both will result in the same kind of array. So we could store, we could do something like result equals A plus B, and then store that in the result, and then print the result. So it's same thing as before. We get the same array. So you can do either one. np.add A plus B. Either one will do that element-wise addition between the elements. Okay, pretty straightforward. We also have the same thing for subtract, multiply, and divide. So for instance, when we have these, now we have a 2D array. So this is now two-dimensional, but the same exact thing is going to happen. We're going to go through and subtract. This is going to do, this is the same as A minus B. So this takes A and subtracts B from it. So we have 30 minus 10 is 20, 40 minus 20 is 20, 60 minus 30, and then we do 50 minus 40. So we're subtracting those elements in the same positions to get a result. To get a result of this 2D array that is a result of subtracting every element from the original arrays. So again, you could do A minus B, you could do np.subtract. Either way should work. 2D plus 3D, could you do it? Well, you could try it out. So this is a 2D. We could try it out. So let's copy this guy. let's do this guy, which is going to be a let's see. So let's do a 3D array. So let's do one of these guys. And then let's do another one, but let's just change up the numbers. So let's do 10, 15, 20, 25, 30, 45. Let's do np dot subtract A and B. Let's see what we get. So we actually do get a result, and the reason we do is something called broadcasting, which is an interesting idea in NumPy that what they do is they basically will force the shapes to be aligned when you do a mathematical operation, but you might get some unintended consequences of doing that. For instance, we get some of these actually work where we get 30 minus 30, 40, 40, 60, 60. So we get these zeros here for this first guy. But notice that we basically take this and apply it to this. It basically takes this and subtracts to this guy secondarily. So we have 30 minus 10 is 20. And then 30 minus 15 is 15. Sorry, 40 minus 15 is 25. And so the shapes, the dimensions don't have to be the same. Dimensions don't have to be the same, but you can get unintended results. So be careful is the thing I would say. Be careful of doing the subtraction of NumPy will try to force the results to fit by taking this and applying it to this 2D matrix here, right? So it can work. You're just going to get maybe some unintended results that don't really make sense, but are possible in NumPy. If you subtract a bigger value from smaller, it'll give you a negative. Yeah, it'll just give you a negative. So like try doing in this example, what would happen if we put B first? You get negatives. So yeah, it's still possible. You just get negatives there. Okay. So we can take like 30 times 10, 20 times 20, 10 times 30, and we can get those multiplications. So if we do that, we get this array, which is going to be 300, 400, 300. So these are just element-wise multiplications. Again, the alternative is to do A times B, and that would be the same thing. So we just did result equals A times B. That would be the same thing. But we can do np dot multiply to make it more explicit the operation we're doing, that it's A times B. And this is not to be confused with matrix multiplication. So that's something I should call out here is that matrix multiplication is a different matrix multiplication is different and will be covered later. So traditional matrix multiplication will be covered later, and that that requires the matrices to be compatible, and it's a completely different operation than doing element-wise multiplication. Okay, which is just A star B or asterisk B or NP dot multiply. We can do division. So notice that this is again a scenario where the shapes are not the same. We have a 2D array and we're dividing it by a 1D array. Now what happens is we basically take this and divide it by this, and then take this and divide it by this and get this second row. So this size is going to basically match the larger of the two shapes. So this first shape is two-dimensional, 2D. So basically the shape of this is 2x3 shape. And this is only a basically a 1x3. Not even, it's just a 3-element shape. Because it's just a 1D array. So it's a 1D array. So therefore, when we do the division, it's going to do that broadcasting thing that I mentioned earlier and try to force this to be able to divide by this. And the way NumPy will do that is say, okay, which is the bigger shape? This is the bigger shape because it has more dimensions. Try to take this and divide it by these guys. What do you think is going to happen if we reduce this size? If we did this, do you think this would work? If I reduce this down to only having 2 elements, do you think this division would work? We could try it. Error. It doesn't broadcast that way. No. So you could even see it even says it tries to broadcast, but it doesn't know how to. So even with broadcasting, the shapes still need to align to some degree. So this still needs to be like so it needs to be a valid shape to be able to broadcast to each one of these dimensions here. Let's try it. Yes, we can divide B by A. We're just going to take, now this again is going to try to match the shape and just do this divided by this divided by this. But remember that A divided by B is not the same as B divided by A. They're not the same result. Yeah, you can get a division by, so try making one of these zeros. So try, let's say this was all zeros and we did A divided by B. Do you think that'll work? Do you think this will work? Yeah, it basically, now it technically returns a result, but they're all infinity. Yeah, it basically says that we have a warning we cannot divide by 0. So it basically says that sure, you could do it, but you're going to get infinities all over the place, and it's not you get a warning that you're dividing by 0. So it's kind of like an error there. Okay. All right. So let's go to doing exponents. So we can do element-wise exponents where every element in A is raised to a power of something in B. So for instance, we like 2 squared, we do 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. And you can see what each one of those would be is this. So this just does every element in A, each element in A gets raised to the exponent of the corresponding element in B. So we get 2 squared, as I said, 2 cubed, 2 to the fourth, 2 to the fifth, 2 to the sixth. That may be useful from time to time. We may have a reason to take elements from one list and exponentiate them from another list. So there's a power function here to do that. So that may be useful. Before we move on to the statistics functions, which are going to be really interesting, any questions about the arithmetic? Are they kind of straightforward? It kind of makes sense in terms of the arrays. Any questions on them? Hopefully they're very much like just regular arithmetic. They're not too bad, hopefully. Can you build arrays from set of arrays? You mean like a Python set? Oh yeah, you can. Yeah, you can build arrays from arrays. Yeah. We haven't done that yet, but I think that's coming up shortly. Yes, but you can. Yeah. Yeah, it's not too hard to do that. So in fact, I can just show you a quick example of that. So we could call a NumPy array uh from an existing so we could have inside of a list we could have np dot array and then we could have 1 2 3 and then we could have an np dot array and then we could have 4 5 6. So this should make so if we then we let me display x. So this makes a 2D array. Does this make sense? Like I'm defining an array as the input elements to build an array. So yeah, you absolutely can do that to build a new one. Yep. Okay. Good question. Any others before we go on to the statistics functions? All right. So what's great about NumPy is with the arrays, it can easily do statistics on arrays. So it can find the medians, it can find the average, it can find the standard deviation, it can find the variance. Now I know we haven't technically defined what each of those are, but that's okay. Um, it's useful to know that given the different statistical functions that we may want to do, NumPy can easily compute them on collections of data, collections of arrays, right? Or data that's inside of an array. So for instance, if we have this 2D array here, we can compute the median of all elements in the array, which would be np.median. So there's a built-in function from NumPy, np.median. So we can do np.median finds the median of an array. Okay, so this will calculate the median. So if you're, again, we will get to what the median is later on in our statistics overview later on, but the median is kind of the 50th percentile, like the middle element, right? The middle element of we basically order it from least to greatest and find that middle element. So in this case, the middle element is 4 out of all these elements that we have. Okay, NP dot median. We can take the average, which is the mean. So that's very nice. We can take the average. So we can do NP dot mean, which will take the average of this array. So it'll average all the elements together, and we get an average of 6.3333. So that's very convenient for us that we can compute an average of an array. I want you to, now this seems really straightforward, but I want you to see how powerful this is that lists, for example, do not have this ability. There is no built-in mean function for a list. So that's why this is so useful that NumPy has this ability, and it's really optimized. It's really fast to find the mean, really fast to find the median. It's a really optimized function to do it. If we wanted to find the average, we would have to do it manually on a list. We'd have to total up all the elements and divide by the size of the list. Not that that's hard to do, but it is something manual that we would have to define. It does not automatically exist like what we see here with np.mean as a simple function that we can apply. And we can apply it to NumPy arrays very easily to compute the average. So same thing with standard deviation and variance. Those are more advanced statistical functions that figure out the spread of the data away from the average. Again, we're going to learn about these later on, but np.std does the standard deviation, and then var does the variance. So, and really the standard deviation is the square root of the variance. So if you took this variance, sorry, if you took the standard deviation and just raised it to the second power, you would get the variance. But you can compute them separately this way. Okay. So pretty convenient that NumPy provides those statistical operations. We're going to be using these quite a bit. Especially when we do like exploration of our data and we want to find an average, we want to find what the standard deviation is. This is going to be really useful to use the NumPy function to compute that on an array of data. Okay, really useful. All right, any questions about these guys? I mean, they're pretty straightforward, but I know we haven't defined exactly what these are. We will later. So no worries if you're wondering exactly how to calculate these. We'll talk about that later, but any questions about the NumPy functions themselves? Okay. Very good, very good. Okay. Let's talk about percentile then. So NumPy also has a percentile function. So we can take an array and compute the 50th percentile, which would be the median. Again, we haven't learned what a percentile is, but if you think about ordering all the elements and figuring out like the median is at the 50th percentile, and then half the data is below that. So there's a point where like 25% of the data is below this certain value, and then 75% of the data is below this certain value, or 95% of the data is below this value. So the percentile is something that ranges between 0 to 100 we can take. So like the 99th percentile means that most, like 99% of the data is below this certain value. Okay, so like 99th percentile means that 99% of the data falls below that value if we ordered it and kind of sorted it that way. So we can compute any percentile we want by just passing in the array and then giving it a number between 0 to 100. Okay, so and this should be a whole number, 0 to 100. So for instance, we can compute the 99 percentile. Oops, I have to actually run this. Let me run that. There we go. So 99% of the values are below 22.8, which kind of makes sense because most numbers are pretty low. So there's really only one number below that number, which is the 24. So if I did the 100th percentile, that would basically be the max, right? It'd basically be that 24. So only 100% of the numbers are below the max. So it kind of makes sense. And then if I did the 50th percentile, that would be the median. Half the values are below that, half are above. So that matches the median that we found here, which was 4. Okay, so we can do percentile. Any questions about percentile? Okay. All right. Finally, wanted to mention that NumPy, you can manipulate strings in NumPy. Now, this is less often used because typically when we're working with NumPy data, we typically don't have strings inside of there. We usually are dealing with numerical data, hence why it's called numerical Python NumPy. But it is possible to work with strings and do different string manipulations. So for instance, if we have a NumPy array that has 2 strings hello world, and then another array that has welcome learners, so these are 2 1D arrays, we can actually concatenate element-wise strings by using the np dot character module. And instead of doing the reason it's inside of the character module is instead of doing like a numerical addition, so typical arithmetic, it's doing a string addition, which is concatenation. So it's doing um, character addition here, which will concatenate these 2 strings, hello and welcome. So those end up merged together, concatenated together, and then world learners get concatenated together. So this is a string concatenation, element-wise string concatenation. So it's from the np.char or character module within NumPy. Okay. It's very rare we would have to do this, but I'm just pointing this out that it does exist. Okay, if for some reason we need to manipulate strings, we will have that ability too. Okay. All right, so then we can replace substrings with new strings. So if we have this original string called hello, how are you? We can print it out and we can use a character replacement to replace within this string, replace hello with hi. So once we do that, we can print out the new string. So then we get hi, how are you as the new string. So this does a string replacement if we can find the substring. So if hello exists, so we should test this out and see like, is there something, so we could just put in something that doesn't exist in there. It's not going to be replaced. So this is saying, okay, let's try to do a replacement of this string. Let's replace something with hi, but something doesn't exist. So it's just going to return to us. It's not going to replace anything. It's just going to return to us the original string. But this does exist. So that's going to be replaced with hi. I'm going to do a string replacement if we want to. We can also manipulate strings to do uppercase everything, lowercase everything. You can see how those, like this is all lowercase, but we do dot upper, pass in the string, it will uppercase everything. This is all uppercase. We can lowercase everything. You can see how that all works. Okay. Again, very rare we would ever need to manipulate strings, but if we did, there's this character module that can help us manipulate strings. Very rare that we would need to because most of our data is going to be numerical inside of an NumPy array. All right. Any questions there? All right. So just to recap, we have our arithmetic operations, basic arithmetic between NumPy arrays we can do, pretty straightforward. We can even use our standard, we can use NP add or we can use A plus B, NP subtract, A minus B, multiply, divide. We can all use those basic arithmetic operations. We also have a power function, which will raise things to exponents. These incredibly useful. We'll use these all the time going forward. Are the statistical functions like average, standard deviation, variance, median. We'll be able to compute really easily on an array. Okay. All right. So let's go to our next notebook and continue working with NumPy. So go to the 3.04 notebook. All right, now the whole point of this one is to practice accessing data within the notebook, or sorry, within the NumPy array. And truly, this is going to be great because it's going to work exactly the same as a list. We're going to be able to access elements by their position and also slice, just as we did with lists, right? So everything's going to work the same, which is going to be really nice. The one unique difference is that with NumPy arrays, we can have multiple dimensions. So that's where we need to actually be careful is that if we want to access elements that are in different shapes, like they're in a second row, third column position, how do we do that? And it's actually going to be really easy to do if we just think about it as kind of a coordinate of passing in like an index as if it was a coordinate of this is exactly what I want to access. Okay. All right. So if you take a look at this picture, this is a really great picture to break down a 2D NumPy array. So imagine we had a 2D NumPy array whose shape was 2 rows by 3 columns. So it's a 2 by 3 shape. All right. And we have elements 1, 2, 3, and 4, 5, 6 in our array. So we have 2 rows. Each row has 3 elements. Okay, so a 2 by 3 shape. Now, the element that is right here is at index 0 because it is at the first row. So it's at index 0 in terms of the row, right? So there's 2 rows. So it's either going to be index 0 or index 1 for the row coordinate. So it's at index 0 for the row. But which column is it in? It's in the first column. So it is at index 0 for the column. So this coordinate for this guy would be like if we passed in 0, 0 as the index, right? So if we passed in 0, 0 as our index, we could access that element right there because what this is signaling is we are at row 0 and we are at column 0. Column 0. Okay. So with multi-dimensional arrays, we have to be careful about that, is that things can be accessed by their coordinate now, their index coordinate, rather than just a single index like we saw with list, right? With a list, it was just, okay, we can grab something at index 0, index 1, index 2, maybe index -1. But with a 2D array, we're actually grabbing things at their coordinate, right? So row 0, column 0 is, this should give me the element 1, which is this guy, right? If I were to access that element. All right. So let's try accessing. So let's take a look at this guy. This guy is now going to be at same row. So this guy is still going to be at row 0, but it's going to now be at column 1, right? So it's now here, column 1. So we should be able to access that 2 sitting at row 0, column 1 index. So this should equal 2, right? This item should be that element 2. Okay. And then lastly, from the same example, we have this 3. This 3 we should be able to get from, we're still within row 0, but we're now at column index 2. And this should equal 3. Okay, so in a 2D array, this first entry is what row we want to go to. So imagine like scanning over this grid. What row do we want to go to? Okay, row 0, that's the first row. What column do we want to go to? Okay, column 2, that's the last column. That's the third column here. Let me ask you guys, does that make sense in terms of thinking about it like a grid and a coordinate of how we access elements? Any questions on that? Are the I and J just random? No. Like in this example, it's random. It's just a 2 by 3, but they represent how many rows and columns we have, right? So I represents how many rows we have. J represents how many columns we have. Oh, sure. Yeah, yeah. They could be any letters. Yeah. No, we're just using I and J because that's the traditional indices for row and column, I and J. That's just kind of like a tradition to do that. But yeah, they could be, you could use any letters there. Yeah. Yeah, no worries. Yeah, that's just the it's kind of the tradition there. Okay, so let's see how this works inside of code. So if we let's create some arrays. All right, so let's create some arrays to practice with. So we create a 1D array, we create a 2D array, and we're going to create a 3D array so we can practice accessing certain elements. So if we look at the 1D array, this behaves exactly like a list. In fact, I'm going to write that down. This behaves just like a list, the 1D array. We can access like the third element or the first element, or, in this case, we're accessing the fourth element, which is at index 3, and that returns to us the 4. So we're doing that just like a list. In fact, we can also do the very last element, which would be at the -1 index, and that is the 6. So it behaves, a 1D array behaves exactly like a list. Not much different in terms of accessing the elements there. We don't need to worry about coordinates because there's no rows and columns. It's just a single, it's basically like a list, right? Very easy to access things. Okay. So, and for instance, we can add two elements from these positions together. This adds the position 1 and position 0 elements together. And so that ends up being 3. And we can see that because that is 2 plus 1, which is 3. So pretty easy to do. All right. So here is that exact, here's another picture of everything we just drew earlier, where we're thinking of the elements at these positions as coordinates, right? So the element right here in the first row, first column is at coordinate 0, 0. And then the element right here is at coordinate 0, 1, 0, 2. And then if we go down to the next row, this element would be at row 1, column 0 index, row 1, column 1 index, row 1, column 2, on and on and on, however many rows and columns we have. So we think of accessing elements that way by their row and column index in a 2D array. All right. So for example, let's get the element that's in the first row. So this should be the first row because that is index 0. And this should be the third column. This should be the third column, right? Is the index 2. So if we go back to our 2D array, it should be the first row, which is this guy. And then the third column, it should be a 3. And it is, right? So if we print that out, we get a 3. How do we feel about that example? Do we see how we're accessing it from inside these brackets, just like we would a list, but now it's a coordinate? Do you see that one? Good? Okay. And we also have, now we can grab something from the second row and from the second row, and this, because this is now 1 and this is now the second column. So if we go back to our array, second row, second column should be this guy here, right? Second row is this guy, second column is this guy, so this should be the 5. Which it is. We print that out, we get the 5. Okay, that's what that coordinate represents. Second row, second column. All right. Very good. I want to take a look at a 3D array now, which is going to be a little interesting in that we're just going to add an extra coordinate to the mix. So with the 3D array, we basically need to know which matrix are we talking about. So remember, a 3D array is going to look like this. We basically have rows and columns, row, column, row, column, row, column. We basically have an array of matrices as our 3D array. So the first coordinate is going to say, which matrix are we at? Are we at this one? Are we at this one? Are we at this one? Roberto, I'm just having a little trouble with the comments. If we already know the value we're looking for, then why do we need to use the coordinates? Yeah, so it's because we need to get familiar with how to access different elements of our data. For instance, like maybe we need to access only that last row or maybe only that last column in a collection of data, which we're gonna see. We're gonna practice slicing coming up in a minute. So yeah, we're going to need to be able to access entire collections of data within within a matrix. So it's going to be important. It's going to be important to be able to grab that collection of data from a large data set. Yeah. So it seems I think I see what you're saying. It kind of seems like redundant to do that right now when we can clearly see exactly what value it is. But in a large data set, it wouldn't be that obvious, and we need a programmatic way to select those contents. Okay. All right, so in the 3D example, what I wanted us to see though is that notice that like the first coordinate is going to say, are we talking about this matrix or are we talking about this matrix? So we're actually going to have 3 coordinates. So this first coordinate is relating to which matrix are we talking about? And then once we know what this is, like this 0 would say, okay, we're talking about this first matrix. Then it's the same as usual with these 2 coordinates are, these 2 coordinates here are now what row and column within that matrix are we talking about? Okay, so with 3D, that first coordinate is which matrix is it? Is it the first, the second, the third, the fourth? Because remember, in a 3D array, every element is a matrix. Every element is a 2D array. So the first coordinate is saying, which matrix are we talking about? All right. And then once we know which matrix it is, we can use the next 2 coordinates to figure out what row and column of that matrix are we talking about. So let's see an example. So look at how this 3D has 3 elements. So if we break this down, this is saying that we want to access within the second matrix. That's what this first coordinate is saying. Within the second matrix, I want to access the element that's at row 0, column 0. Right? This is the second matrix. Second matrix. So in the setup, it's like we have a matrix here, we have a matrix here, we have a matrix. Actually, we only have 2 in our example. So this element means we want to look at that second matrix. And we want to grab the element that's at coordinate 0, comma 0. So let's go back to our matrix and see what that should be. So what is the second matrix? It's this guy. This is the second matrix that is within our array. And then we want to access row 0, column 0. That should be this. It should be this 7, right? So row 0, column 0 of that second matrix should be that 7. And that's exactly what we get if we print out this this coordinate. We get 7. Matrix refers to row? Kind of, yeah. It's because in a 3D array, every element is a matrix. Is a 2D matrix, right? Okay. All right. How do we feel about this three-dimensional indexing? Does that make sense? This is matrix. This is the second matrix, and then this is row 0, column 0 of that second matrix. Good? Okay. All right. Finally, I want to mention that we could do negative indexing for all of this, right? So that still applies. Like if we did -3, that would be, third from the last. So if we go back to our 1D array, we could do -1, we could do -3. So -1, -2, -3 should be the 4 here. So we can still use our negative indexing as we would with any list. So that does not change. We can still use minus indexing. We can even use it in the 2D array. So if you imagine there, this is now in terms of the column, because now this is saying in a 2D array, we want to grab the element that's in the second row, but in the last column. That's what the -1 would mean in this case. Second row, but the last column, because we have a -1 index there. So second row, last column, let's go verify that's a 6. So second row, last column would be this guy. Yep, that would be a 6, right? Because this is our second row, and this is our last column is a 6. So that's a nice thing. That's a convenient thing. We don't need to know exactly how many rows there are. If we just want to grab the last one, it's just a -1. So this is second row, last column. And then if you look at the 3D example, we have in our second matrix, the second row, last column again. So we can grab that. So that should be second matrix, but then the second row and last column. So second matrix would be this guy. Second row is here, and then last column would be the 12. Right, so there it is. There's that coordinate. Gets us to the 12. All right. Okay. Any questions on accessing elements? Any other questions about this stuff? By the way, there's some extra practice for you guys, so give this a chance. I encourage you guys as kind of homework for next time to try out this practice, extra practice here that's at the end of this notebook. So it just has you go and create some arrays and do some indexing. So go ahead and try that out on your own. Let me know what you think. Can everyone see this? Okay. Should be at the 4.01 notebook. Thank you guys. Thank you. All right. And then hopefully you guys have this notebook too, and are able to follow along. So as I said, we're getting into our fundamental data structures here for working with data science and eventually machine learning. And Pandas is going to be really crucial for us because it contains two really critical structures, the series and the data frame. So I wanted to take time at the beginning to review what those two data structures are, and their use cases. And then we'll spend the rest of today going through a bunch of notebooks to get some familiarity with those things like series and data frame. So we'll be doing a bunch of examples of different manipulations and different ways to work with data inside of series, inside of data frame. So we'll be covering the ins and outs of that, as well as some other features of Pandas that we'll use along the way from every now and again. So that'll be all of the beginning of today will be Pandas. If we have enough time, we'll get into lesson 5, which will be around visualization. So we'll start going into, doing things like plotting and using libraries like Matplotlib and Seaborn and those. But mainly want to focus today around Pandas as a really fundamental Python library for us doing anything with data. All right. So where we had left off last week was that I told you guys Pandas was going to be really important for us and had mentioned that it had these two primary data structures that we will use all the time, which are the series and the data frame. So just to review that, the series is essentially a fancy NumPy array. It has a NumPy array that underlies the series that contains the actual data. So you think of it as kind of a one-dimensional array. What's special about a series, though, is that it also has an index to it that can be customized. So it doesn't have to be just a standard like positional index, like what we've seen with arrays, they have natural order to them. They have a 0, 1, 2, 3, 4th, 5th element. We can actually have a custom index that could be a string, it could be a date, could be really any object we want it to be. So that's what makes a series kind of special, is it has the array of data, but with a custom index, which is useful in different situations to customize that, as we'll see. Now, a data frame just takes that into a second dimension. So if you think about a series as being kind of I would think the best example of a series is kind of like a column in a table or a column in like an Excel spreadsheet. Okay, that's probably the best example of a series. It's got a single column has just a bunch of data. It has a bunch of data, and it can have like a row label like you see in Excel, right? So every entry can be labeled coming from row A, row B, row C, row D, etc. That's a series, but a data frame is really the whole table. So a data frame is basically a collection of series, that a data frame has rows and columns to it. So it's got a bunch of different series. We think of it as kind of a two-dimensional array. Data frame is going to be incredibly useful for us because nearly all the data we work with that has structure to it, especially in machine learning, will be in the form of a data frame. We'll put it into a data frame, we'll manipulate it as a data frame because it will have rows and columns to it. Those columns will represent different attributes of the data. So think of an Excel spreadsheet as that example, right? You have different columns that represent different things. Maybe if you're thinking about a bunch of data that represents different houses, every row is an example of a house, and every column is a different feature of that house, like the number of bedrooms, number of bathrooms, the price, those kind of things. So if I had to draw a picture of these two guys, again, the series is kind of a single array. I think of it like a column, and those entries are inside of the series, and it does support different data types, including different objects. So I see your question, Tim. Yeah, a series can hold different objects. Can it hold a function? In theory, it could. I haven't really seen that, but I don't see why it couldn't use a function inside of there. Um, but yeah, like generally it can hold objects, like any object, which everything in Python is an object. So yeah, haven't really seen a use case for it, but I'm sure that it could. But anyways, the series is going to be this one-dimensional array, and then it's going to have an index like A, B, C, D, etc. That's fully customizable. So it doesn't have to be the standard kind of positional index. Could be fully customizable. Now, that's the one dimensional, that's the series. And then if you extend that into 2 dimensions, you have a data frame, which is going to be kind of an entire table. So it's going to be many series kind of stacked like this, and you have rows and columns. So and then you may have, just like in Excel, you can have an index here like A, B, C, D, etc. as the index. Okay, so series is one-dimensional, data frame, two-dimensional rows and columns. Okay. All right. So that being said, let's start with the series, and then we'll work our way up to extending that into 2 dimensions. So we're going to start by looking at the series. So in general, as I said, a series is going to have data, which is going to be that one-dimensional array of data, and it's going to have an index. So, and again, that index can be fully customizable. It can be by default, just the standard positional index. So just like we would see in a list or in a NumPy array, it would be 0, 1, 2, 3, just like you see in this little picture right here. This would be kind of the standard like positional index of the series. And then this is your data here. That is the underlying data of the series. What's really nice about Pandas is it actually builds on top of NumPy. So this underlying data is actually stored by Pandas as a NumPy array. And so because of that, series kind of inherit all the nice properties of NumPy arrays in the sense that they can do all the same arithmetic. They can be manipulated in a lot of the same ways. They have a lot of the same attributes, like a shape, and a reshape function, and a transpose, and all these things. So that's really nice about really series and data frames. The underlying data is all built on top of NumPy, which is nice. So you can create a series out of a list. You can create it out of a NumPy array. You can make a series out of a tuple. You can make a series out of a lot of different data. It's just that one-dimensional array that has that special kind of index to it that we could customize. So we're going to see different examples of building a series and manipulating a series. The other thing I should mention is that there's no restriction to the kind of data that the series can hold. So it can hold objects, it can hold strings, it can hold integers, floats, really all of those. And it can even be mixed. So just like in a list, we would see, we can have strings, we can have floats, we can have those kind of things. All right. So let me show you an example. And the first place we'll start is by importing Pandas. And this is just like we did with NumPy. Remember, all of our NumPy examples had import NumPy as MP. All of our examples here with Pandas are going to be import Pandas as PD. This is something we're going to get super used to as we go along, is the fact that we see PD, that instantly should tell us we're using Pandas. That's the industry standard. So industry standard alias for Pandas is PD. So if you're reading some code and you come across a PD, that is just short for Pandas, and that's the standard in the industry. So everyone would understand you if you were using PD there. So we import Pandas as PD. Look how easy it is to make a series. We just start with a list. So we just have a regular list of 1, 2, 3, 4, 5, just those 5 numbers. And we create a series by doing pd.series, and we pass in that data as an argument to the pd.series function. This constructs a series, and we store this as a series object. So what's interesting about this is when you first create the series, if you don't specify an index, so if you don't specify the index, Pandas uses the default positional index. So it just assumes that the data is going to be indexed by position. So that's just, this 1 would be at the 0 index, this 2 would be at the 1 index, this 3 would be at the 2 index, and on and on. So it's just the standard, just like we learned how to slice, so we learn how to access elements by their index. That's all we would need to do to access these items of the series. So that's if you don't specify an index. But I want you to see this example here where we use the same data, but now we actually customize the index to be, special labels for every item. So for instance, 1 would be indexed with A, 2 would be indexed with B, 3 would be indexed with C, and so on. So the way we do that is when we create the series, we actually explicitly pass in an index array, which signals that these elements are going to, all this data is going to be indexed by this specific index. And then why that's relevant is because when you print out this series, you can access things. Look at how down here we actually access things according to this B index. Or obviously we could pass in a C. Okay. But in the series that does not have that just has the default index, notice that we can access things by this numerical just positional index. So we could access the first thing, It would access the second thing, and then this would access the third thing, which is at index 2. Okay. So, and by the way, you can combine these. So you might be wondering, well, we have some data and we have an index. Why don't we just map those two together? And we can. So if we use a dictionary, we can actually combine those two together and say, okay, A should map to 1, B should map to 2, C should map to 3, D should map to 4, and E should map to 5. And we can create a series from this dictionary. So you can actually build a series from a dictionary. And what this will do is it will treat all the keys as the index values, and it will treat all the things that they map to, the values, right, will be the data. That'll just be the data, right? All of these 1, 2, 3, 4, 5 will be the data, and this E, D, C, B, A will be the index. Okay. So when you do this, when you use a dictionary, keys become the index and values become the data. Does that make sense when we're creating a series? Any questions on that? We can use a dictionary. We can just use a regular list. You can also use a NumPy array. It doesn't have to be a list. You can use a regular NumPy array to create a series. So all the code here is just creating a series. Nothing that interesting going on so far. Just creating a series. And I want you to see if we were to print out, I'm going to add this in here, just one little cell below this. I'm going to print out the series so you can see it. Let's print the series. You can see that it's going to have, notice how the series prints out with kind of two columns. This is indicating that this is the index 0, 1, 2, 3, 4, right? It's the positional index of this regular series. And then here's the data, the 1, 2, 3, 4, 5. Okay. So you see both of those. Let's print out this series with index. And let's print that guy out. And you can see now that the index is A, B, C, D, E. That should make sense. This is kind of like an Excel column, isn't it? Because Excel, if you're familiar with those spreadsheets or even in Google Sheets, right? Every row has this index A, B, C. Like you're dealing with cells that are in row A, B, C, D, and on, right? Let's take a look at a series with dictionary. This should be a series from dictionary. And we get the same thing, the A, B, C, D, E, 1, 2, 3, 4, 5. What is the difference between dictionary and series? Well, a series is a different object. A series is a pandas object, and therefore it has certain functions available to it, like finding an average, plotting, finding a mean, or sorry, finding a median. Like it has a lot of built-in functionality as a series that you don't get as a plain dictionary. Does that make sense? Like you get a lot of, we're going to see this in pandas, you get a lot of functionality if you're a series. You get a bunch of statistical functions that can be easily ran. You get, um, uh, you can do a bunch of summarization on that data. You can do plotting against that data relatively quickly as a series versus as a plain dictionary. Tim, it would be object. Try it out. So try it out. If we did, so let's say we did a string inside of here. So let's make that 3 a string. So we have integers and strings. Let's now print this out. They basically, do you see how they're all objects, which means that Pandas would actually convert everything to a string. Once it sees one string, it's going to treat all of these as a string. So if you see a data type as object, that likely means everything is a string, because string is technically an object. So we can convert that back to an integer, rerun that, it goes back to an integer. Okay. Okay. All right, let's see what we get. So I think it's a valid question. What's the difference between a dictionary and a series? Because it's getting at like what do we get by having a series that we wouldn't have if we just had the dictionary? And it turns out that we get a lot of different functionality out of the series that we wouldn't otherwise have. So we're going to see some of those functions. The first couple of functions I want you to take a look at are right here, which are the head and tail functions. So what these do is they give you a view or essentially a copy of the first n rows. So whatever value you put in here, you'll get those first few entries. Head goes from the top, so it goes from the beginning of the series and does the first however many rows. So if you don't put a value in there and you just have this, the default is 5. The default is the first 5 entries. Okay, if you don't put anything in there, you could put a value in there like 10 and you'll see the first 10, right? Or you want to see the first 3, you put in a 3. So head gives you that copy of the first 3 elements, and tail gives you, on the reverse end, it gives you kind of that slice. Think of it as like a shorthand for a slice. It gives you a slice of those last 5 guys. So this is almost like this is similar to doing series, and then we were to slice out the like last 5 entries. Think of it like doing something like that. And then this is similar to series, and then we do the first 5 like that. Okay, so head and tail, very interesting functions that actually we will use quite a bit with DataFrames, particularly to just get a quick view of the first 5 rows and last 5 rows with the tail. So if we were to run this, we could print out that. So we could print out the first n rows, and we get the first 5 entries, right? We could actually do the first 2, and that would just give us the top 2, right? From the top. Now we could print out the last 2, let's say. So print last n rows, and this does the last 2, right? All right, so head and tail, pretty straightforward. They give you the first, either from the beginning, first 2, or from the end, the last 2. Series have a shape to them, which makes sense because the underlying data is a NumPy array, which also has a shape. Now let me show you what the shape is. Let's print the dimensions. Print that, and let me comment that out. So as you can see, this series only has 5 elements, and it's basically one-dimensional. So even though it has an index, it is one-dimensional. It doesn't have rows and columns. It basically only has rows, as 5 rows of data. It's just a single column, essentially, right? It doesn't have multiple columns, so we just say it has a shape of 5. It's just one-dimensional data, right? So a series is always 1D, one-dimensional. Okay, it's always one-dimensional. All right. Now let me show you a really awesome function called describe. Now this is a cool function to give you a bunch of the statistics, basically give you a summary a descriptive summary of your data. So when you have, this is the advantage to having your data in a series, is you can easily run a describe function and see how it's series.describe. What this is going to do is give us a quick descriptive statistical summary of our data. So it's going to print out the mean, max, min, median, and then like various percentiles of the data. So it's going to give us that quick view of all those statistics, which is really nice. So let's see that. So if we print out the stats, we can see what everything that gets produced. So you can see here we get this summary. This is our descriptive summary. We get a count of how many values are in the series. We know that there's only 5 because we created it with only 5. That makes sense. The average is 3. That also makes sense. Just the numbers 1 through 5. So the average is 3. The standard deviation is 1.58. The minimum is 1. 25th percentile is a 2. The median, which is the 50th percentile, is 3. That makes sense. The 75th percentile is 4. Also makes sense. And the maximum is 5. That makes sense, right? It's just 1, 2, 3, 4, 5 is our data. But that's extremely useful, right? To get that quick, you just run one function, you get all this summary of the various stats of that data is pretty useful. And it's actually going to be incredibly useful to do when we have data frames. The describe is going to be something we'll use quite a bit on an entire collection of series in the data frame. Any questions on the describe? Does that make sense what it's doing? It's taking our series data and just doing a bunch of statistics on it. So we get things like the max, the min, the average, the median, all of those get produced on that series of data. Pretty convenient. Can we get the median alone? Yeah, we can do, remember how we had the np.median function? We can do that. So if you just wanted the median, you could do, there's 2 ways to do it. You could do series.median like that, or you can do np.median and pass in the series. You could do it either way. If you just want the median, you want to compute the median. Right? So we can't forget that. The underlying data is a NumPy array, so this function is compatible with the series. All right. Okay. So if we want to get all of the unique values of the series, we can run this unique function, which will give us all the unique values that exist within the series. So if we print this out, this should be the values 1 through 5 because we don't have any duplicates. They're all unique, right? So this should just give us all of those values. Clear that out. And it does, right? So 1, 2, 3, 4, 5. This basically gives us a list or an array essentially of all of the unique values if we run the unique function on the series. That's another advantage, right? If your data is in a series, you can quickly get all the unique values. If it's in a dictionary, that might be harder to do. Might be harder to kind of sort through it and try to deduplicate it. So unique. We can also get the number of unique. So if we just stick an N right in front of that unique, N unique gives us a count. So this should be 5. This should tell us how many unique values there are. We should be able to print this out and see that there are 5 total unique values, right? Just the numbers 1, 2, 3, 4, 5. Pretty straightforward. Any questions on those functions? We're going to use these more and more. I would say head and tail we're going to use quite a bit, especially with data frames. And what's nice is these functions on a series actually carry over to data frames one-to-one. So the head function, the tail function, the shape, describe, unique, and unique, these will all carry over to DataFrames pretty easily. So DataFrames are going to be those multi-dimensional, two-dimensional data structure that we will extend our knowledge into after we cover series. Any questions on these functions? Good. Okay. Fantastic. So we can keep going then. So just like with NumPy arrays, we can do arithmetic with series. So we can add series, we can subtract series. The catch being that it can be tricky to do arithmetic with series when they do not have the same index. Let's see how that plays out. So these series have different indices. Remember, this series was built with the default index with 0, 1, 2, 3, 4, 5. Sorry, 0, 1, 2, 3, 4 as the indices. And this one was built with the indices that have the character indices, right? A, B, C, D, E. So it might be a question of like, what actually happens if we add those series together? Like the data, if we were just looking at the data arrays, those make sense to add together because they're just arrays that are the same shape. So it makes sense to add their elements together, and that should be a very natural thing. The question is, what happens with their indices? So let's see what we get. Let's print that out. So it turns out that Pandas doesn't know what to do with that because they don't have the same indices. So this is just a warning that you can add together series that have the same indices, no problem, and the resulting data is just going to have that same index as the first two. But when you add together, these have different indices. So just to give a warning here, we have a warning. These series have different indices. We can't add them together. Okay, we can't really add them. Now we don't get an error, but we basically get an undefined result, right? We don't know how to add things together because, and look at what the new index is. It thinks it's adding them two together. We get 0, 1, 2, 3, 4, and then A, B, C, D, E. It's just a mess. Right, it's just a mess. It doesn't really make sense to do. So if you're adding series together or doing arithmetic in general, multiplying, subtracting, all those NumPy arithmetic operations we learned last week, you can do them as long as they share the same index. Yes, the order matters. Yeah, for sure. The index order matters because that dictates the position of elements, right? The relative position of elements is determined by the index. Okay. Now I want to show you something really cool as well, which is the ability to basically apply a function to every element of the series. So if we have a series, we can manipulate every element of it at once by using a special function called apply. So apply does exactly what it sounds like. It applies a function to every single element. So the input to apply is going to be a function. So this is where the input, or I should say the argument to the apply function is a function. And we have a special function here that we have not seen before called a lambda function. So we haven't seen this before. What this is, this notation here actually is declaring a function. Lambda declares a function without having to use def. So it's a shorthand in Python to define a function on one line of code. And what it means is this is defining a function very similar to def, and it's saying we have a function that has one argument, and we take that argument and square it. So that's a function. It's saying take whatever argument is input to this function and square it. So what that means is on this series, we're going to take every element, because those are the arguments to this apply, and we're going to square them. So that's what this means. So this has the effect of squaring each element, because it's star star 2, remember, is the second power. So this will square each element. That's what apply means, is apply some function to every single element. And this is we're defining a function here to say, take every argument and square it. That's what that function is. Now, do we have to do it that way? No. The alternative to doing this is if we quickly came up here and said, let's define a function called square, where we take any x and we return x star star 2. That's a function really easily, right? That's a function that squares the arguments. And so instead of doing this, we could alternatively do the same exact thing, but instead of passing in this lambda, we could pass in our square function there. Okay, which says we should be taking the elements of x and the elements of the array, sorry, the series, and we should be squaring them. This is the same thing. This is the same as above. It's the same thing as doing this. Lambda is just a shorthand for just doing def and returning this argument. This is your argument to the def, and this is what you're doing to that argument. You're squaring it. Does that make sense on the lambda? That this is equivalent to, this is exactly equivalent to this lambda. Exactly equivalent to that lambda is just a shorthand for this function. Yes, Roberto. Yeah, it's shorthand. So lambda notation is you declare lambda as a keyword, and then you write down your argument. And you can actually have more than one argument. So you could do x comma y comma z if you have 3 arguments, let's say. In the series, we only have one argument, which is every element. That's the intention, is to apply this function to every element. So there's only ever going to be one argument. So we have one argument, and then we have a colon and then we have our math to say what are we going to do with the argument to return. So the colon is like shorthand for returned. Lambda is like shorthand for def. So yeah, it's always def returned. Okay. And we always, so the other thing I don't want to the other thing I don't want to get away from either is this notion of apply. This is a really powerful idea. This is a nice shorthand to say, I want to take every single element of this series, and there could be millions of them. There could be millions of these elements. I want to take every single element and apply some function to every single element. And this is the way to do it. So apply is really powerful. We're actually going to use apply quite a bit as we move along and work with DataFrames. Apply will be really useful to apply a function to every column or specific columns that we want to transform. We will use apply. Any questions about apply? or the input to apply. And remember, the input to apply is a function. Whether you define the function like this, traditionally like a function, or you use a shorthand lambda, either way, those are functions. Okay, let's make sure this works. Let's print out the squared series. Let's do both. Let's do the lambda version first. Let's uncomment that. Do
I don't
the
see the version in your contacts. Who do you want?
let's do this. Oh, I forgot to put this. Okay. So see how this, let me comment this out so we don't try to print that out again. Rerun that. Okay, so see how it ended up squaring everything? So there we took the apply and gave it the lambda function and ended up squaring every element all at once. So everything gets squared. And again, like we could do it this way. Alternatively, we could run it this way and it should work the same. There it goes. So the same result, whether we use the traditional def function definition or we use a lambda, either way, get the same thing. Okay, cool. So no questions on apply. We will use apply quite a bit whenever we want to make sure to transform all elements of a series. Remember, in the apply, every element of the series is going to be applied to this function. Or I should say this function is going to be applied to every element of the series. So apply will transform everything in that series according to this function. Now, the kind of the more targeted way to replace values is the series dot map. So this is a little less, this is basically more targeted than apply. More targeted than apply. It's a replacement of values within the series. So essentially what we're doing here is we're going to take our series and replace this data with this data here. Replace this 2 that's in our series with this data here, and replace this with this data here. And so you can choose which data values you're replacing in the map. You don't get to choose that with apply. Apply is going to apply that transformation to everything in the series. All of it's going to be mapped with this function. Whereas map is going to do a specific replacement. So map can be useful like if you only want to transform certain data values. So if you want to find out where there's a 0 or a 1 or a 2 and replace those with certain values, you can do this. This kind of does like a find and replace. You think about it like that, find and replace. So let's see what the result of this is if we print the mapped series. So you can see that 1, 2, and 3 get replaced, but we actually don't have any replacement for 3 and 4. So those get mapped to NaN because we don't have a specific replacement for them, and their original data was integers. So we now have strings, and we had those integers. We don't know how to replace those, so those get overwritten with NaN. So the thing you have to be careful with a map is you want to make sure you basically cover all the cases that you have within your series. So if you have, 1, 2, 3, we know that the other data members are 4 and a 5. We should probably pick some candidates to replace those with. So if we have 4, we want to map that to 4 probably, and we had a 5, we want to map that to 5. So again, this is a more specific find and replace. So now all of that data has been replaced, and we actually have those replacements that we can now make. Okay, so map will map these data members to this value, and that will happen for every copy of this. So if we had a bunch of 1s, they all would be replaced with 1. Every instance of 1 would be replaced with 1, not just like the first one, but every instance. All right, questions about map? Do we see how it's different than apply? Apply is going to take a function and apply it to everything all at once. We're not picking and choosing what to replace something by, which is what we're doing with map. All right, very good. A couple more examples. So beyond applying transformations or replacing certain values with something, we can also do things like sorting. So this should make sense to us that we can sort. So by the way, the default sorting is least to greatest. So it's an ascending sort. If we want to turn that off and do a greatest to least, we have to go into here and turn that, we have to do ascending to false. Okay, so if we do ascending to false, let me jot that down. Ascending equals false, we'll do greatest to least. So this will sort our data. So we have 1, 2, 3, 4, 5 currently from the beginning to the end of our series. If we do this sort, it's already sorted, but if we do a greatest to least, it should put it now as 5, 4, 3, 2, 1, right? It should now be sorted like that. So let's go ahead and print that out to be sure that it got sorted properly. So print sorted series. And you can see now we have 5, 4, 3, 2, 1. And you can also see the indices now change to where this is now 4, 3, 2, 1, 0 because the data retains its index. So we're sorting the whole series. The index also gets sorted along the way. So that's something to be aware of is when you're sorting the series, you're sorting both the data and the label. That label comes along with it. Or I should say the index, not the label, the index. So if we were to keep this as true, which is the default behavior, it would just be how we had it. It was already sorted, right? 1, 2, 3, 4, 5. So in order to do a greatest to least, we have to put this to false, ascending as false, and that will be the greatest to least sort. Does that make sense? Any questions on the sorting? That's valuable, right? That should be a natural thing we can do is we can sort the series. You can do that in any spreadsheet, right? You can sort a column. So we better be able to do that, right? That should make sense as a basic operation we should have is the ability to sort a series. Okay. Very good. Let me move on to a couple of really important things that deal with missing data. So we have a simple function here to check and see if there's any missing values, which is series.isNull. So this will check and see if there's anything missing, meaning that we have a blank value or an NaN value in our data. So we're missing something for that index. for some reason. Maybe we loaded in this data from a spreadsheet and we're missing a value. We want to be able to see if we actually are missing anything. Let's see what this returns. So you can see what this does. This goes through and checks every entry and sees if any of them are true or false. If it's true, so this will return true for missing entries. So if there was a true here, that means that slot in the series has a missing value. It has an NaN. It was blank, essentially. It has an NaN. It doesn't have a valid value there. So it's null. This will give us a check for every entry. And more importantly than that is maybe we want to know the total of them. So let me show you an additional example is we can see the number of missing values, which is if we just tack on a sum. If we just tack on a sum there at the end. So if we take this and total that up as an aggregation, we can get how many missing values there are. So this should be 0. There is no missing data in our sample series, right? It's just 1, 2, 3, 4, 5. There's no missing numbers here. So, but we could confirm that this should be 0. So you see here we get 0 as the number of missing values. There is no, so both of these are valuable. This is valuable to see which slots are missing. And we could have a place to see how many are missing. Can you insert a null? Yeah, you can overwrite. So we could overwrite a value to be null by doing something like series 0 equals none. That would overwrite the first entry to be a null value, none. Does that make sense? This would overwrite the first entry to be null. Yeah, none. The Python equivalent is none. Yeah. By the way, if we do that, look how many are missing now. After we do that, look how many we get missing now. We get 1, right? So we overwrote that first item. Now when we do this, we actually get 1. That should make some sense to us, right? Yeah, it's because count is usually counting the number of a specific data value. Like count how many zeros there are, count how many ones there are, count how many twos there are. In this case, we're getting a total. That's what sum really represents, is how many total nulls do we have? So we're thinking of count a little differently in this context. Like it's the count of how many of a certain data type we have. In this case, we're checking is null, which gives us like a Boolean 0 or a 1, and we're totaling that up. So if we have all zeros, the total, if we add a bunch of zeros, we get 0. All those falses are like zeros. So we total all those zeros, we get 0. In this case, when we fill in a null value here, we get 1 missing value as the total, because now there's a true. There's actually a true sitting here, which we could see if we printed that out again. If we printed series.isNull, there's now a true sitting here, which is a 1, basically. Python tree says 1. So we total that up, we get 1. All right. So you may be asking, well, what do we do if we have a null value? Well, luckily there is a nice function to replace null values with a default value, and that is the function fill NA. So if we're missing something, we can go ahead and just fill it with a specified value. So in this situation, we have a null here. Let's fill it with a 1. Let's go ahead and fill it back in with a 1, because that's what it used to be before I took it out and said it was none. Let's go ahead and fill that NA with a 1, and then let's print the filled series. So now this should have that null value filled in with the 1. And there we go. So we have 1 there, and all the values we have no more null values. So fill NA will fill back in, it will fill in any missing values with a default. Okay, so pretty convenient. If we identify anything missing, we can fill it in, right? We can fill it in with a default, with this fill NA. Any questions on this? All right. So what I wanted to show you next is the ability to essentially filter a series. So we can put in conditions to basically filter out different rows or different entries in the series. And I want to show you how to do that very easily, which are just going to use our comparison operators to basically generate some filters for us. So I want you to see the syntax of that. So we have this sample series that we built from this fake data. We have index A, B, C, D, E, and we have that data mapped. We have those values mapped to this data 10, 20, 30, 40, 50. Okay, so some fake data there, and we build our series. So we have a new series sitting here. I want you to see the syntax of how we can generate a filter. So generally, we can build filters by using the comparison operators and the brackets for value selection. So remember, we typically will use brackets to put an index in there. That's typically what we're used to doing, right? We put in a 0, or we put in an A, or we do a slice. We can grab elements that way. So think of doing that, but with a comparison filter now. So this would, like, for instance, this says we want to pick only elements of the series that are going to be bigger than 30. Excuse me. So we have we pretend like we were going to pass in an index here. So we have series bracket, because what would typically go here would be something like this, right? That would typically select something from the series. It would select the first item, or we could slice it to be something like that, right? We could slice. So that's how we select things. But in this case, we're actually going to do a filter, which is a condition to say, I only want to keep items that meet this criteria. That's the filter. Okay. So inside the brackets is our filter condition. So it's basically we only keep elements that meet the filter. So let me show you what this should be. If we're filtering out to say, only give me items from the series that are bigger than 30, we should only get this part of the series remaining, right? Everything else should be filtered out because 10, 20, and 30 are not bigger than 30. They're all less than or equal to. So these guys should be left out, and we should only be seeing this as the result of that filter, right? We should only see those guys as the result of the filter. So let's make sure we do. Let's print out this selected greater than 30. So here it is, right? We only, oh, it already did it for us. So it already showed us this. The selected greater than 30 results in only those two parts of the series remaining. So that was an effective filter, right? To only give us the items that are bigger than 30. So that's how we filter. And so all we have to do is, if we want to do other kinds of filters, we just have to do other kinds of comparison operators. So for instance, let's pick all the items of our series that are exactly equal to 20. How many of those do we have? We really only have one. Only this guy exactly equals 20. Right? So when we do this filter, this should ignore everything else and only give us this item out of the series. So our series is going to be filtered down quite a bit to only this element. And we can see that. So when we come down here, the part that gets printed out there is going to be only that part of the series, the index B and the 20, the data 20. Right, so that is that filter. Not equal to 40. Which items of our series are not equal to 40? That's what this filter really is asking. So we go to our data and look at it. We have a 40 here. Which parts of the series are not equal to 40? Well, it's basically everything else, right? This is not equal to 40. This certainly is, this is, and this is as well. It should be everything but that 40 should be filtered out and returned back to us. So if we take a look at that, what is not equal to 40, we get everything else in the series, 10, 20, 30, 50. So that was an effective filter, exactly what we were hoping for. Okay, so greater than 30, equal to 20, not equal to 40, those are all valid filters. And I want you to see that syntax where this is inside of the bracket. It's basically replacing an index. They say, I want to pick something based on a condition, not based on an index, okay? Based on a condition. Any questions on that? Okay. So I'm going to show you some other examples of conditions. For instance, we can actually combine conditions using logical shorthands. So this is multiple conditions we're combining. It is greater than 20, but less than 50. So this is greater than 20, and this symbol here we haven't seen yet is the shorthand for and. It's the Boolean and symbol. So this ampersand symbol is shorthand for and. So this means that we're looking to filter out data that is bigger than 20 and less than 50. So multiple conditions combined. Now we could do or. There's a shorthand for or that we could use in here. And that is the pipe. Basically the pipe symbol is shorthand for the logical or. So we could have a pipe symbol here. Oops, I don't know what happened. Yeah, we could have a pipe symbol here, which would signal that we would be looking at this condition or this condition. So things that are less than 50 or bigger than 20, which would really be everything. So it's kind of a useless condition, but we can have that one. So does that make sense? Those are just shorthands for and or. And so because we can filter on conditions, there's nothing stopping us from filtering on multiple conditions that are logically combined. So greater than 20 and less than 50, well, what should that be? Should really just be these guys here. Those are the only things that are greater than 20 and less than 50. We should just get those two out of it. So if we went down and looked at it, we would get these two guys as the filter, which makes sense. So we can do that. That's a valid way of filtering. You can also, what's really cool is you can also filter based on a specific list. So you could say, I only want to keep values that are inside of a specific list. So this is where we use the is_in function. So this is a function that gives a Boolean true or false if the members of this data are inside of this exact list. So what this means is we should really only be keeping values that are going to be 20, 40, or 60. Only those three numbers should be kept. So if we go back to our data, we only are going to keep only these two. There's no 60. So 60 wouldn't match to anything. So we're really only going to keep the 20 and the 40. Okay. So is_in is a special kind of filter that only retains values that are actually in this collection. So if we did this by list, we only get those two, only the 20 and the 40 remain. You can do string filters. So for instance, if we had our data was all strings, we could filter based on the string starting with a B. So that's actually a very specific condition, right? So we want to filter all strings that only begin with B. So in this case, that would just be the banana, should be the only one that is returned, the only entry that's returned. Everything else starts with A, C, D, or E. So that's possible. Okay. Let me pause there. Any questions about these guys? On this one, this starts with? Yeah, so what this means is we have a series that has strings. If we were to filter it, what we're doing is saying, okay, here's our overall bracket. So that does not change, right? We have our string series and we have our bracket to say we want to select something. The bracket's always meaning let's select something. So first of all, that's why we have a bracket. Then this accesses the strings. So whenever you want to access string functions, you do your series.str, which is the string module of the series. So that gives us access to string functions, and one of those functions is finding out if a string starts with a certain character. So that's what the syntax means is give me only the things that start with a B as a character. Which strings start with a B? In this case, this is the only one that starts with a B, and you can see that based on the starts with, the only thing that gets returned is the banana. Right, it's the only thing that gets returned. Yes, it is case sensitive. It is. So if we did capital B, this would be different. This would be nothing. Nothing starts with a capital. So yeah, lowercase b is not the same as uppercase B. So we'll continue. We were practicing, selecting items from the series. And one of the crucial ways of doing that, that's also going to be very crucial for DataFrames as well, is the loc and iloc, which operate on different indices. So what's really important to know is that loc allows us to pass in the basically the labeled index. So our index that we have, which is either the default one or the one we provided when we created it. In this case, we created a series that had a index with A, B, C, D, and E. So loc will allow us to select multiple of those indices, almost like a slice. So loc allows us to use our index. So we use our series index to select data. So we're selecting A, we're selecting C, and we're selecting E. So we pass those into a list inside of the loc function. And we can pass in as many as we want. We can pass in just a single value. It doesn't need to be inside of a list. But loc is pretty typical for selecting multiple elements using the index. So that's the key thing to remember about loc. It uses the index of the series to select items, and you pass in typically a list of those indices that you want to pick. So we're picking the elements at A, element at C, and the element at E. Let's go back to our data. That should be 10, 30, and 50. So if we go back and look, that should be at those three guys, right? A, C, and E, 10, 30, and 50. Okay, so loc uses our indices. And now, how is that different than iloc? So iloc always uses position. So this always uses position regardless of index. So even if you have a really nice index that you've provided, like a date, or in this case, A, B, C, D, E, we can ignore those and just use their position within the series, which is what iloc does. It just uses the numerical position of the elements. So for instance, if we want to pick the very first item, we know is at index A, but in terms of its position is really just position 0 within the series, right? Position 0 is the very first item, even though it has index A. In this case, we're picking the positions 1 all the way up to 4. We're doing a slice. We can do that. We can slice based on position. So that's okay with iloc. So remember, iloc is different than loc. Loc uses the index, whatever index we have defined, which is, it can be special, right? It can be dates, it can be strings, it can be objects. That index can be whatever we define it to be. iloc will always use numerical positions, always. So you would never put in, like, this would be invalid to do this. This would give us an error. We can only use this with loc because that is the index of the series. But the positions are just the data positions within the series array. So we have just a natural ordering that always exists of our data within the series, and we can use that with iloc. Okay, so they're very similar. They're both used for selecting data, but they use different indices. Loc uses the defined index of the series, and iloc uses the numerical position of the elements. Okay. Any questions on those? So we see, by the way, this is 1 all the way up to 4. So what is at position 1 would be this guy, even though it's at index B. Even though it's at index B. And what is position 4? Well, this is 0, 1, 2, 3, 4th, the 4th element of our data. So that would be all the way up to 50, but not actually including 50. That's the slice. So it should be 10, 20, 30. What is 4? It's a position. It's just this would represent the fourth element in the data. The fourth element in the data, which is this is the 0th element, this is the first element, this is the second, third, and this is the fourth. Right? Numerical position. That's what iLoc uses. Based on this data, what do you think is at the first position? At position 1, what data do you think is at position 1? If you were looking at this, so 10 is not at position 1. 10 is at position 0. 10 is at position 0. What's at position 1? Right, it's at 20. Yep, it's 20. Well, so yeah, let me explain it one more time. Yeah, so let me explain it one more time. So series have an index we can define, right? So in this case, we have 5 elements. And so we have 10, 20, 30, 40, 50. And do we agree that the original index we set up for this is A, B, C, D, E? Does this make sense for our series? This is what our series looks like. Do we agree on that? So without worrying about the positions or the loc or the iLoc for a moment, does this make sense for our index? This is based on this data. That's our index, A, B, C, D, E. Okay, so we do agree on that. Okay. Now, what data if you were to ignore this index for a minute, this is the index, and just think about this data's positioning from left to right, what index would we say, or what position would we say is the 10 at? What position is the 10 in the array? If we were to just think of it as a list, let's say, what position is that? Right, it's position 0. And what position is 20? It's at position 1, right? And so 30 should be at what should be 30? 2, perfect. 40 should be 3, and 50 should be 4. So what I was saying with those examples is iLoc uses these positions, while loc uses the index. Does that make sense now? When you think of it this way? iLoc uses those positions of the data, the relative positions of them, to select things. So when we say 1 to 4, that's this slice, right? That's this slice of the data. Not including the 4. So it's really this slice. Yeah. iLoc, default indexing, loc, user indexing. Yes, I think that's a good way of thinking about it. Yep. For sure. Go to the syntax? Yeah, let me go over to there. Does it make more sense when you see it with the picture? So you see the code, loc using A, C, and E. It's picking those 3 items using the defined index. 1 to 4 is a slice. It's 1 to 4 will be this slice that I've circled here. 1 to 4 is this slice. Right, it's a slice. And remember that the 4 really means it goes up to 4, but not including 4. So it's the slice 1, 2, 3. Yeah, no worries. Any other questions on this? All right. Very good, very good. Okay. So what I wanted to show you guys is that was the end of this notebook, but there is some extra practice. I encourage you guys to try this out on your own. So this is your own practice here at the end. Try this out on your own. So this 4.01 notebook, try this out when you get a chance to do some extra practice accessing and manipulating this data. Okay. So you have some example arrays here. You'll build some series and go through and do some selecting of some data using the different methodologies we just showed with loc and iloc and um, picking different indices and things like that. So this will be some extra practice for you. What I want to do now is go over to talk about the data frame. So we've talked about series so far. We have some different functions on a series. Most of these are going to carry over exactly into the data frame in the 2-dimensional aspect. So everything we've been doing, mostly been dealing with 1-dimensional data, but we are going to deal with 2-dimensional data. Let's go over to 4.02 now and talk about the data frame. Okay. So if you have a moment, pull up the 4.02 notebook. We're going to go over to that and talk about the data frame now, which is going to extend everything we just learned over into the 2-dimensional data with rows and columns now, which is going to be the data frame. You guys have this notebook? And go over to the 4.02. Yeah, just go over to that one. I'm going to do that one next. Okay. So let's remind ourselves what a data frame is. So a data frame is now going to be our 2-dimensional extension of the series, where we are going to have a tabular data structure, meaning it's going to look more like a table. We're going to have rows and columns to deal with now. And what's going to be really interesting is we'll actually have multiple indices to worry about because we have multiple dimensions. So imagine if we had these 2 series of apples and oranges. So we had a series called apples. It has this data 3201, and it has just a natural positional index of 0, 1, 2, 3. So nothing that interesting. We have another series over here called oranges that has data that looks like 0, 3, 7, 2. It also has the same index of 0, 1, 2, 3. That's fine. That's just the default index. Now, what we can do is concatenate these into a single data structure called a data frame, where now these 2 series actually form columns in this table structure. So now we have more of a table, which is a data frame that contains one row index. So this is called the row index here. So it has a row index, which is row 0, row 1, row 2, row 3. So we can think about the data at a row level. So we can say, okay, this is one row. This is one row. It's very much like a spreadsheet, right? This is one row. This is one row. We have that. And then we have data at the column level. So we have these, what are known as the column index that we have here. So the column index just allows us to select columns based on those names. So we can always go into this table and grab the apples column. We can grab the oranges column. We could grab the apples and oranges columns together and pull back multiple columns. We have that flexibility with a data frame, just like you would in a spreadsheet. You can pick data at a column level as well. So you always have that flexibility in a data frame to select rows, to select columns, to select rows and columns. So that's something we're going to learn how to do, is select data based on where it is, what row it's in, what column it's in, select sections of a data frame, or rows and columns. What will be the merge title? So that's up to us as a variable. The title of the data frame is not that important. It's more when we add these two columns together, we get a single data frame with two columns, and we have a row index and a column index. Oops, this is the row index. But the name is whatever we want to call it. We can label it whatever we want as a variable. Like we could say this is our fruits data frame. We just call it that. Fruits data frame, which has apples and oranges as columns. And it has 4 rows, right? It has 4 rows of data and it has 2 columns. Basically, the shape of this is a 4-row, 2-column matrix, right? Think about this as a NumPy array. That's what that is, right? 4 rows and 2 columns. Okay. So one thing to point out about this, so I told you guys it has a row index and a column index. So those will be really useful for when we want to select data from the data frame. But the other thing is there's no restriction on the data types in the data frame. So the data types of one column can be completely different than the data types of the next column. So like this column could be all strings. This column could be all floats. That's totally fine. There's no restriction there of what the columns can be. They can be mixed data types. That's totally fine. There's no restrictions on data types. Oh, that's just random data. It's just random. It doesn't represent anything meaningful. It's just random. We just wanted some values to be in there. Yeah, they can be different for each row. Yeah, they can certainly be like they generally could be if, let's say I had like this data type was a string. So this column was a string, this column was a float. Then I'm gonna have like within this row, this is gonna be a float, but this is gonna be a string. So yeah, the rows can be different. If you have mixed data types, the rows are going to be different. Yeah, we're going to have lots of examples. Yeah, they're coming up. They're coming up. This is just to get us introduced to the data frame. Yeah, we're definitely going to have meaningful ones coming up. We're going to load. So the most meaningful example I can give you is most spreadsheets can be loaded into a data frame structure. So if you take any like CSV or Excel sheet, they can be loaded into a data frame, and then we can do all of our analysis on that data frame. That's typically what we're going to do with the data that is inside of a comma separated value file, a CSV file. We'll load that into a data frame. We're going to practice doing that quite a bit. Okay. All right, so before we get to those examples, let's talk about how we can create some example data frames using our code. So here we are going to import Pandas as PD. And one of the most common ways of creating a data frame is from a dictionary. That's one of the most common ways of creating a data frame is from a dictionary. Now, why from a dictionary? It's because these keys in the dictionary are actually going to be our column names. These are going to be our columns. The keys are going to be our columns, and then the data within those columns are going to be inside of this list. Okay, inside of each of these lists. So I'll show us that data frame in a moment, but this is pretty common. So the keys become the column indices, and the data within the columns are the values, which are the lists. So those lists become the data within the columns. So the name has these three strings, the age has these three ages, and the salaries have these three integers. So let's go ahead and see that dictionary. So it actually looks like this. Name, age, and salary. It looks like this. This is our data. It has 3 rows. That's not surprising because it has every column has 3 entries. So it ends up being 3 rows. And here's the name column has Alice, Bob, and Charlie. The age column has those ages that were in that list. And the salary column has those 3 there. So using a dictionary is one way of building a data frame. It's a very common way. So we can do that. The other way is to use mixed type lists. So basically where you define every row. So creating a data frame from lists is possible where we have a list for each row. So we have the first row, we have the second row, we have the third row, and we actually manually supply what the column names should be. So this is all the row level data, and this is the column name. So we can actually build a data frame off of that using pd.dataframe. We pass in our row data, and we say, here's what our column should be labeled. Here's the column indices. So these are the column indices. We say, here's what our column should be. Here's our row data, and that builds the same data frame. Builds the same exact data frame as we had before, just doing it not in a dictionary, but in a list of lists, essentially, right? All of our rows are utilized here as like this. I agree. Yeah, the dictionary is probably the cleanest way to build a data frame. I would agree. Probably the cleanest way. But this does build the same exact data frame. All right, same thing. We can use NumPy arrays. Now, this is a NumPy array. This is the 2D array of our rows, right? So here's the first row, here's the second row, here's the third row, and we can give it our column indices as well. So again, the NumPy array data is our rows of the data frame. So this data formulates our rows, and we're passing that in to build our data frame. So this should be the same exact data frame that we have from before, just using NumPy arrays to build it. Okay. All right, let me give you a more practical example that will be realistic to a lot of the use cases we will see over the course of the program when we're loading in data. And this is one that's used all over the industry. People use it all the time. I use this one nearly every day, is reading data from a file. So if you want to read a CSV file, you use the pd.readCSV function. So read CSV, and all you have to do is pass in the file path. So now this path looks a little wonky because I am inside of Colab and I had to mount this file within my drive. So this data is in my Google Drive on Colab, but generally that, like, if you're in VS Code, this would be a path to the data that is somewhere on your computer. So this is just a file path to this CSV file. Okay. And by the way, you guys should have this data. If you go into your, let me show you where it is. So if you go into your LMS, let me log in. Do you guys have access to the data sets? It should be from your reference materials. It should be in this data sets here. Okay, this data sets. So go to this data sets and the reference materials, and that's where I'm getting this house price CSV from. So if you download that and extract it onto your machine, that's where you can get that. That's where you can get that file from. So house prices. By the way, if you have it in your Google Drive, you have to run this code. You have to run this code first to be able to access files that are stored on your drive in Google. So you want to run that first, and that makes your data accessible within your. So this is if you're running in Colab. If you're running in Colab, you want to run that in a cell, so you can. This makes your data accessible. Let me write that down. This makes your Google Drive data in Colab. Okay, so you have to run that, and then once you run that, then you can access data that's within your drive. So if you go to this like folder icon, you can see you can browse your drive within this folder icon. There is, but only for the folder you have open. It's just the like file explorer on the left. Roberto, it's just the file explorer on the left, but only if you have it only in the folder you have open. So what I would recommend if you're working in VS Code is to I would recommend to put that data set in the same folder as where your notebook is, so it can discover that file pretty easily. Does that make sense? Like put that data set file. So there's two files in this notebook that you're going to want access to, which is the house prices and the iris Excel. So put those in the same location as this notebook, and it should work. So let me actually put a comment here. So you should be doing pd.read CSV, and then it should be file path to CSV, wherever that is. So I think the easiest thing to do is put it at the same location as where the notebook is saved. Because if it's in the same place, then that should just be pd.read CSV, and then it should be house price .csv. Should just be that. Loads the whole file. Yeah, loads all the data in memory. Yep, that's right, Tim. I don't have import drive command on the. Yeah, this is for Google. This is for Colab. This is only for Colab. You need this to access data on your Google Drive. The two files are the house prices CSV and the Iris Excel XLSX. Do you have those two? House prices CSV and Iris Excel XLSX Excel sheet. So you can build a data frame from here. Now, when you load all this data and you print it out, it's actually quite a big file. It has about 5,000 rows. So it's not going to show you all of that data, but we're going to have some functions we can do that can easily get us some summaries of this data, which will be nice. Okay, so we'll have that coming up shortly. But there are 5,000 rows. So, or sorry, about 4,600 rows. So it's a decent amount of data there, 4,600 rows. And the Iris data also has 460 rows and 18 columns. 4,600 rows, I should say. Sorry. All right, were you guys able to run this? Were you able to read the CSV using Pandas? Were you able to run this? Not able to. Make sure that the path that you have the. Oh, that's fine. The output's getting truncated. That's fine. That's expected. It's not going to show you all 4,600 rows. That's expected. Yes. Are you running in Colab, Mario? You are? Okay. You have to give permissions. So there should be like a pop-up when you run this code. When you run this, there should be a pop-up to give permissions from your Google account for this notebook to access your files. So make sure that that pop-up actually shows up and you click and you validate it. You should see a pop-up when you run this. Okay. Yep. Worst case, by the way, what you could do if your drive isn't mounting, a backup is to go. Do you see this file? Do you see this files on the left? And this is for everyone running Colab. If you're unable to get the drive to mount, what you could do is you could just upload the file into the workspace. So if you go to this files, you can upload. You can hit this upload button to upload data. So you can see this upload here from if you click on this and then you click on this, you can upload the file manually into this workspace, into the notebook workspace. So you could do that too. If you have the file on your computer, just upload it. That works too, without having to mount your whole drive. So just click on this upload, and then you can upload the file. So I just uploaded the house price CSV. So now I have it available in the session. And then I could just like that. What should it look like? It should look like this. You don't have to do Google Drive. You can do it this way too. Do you see the way I just showed? Where you can upload it into the session, into the notebook session. You can do that. You can keep the file on your local and then just upload it to your notebook using this files upload. Roberto, do you see this? Like all of this data displaying? That's how you know it worked. If you rerun the cell, that means it worked. It should display the same thing. If you scroll back up, people posted it, but it's in your LMS. It's in the data sets here. See this data sets link? It's this one. Download the data sets. And we're doing the house price and the Excel and the Iris XLX. Yep. Okay. So you guys should be able to see this. Now, this is loading. Let me just take a step back and say this is loading the data into a data frame. So now this is the contents of the CSV are now in a data frame. So we can do data frame operations to that data, which is going to be really useful. We can manipulate it. We can do summaries. We can do group bys. We can do filtering. We can do all kinds of stuff to this data frame now that we've loaded all that data into the data frame. So read CSV, we are going to use a lot during the program. We're going to use a lot to load in data from a file, to load in data from like a spreadsheet style file into a data frame and then manipulate that data frame. Okay. And there's a read Excel. Pandas actually supports a lot of different read functions. So it has read JSON, read Parquet, read all read arrow. It has all kinds of different file types that it supports. Okay, so not just CSV and Excel, even though those are very common. We can read all kinds of different files in Pandas to load them into a data frame, as long as they're supported. Okay. All right, so we practice loading in the data, but now what we want to do is practice accessing data from that data frame. Now that we've seen we can load data in, how do we actually access data and then start to manipulate it, summarize it, do all those things we were doing with series, we want to extend into the data frame. So let's get some practice there. Let's scroll down and build an example data frame with some fake columns here. So we have column underscore name, column 1, column 2, another column. We're going to practice accessing data from this. And then eventually we're going to come back to this data frame with all that data we just loaded from the house prices or the Iris and practice working with that. But for the moment, let's work with this fake data frame built from this. So we do pd.dataframe, that builds it out of this dictionary. And here's our column data that we have mapped to these different column names. So if we want to access a column, it's super easy to do. We just pass in that column name here inside of the brackets. So we do df, which is the name of our data frame, and we just have column name here. That's going to access all of the data within a column. By the way, what do you guys think is the data type of an entire column? We just studied it. What do you think an entire column is inside of a data frame? It's a particular type of object. You're right, it's an object, but what type of object? It's a Pandas object. Not a string. We just learned about it. We just were manipulating it. Series, very good. So a column is a series. Okay, a column is an entire series. Yep, a column is a series. So when we access this column, it's as if we're accessing an entire series. Okay, so if we print out that column, we get this. This looks like a series, doesn't it? It looks the same because that's what it is. It's a series. We're grabbing that entire column, which is 5, 15, and 8. So to access a single column, we just use the braces and we pass in that column index name and we pull back all the data from that column, which is really a series. So remember, a single column is a series, is a Pandas series. So we're actually accessing that series when we do column name. By the way, if we were to try and access an invalid name, we will get an error. So let's say we did some column. Now this doesn't exist, so this will give me an error. So if I try to do this and that doesn't exist, this will give me an error. And you can see what kind of error I get. A key error that this does not exist. Basically, I don't know how to access that column because it doesn't exist. Right, so this is, we would not want to do this. We would want to use the proper column name, and that should work just fine. Okay. All right, now how about this guy when we pull back multiple columns? So we can use a list and select multiple columns at once. Now, what is a collection of series? We are studying it right now. What is a Pandas collection of series? Perfect, DF. Perfect, you guys got it right. Data frame, perfect. So when we pull back multiple columns, this should be multiple series, which is a data frame. So you guys are absolutely right. When we access multiple columns, gives us a data frame. So this is actually going to be kind of a miniature data frame. It's only going to be these two columns because we're accessing these two guys, which are these two columns worth of data. That's kind of like a mini data frame that's part of the whole data frame, right? Selected columns there. So let's look at that. When we access multiple columns, we get these two guys, which is a data frame. Okay, we get column 1, column 2, and we see the data, and we have 3 different rows from the data frame. So we definitely can access as many columns as we want by passing in a list into that data frame bracket, and it will allow us to access multiple columns. Now, we can't forget about loc and iloc. So, for instance, iloc will allow us to select particular rows based on the index. So iLoc of 0 is based on the position. So this is saying, let's grab the data that is at row 0. So again, this is using the positional index 0. Regardless of what the actual index is, the user-defined index, and DataFrames can have user-defined index. The rows can actually be a custom index as well, because we know a series can have a custom index. So iLoc doesn't really care about our custom index. It's going to use the positional index to grab that entire row. It's grabbing the first row. So df.iloc is grabbing this entire row, which has values of 5, 10, and 100, and 25. If you look at it, that makes sense. That should be this row here. That's the row, that first row. We can do filters, just like we did with series. We did filters. We can do, so we can do conditional filters here, where now, how do we do that? It's exactly how we would have done with the series, right? So we do a bracket to signal that I want to access something, and here we give a filter. So what this filter does, meet the condition. Okay, so any row where this condition is occurring, in other words, this column name, it has a value greater than 10, we will keep. So we go to that, column name bigger than 10, which ones are bigger than 10? It looks like only this guy is bigger than 10. So we really should only be keeping, this row here. Should be the only row that gets kept, because that is the one that corresponds to where this column has a value greater than 10. Okay, do we see how that filter works? We're really checking, so we go back to the syntax. We're checking where a particular column is greater than 10. Only those rows do we keep where this condition is met. So what we should do is go and double check this. So the filtered rows, we only are keeping that one row. So we just filter that one row because that's the only place where this guy is bigger than 10. So that's very powerful. We do this very big kind of filter operation on the data frame. So you have to think of the filter operations we did on the series, we're extending it into 2 dimensions. We only keep the rows where this condition is met. Okay, only keep the rows where that condition is valid. Any questions on that? Only keeping the rows where that condition is valid. Yeah, so why do we need df twice? It's because overall we access data by using df and then the bracket, right? So that should be generally accessing data. We saw that with the series too, right? It's a series and we have bracket. We saw that with lists. Usually it's a list and then a bracket and we pass in an index. So we generally have the first df with the bracket to signal we're accessing something. Okay, just generally we're accessing something. Now the reason we have df twice is because inside of here is a filter condition, and the condition says I want to look at this column. So the reason we have the data frame twice is you see that we're accessing that column, which is df bracket the column. This accesses this column and says, I want to check where this column is bigger than 10. All the rows where this column is bigger than 10. That's why we see df twice. We see it once on the outside to signal that I want to access something from this data frame. What do I want to access? Only the rows where this condition is being met. Only the rows where that condition is true. That makes sense, Roberto? Yes, we're going to study that coming up. We're going to study that exact thing, how to get a summary. We're going to look at that. Yep. It's coming up soon. That's correct. Yeah. So if we had multiple conditions we were checking, we would be using df multiple times. Yes, that's true. Show once again how we can load data from local folder. Yeah, sure. So do you guys see this folder over here? Do you see this folder icon on the left? Click that. Click that folder, and it should show something like this. And then click this upload button right here. That's how you load data into your notebook session. Yeah, so you can get the path. By the way, you can always get the. Do you see the file in there now? Do you see the file in there when you upload it? You can get the path of it by clicking to the right of it, these three dots. You see how there's three dots? If you click that, you can copy the path. Click on copy path, and then you can. It's the same code. It's the read CSV. Read CSV, and then you put in your path inside the string. Like this. Which I think it's probably the same, probably this for you. It's not from your computer. No, if you're in Colab, no, it's not going to be from your computer. It's going to be from the uploaded file. Are you working in Colab? Yeah, so if you're in Colab, it's going to be from this path. It's this path of the uploaded file. Or your drive path, wherever it is in your drive. Yeah, we're just somewhere in the cloud where you've either uploaded it here, and you can always copy that path. Oops. Oh. Okay. Where was I? Oh, we were doing the filtering. Okay. Let me ask you guys, does the filtering make sense to us? It does? Okay, perfect. All right, I have one more thing I want to talk to you about on the filtering, and then we'll take another little bit of a longer break, so we've been going for a couple hours now. So once we filter like this, we're basically picking all the rows that we want out of the original data frame, right? Because that's what this does. It selects rows based on meeting this condition. But there's nothing stopping us from accessing a particular column after we do that filter. So that's what this, I'm going to scroll down to the bottom of this cell and go to this example, and I'll come back and talk about IAD, and loc in a minute. Once we come back from a break. I'll cover those. But do you guys see how we are accessing? This is the filter again, same exact filter. This is bringing back. So let me copy this and make a comment here that this part of it gives us the DF rows that meet the condition. And then we access a particular column of these rows. So that's what this does. Do we agree on that? So this is saying I've already filtered my data frame to be filtered to this set of rows, but it's still all columns. So if I were to draw this, right, if I were to draw this, we've basically filtered it out to this selection of rows. Just imagine that, right? We've filtered it down to this selection of rows. But what this thing does is says, let's zoom in on this column, right? Let's zoom in on that column. That's what that does. So we are allowed to do that in the syntax. Once we filter, we can select a column from the filtered result. We can basically chain those together, which is what that's doing. That code is doing. Yeah, I'll summarize it in a moment. Okay. All right. So let me just summarize the things that we've done in this cell. Let me move that. So all we did was we created a data frame with some example data. We didn't even use that data yet. We'll come back to it. But we're just using this example data from this dictionary, and we were just practicing some different things, like accessing a single column. All you have to do is put the brackets and then the column string, which corresponds to whatever column you're selecting. That is going to retrieve the series of data, in this case, like the column, right? 5, 15, 8. So it's doing that. You can select multiple columns if you pass those names inside of a list. So column 1 and column 2. This is actually going to give us a data frame result, right? Because now we have multiple series being pulled back. Multiple series equals a data frame. Okay, multiple series equals a data frame. So we have a data frame result that is giving us only these 2 columns out of the 4 columns that exist. We can use iloc to grab a row based on the position, the positional index of that row. Like this is the first row. We can do the second row. We could do the third row, the fourth row, etc. So that's just the first row. We did a filter. So this is just a basic filter. We were just talking about this where this is the condition. And so this is saying, let's grab all of the rows out of this data frame where this condition is being met. Okay, all of the rows where that condition is being met. All right. Then, yeah, different from a slice. Different. This is a filter, different than a slice. This is because this is conditional, right? A slice is more positional based. It's not conditional. This only selects data that meets this condition. This is conditional. And then what we said is based on this condition, we can actually select another column right after that, which kind of chains it together. Yes, Roberto, it's like a bidirectional. Yep. So while you try that, let's continue talking about on this set of examples here. We had the at. We had just gotten to the at. Now, the at is like the equivalent of loc for accessing a single entry in the data frame. So this is the equivalent of df.loc for a single value. So at will use the index. So at uses the index, uses the row index and the column index for accessing. So the row index in this data frame is just the default. It's just the positional, just happens to be that way. Does it have to? No, it could be dates, it could be strings, it could be anything. In this case, we didn't specify any special row index. We do have column indices, right, which are these names. So we can use those, but there's no special row index with this dictionary when we create this. So it just has the default row index. So when we use @ we can say, I want the value at the first row, which is row 0, the second row, which is row 1, the third row, fourth row, fifth row, and those are all going to be this positional index because that is the true index of this data frame, the row index. However, we also have the column index, so we can access things based on that. So column name, we're grabbing the element in the column name column, but the first row here. So this should fetch us this 5 because we want to be within this column, but the first row. So this @ should return to us the a 5. So if you go down to single cell by label, this should give us 5, which is what it does. So sometimes you can use @ again, this you only ever use it if you want to access a single item, which is kind of rare. You're not usually going to be grabbing just a single item in the data frame. Usually you're going to be grabbing multiple rows, multiple columns. But there is the @ function for passing in a row index and a column index to access a single item. Yes, but that's true, Ramiro. But I would call it the row index and column index. In this data frame, the row index is 0 because it has the default index. Right, it has the default index for the data frame, which is 0, 1, 2, 3. It's this. This is the row index, right? This is the row index, and then this is the column index. Column index. All right. So with @ we have the equivalent of loc. But for accessing a single item, we also have I@, which is this is the equivalent of iloc. So this is the equivalent of iloc for accessing a single element. And so this one we use. So this one uses the positional index for row and column. So we do not use the name for the column. We only use its positional index as far as which column are we in going from left to right. Are we in the first column? Are we in the second column? Are we in the third? This would signal that we are in the second column because that is the column that is at index 1. So if you use the positions with I@ or iloc, for example, we would be like, this is column position 0. This is column position 1, column position 2, 3, regardless of the actual column index, right? It has a position within the data frame going left to right. Every column has a position. So I@ uses this column position. It also uses the row position regardless of what this is. It just happens to be the same because the data frame uses the default row index. But so 0, 1, if we did I@ and then we did 0, 1 would be the first row, second column. Right, first row, second column. So that should be this guy. So we look into our data that we have, which is this data frame right here. It should be first row, second column. It should be 15. So we want to make sure that we get 15. So if we run that single cell by position, don't know why it's saying. Finally, we have df loc. So if you guys remember, loc uses the we've kind of already talked about this, but loc uses the indices, right? So it uses the row index and the column index. In this case, we're selecting the first row, but all of this column named column name. So here we are selecting the first row, but all of column name column. We're picking all of those values. So we should be getting first row, but the whatever is in the column name entry. And so that would be if we go back to, we should be in the first row, but only getting this 5 essentially, which is the value in that column name. So loc will use the indices just like at would. So at uses the indices. Loc also uses the indices. Basically, loc we would use though when we want to select. So we use loc just like we did when series, right? We use loc to select multiple values. You can even slice the rows. So for instance, we can grab the first 2 rows and slice it that way. And that would pull back multiple values for this data selected with loc. So it's actually going to grab all of those rows 0 and 1 and the data belonging to column name. So you can even put it, so you can use loc to grab multiple entries. So you can have a slice in there, which is pretty interesting. So here's a slice, 0 and 1 rows. All right, any questions about these? We're going to get to some really important summarization functions coming up, but any questions about these, like accessing patterns? I think the most common way we will access data will likely be from picking columns like this, or honestly doing filters like this. Those will probably be the 2 most popular ways we select data. JD, they do for the rows. Yes, because most people use the default row indices, but the columns usually have a label, right? They usually have a name, like this example up here. The columns usually always have a header. They usually have a name, right? If you think about an Excel spreadsheet, columns usually have a header to them. But rows, yes, usually will have a default index like 0, 1, 2, which kind of lines up with their position. Okay. Very good. All right, let me get to some exciting summary functions that we will cover next. So I want to go through some basic data frame functions. Now that we've seen how to access data, let's look at some other convenient functions. And some of them are going to be really familiar from basically from series. They're going to be the exact same, like head and tail and sort and is null. Those are all going to be the same that we have, except now it's going to be in multiple dimensions. So let's take a look at some of those examples, but some of them are going to be pretty unique. But some of them are going to be basic multi-dimensional extensions of the functions we've already seen for series. So let me walk you through some of the functions that we are going to do some examples with. The first couple we've already seen, which are head and tail. So just like in series, we have a head and tail function which shows us the first few rows of the data frame. Remember, if you don't put anything in the head and tail argument, like if you leave this blank, it will just do by default the first 5 or the last 5 rows for head and tail. Now, why is that helpful? It's actually really helpful often when we load in a data frame. The first thing we typically do is run a head or a tail so we can sanity check what we just loaded without having to print out the entire data frame. Printing out the entire data frame is usually inefficient, and we don't it's going to get truncated anyway. So a very standard thing to do is to just print out the head or just print out the tail so we can get that view of the first 5 or last 5 rows to sanity check what we just loaded in. So that's a very common thing to do. We're going to see examples of that, and we're going to use head and tail quite a bit as we move along. And as we load in data, that'll be usually the first thing we do is head or tail, just to take a look at the data we just loaded in. Yes, it's going to include the header. Let me show you an example. So if we go back to the data we loaded earlier, so the house prices, let's print out the head. So df.head. It shows you the header, but it just shows you the first 5 rows. See how it's just the first 5 rows, but we can see all of the contents of the data pretty nicely and succinctly. So it's a very useful thing to do, right? When you load in this data, this is very useful to do to sanity check, what did we just load? What does it look like? df.head, we can get a sanity check of what the data looks like after we load it in. And we could do tail, so that will give us the last 5 in the data set, right? That'll give us the last 5. So we can see there's 4,600 rows. This gives us the last 5 of them. Sanity check that too. Usually we look at the first 5. Okay. So head and tail. Now, you were asking Roberto about a summary earlier. Here is a couple of really nice summary functions, which are going to be 2 that we'll use quite a bit. One is called the info, which gives us an information summary of the data frame, including all of the columns that exist, all of the data types, and if there's any data missing from those. So the df.info function, which you see used right here, is an incredibly useful function to give us a summary of what is there. Okay, it gives us a summary of what exists. So let me show you what that looks like on the example I just did. So on that house price data set, we looked at df.head. Let's do df.info and print out the information summary. So if you take a look at this summary, what it looks like is we have a total number of columns. We have a total number of rows. So 4,600 entries, that's 4,600 rows. We have a listing of all of those columns and how many non-null values they have. So you can quickly eyeball and see which columns are missing data, because we're expecting to have 4,600 entries in every column. Those are the rows. And this tells us how many were not null. So 4,600, that's a good number. That means we have full amount of data not missing. Right, that's pretty good. Not only that, but we get the data type. So what this would tell me is anytime I see object, I'm thinking of that as a string. thinking of that as a string. So the date is just a string of the date. The price is a float, bedrooms is a float, bathrooms is a float, square footage in the living room is an integer, square footage of the lot is an integer, floors is a float, waterfront is an integer, view, all of these things. You could see exactly what year that it was built was an integer, year that it was renovated. So you could see what all of these columns are about these houses. It's all different attributes of the houses. These are all strings, so they're related to like street, city, zip, country. They're all address related things. Are all, strings. That's not surprising. So you can see that we have a bunch of float columns, a bunch of integer columns, about 5 string columns, and this is how much memory our data frame takes up. That's a pretty good summary, I would say. Is this the summary you were looking for earlier? Oh, that's a pretty good summary of all the columns and their data types and not null. This is a great summary. Yeah, so this is df.info. df.info gives us that information summary about this data frame. What is non-null? Non-null means not missing, like not null values, not missing. Right? Meaning it's like not empty. Okay. So we have info, incredibly useful. Now, do you guys remember this? We had this for the series, was to describe. Now, this gives us a summary of the statistics. And now if we take that describe, remember, it was operating on every series, but what is every column of our data frame? Let me ask you guys, what is every column of our data frame? What kind of data type is it? There we go. Yes, it's a series. So should we be able to do describe to every column? Because remember, describe was a function on a series, right? We've already seen that. Describe gave us a summary, a statistical summary of our series. So it should be natural to extend describe to the whole data frame. That should be pretty natural. And we will. So basically what describe will do, we'll take that same exact describe that we did on a series and we'll do it across every column. Every column that is, the catch is, it's only going to do it to columns that are numerical data types. So it's not going to do this to strings, okay? Because it doesn't make sense to compute like an average or a median or a percentile. Right? It doesn't make sense to do that to object columns. So it's only going to do this to numerical types. So it's going to do that summary for every numerical column. So numerical meaning it's some type of integer or float. It's going to compute the min, max, average, median, percentiles, standard deviation. All of those are going to get computed. So that's a great summary. That's a really great summary to get a sense of what our min and max, like our range is, what our average is. That's a great summary as well. So let's run that on the housing prices. So we go back up. We just did info. Let me do df.describe. So this should be computing those averages. So this is going to be computing those values across all of those numerical columns here. So for the bedrooms, the minimum is 0, kind of wacky, 0 bedroom. And the max is 9. So there's a 9-bedroom house in there. The minimum bathrooms is 0. I'm gonna guess that's likely because it was missing, so it just filled in a 0 in the spreadsheet. but the maximum bathrooms is 8, and the average bathrooms is about 2, little over 2. The average bedrooms is about 3. I think that makes sense. It's pretty reasonable. Just sanity checking. Just sanity checking that. And then we see that the average price is sitting here about 55,000, or sorry, 551,000, I think is what that is. Because Roberto, I mean, it's not missing, but it was filled in with a 0 ahead of time. So there technically is a value there. It's just meaningless, basically. But there is a value there. It's just kind of like defaulted. Yeah, so you're right. Like 0 bathrooms would make no sense. So that data is likely probably not good, probably not very great data, but it's not missing. There is a value there. It just happens to be 0. It was probably like whoever was recording that data didn't have a number of bedrooms and bathrooms, so they just put 0. Does that make sense? Like if you were filling it out from a survey or something, they just probably just put 0 as a default. You didn't know what it was. Just put 0. How can you remove scientific notation? You can display it, I think, as a normal value. So I think if you grab, let's try this. Okay, so if you set that at the Pandas level, which will default that for everything, yeah, that works too. I like the round though, because we can be a little more selective on when we do it instead of just doing it by default to everything. But thanks for, yeah, I agree that that should work, setting it at the Pandas level. Yeah, Roberta, this is just rounding the describe results. It's not rounding the real data. No, it's just rounding the describe results. That's true. Okay. What do we think about describe? Does it seem useful to you guys? Does it seem useful to have a nice summary view of the statistics? Like you get a mean, you get a min, you get a max, you get remember the 50th percentile is right. You get the median, standard deviation. So about the average house price in this data set is about 551,000. Now there's a max that's way out there. Looks to be like 26 million. I mean, that seems like an outlier. I'm gonna guess it's this 9-bedroom, 8-bathroom one that has 13,000 square feet. But seems like seems like an outlier potentially. But maybe we'll study that later on when we get into the get into identifying outliers and such, which we will. But that seems like yeah. And the square footage of the lot. I mean, this seems like a lot of land. So that's we'll have to see if that's an outlier or not. Okay. All right. So let's go back to our function. So we had describe. Now, the shape we know we can get. So that's just an attribute. This isn't even a function. This is just if we ever want to see how many rows and columns we have, we can do dot shape. So we go back to our data. We can do, so we had the statistical summary. We can do df dot shape to see how many rows and columns we have. So we have 4,600 rows and 18 columns. That we know that's what we had. So not surprising there. We can always do dot shape to see what we have. Now, what's interesting is we can also do dot columns to get a list of all of the columns that we have. So that's another useful one if you want to quickly see, if you want an exact list of all of your columns. So df dot columns. This gives us a list of all of our columns. So we can quickly see which ones we have. And we have a list of those guys. So df.columns gives you the kind of listing of all the columns that are in your data frame. All right, loc and iloc, we've already talked about. Those gives us the ability to access data. So we have, those are the same from series. We just did some examples with those, so I won't spend too much time on them. I want to get to a couple of interesting ones. Any idea why I'm not getting my house price head or tail? Data load is complete. Are you running it like what did you load it into? What did you name the file when you did read CSV? What did you name it? Okay, so you should be doing df csv.head. Does that work? You can either run it in the cell or you can try printing it. Either one should work. If it's not working for you, you could try restarting your session. If you're in Colab, you could try restarting your session and rerun it. Maybe that'll work. Okay, it works. All right, great. Yeah, that should work. Just df. That's what I did here. You don't need to do it with print. You can just do it in a cell and run it. Should work. Yep. Should work. Okay, so we can sort, we're going to do some examples with sorting down below, but what we can do now, what's interesting about a data frame is when we sort it, now we have columns at stake. So sorting is a little more complicated. We have to decide, how do we want to sort this data frame? Which column do we want to sort the rows according to? So that's where sorting the data frame has the ability to sort by one or more columns. So here you pick which columns you want to sort by. We're going to do some examples with this, but you can basically sort by one or more. So you can say, hey, I want to use the square footage and sort everything from greatest to least square footage, which will shift all the rows around according to that square footage column. You could sort by the number of bedrooms, number of bathrooms, right? We can pick which columns we want to sort by. So that's the only thing is, like, when we're sorting a series, we just sort the data. It's only one dimensional, right? So we just sort it. But when we have a data frame, we have to be more selective and pick which column we want to sort by. So that's the only thing that we have to be careful about. So we'll do some examples with that. Now we have some another interesting function here that we're not going to get to today, but we'll cover this in our later lesson 8 or 9, or sorry, 9 or 10, when we get into working with our data. But data frames support group by operations, which is basically, like, if you're familiar with SQL, doing a grouping of the data according to a certain column, and then we can do aggregations based on that group. So we will learn about this later, but data frames support grouping according to certain columns, which is really useful. So suppose we want to group by number of bedrooms. So we want to take all of the houses that have a certain number of bedrooms. So all the 2-bedroom houses, all the 3-bedroom houses, all the 4-bedroom houses. We want to group by those and figure out what their average price is. We could do that. we could group according to the bedrooms and then do like a mean on the price. Those kind of slicing and dicing we will be able to do later. We're not going to get into it today because it's a little more advanced, but we're going to have a whole lesson dedicated to doing this in the future. So we'll come back to group by later on. But that's a really, really useful, as you can imagine, right? Grouping by column is really useful. So we'll get into that later. Now, one function we've already seen, and it will show up here again, is the apply. So we have that basically the same to where we will be applying a function usually to a column to transform that column. So usually we will apply to a column or maybe multiple columns in order to transform them. So maybe we want to take a column and multiply everything by 10, or take a column and square everything or divide it by 5, or whatever the case is. We can use df.apply to apply a function to a particular column, just like we were talking about with series, because what is a column? It is a series. So it should make sense that we can apply a function to that series. And so we will be able to do that. We're going to see some examples here of using apply to transform an entire column of a data frame according to a function. Right. So remember, the argument to the apply is a function. So we're passing in, hey, what function do I want to transform this entire column according to? Do I want to square everything? Do I want to cube everything, take the square root of everything, take the logarithm of everything? And really, when you're looking at the column level, that would be every row, right? Every entry within that column we're going to transform. So we will do that in some examples coming up. So we're going to see apply. Now, something we're going to see later on that we have that will be also in the same basic lessons that we're going to learn about group by is going to be the merge or concat. Now, this will be able to take multiple data frames and merge them together. That's incredibly useful. You can imagine like loading in data frames from multiple files, and those will create multiple data frames, and we want to bring them together in some way. So merge them, like join them together like you would kind of like a database table join. We'll be able to do that, or just actually concatenate them. Just maybe they represent the same column, so we just stack all the rows on top of each other in a concatenation. So the ability to merge or concatenate data frames, we'll learn about that later. I don't think we'll do any examples today of those, but we'll, again, whole lesson dedicated to grouping, a whole lesson dedicated to merging, concatenating. So we'll certainly cover that later on. Okay. By the way, any questions about any of these functions so far that we've kind of touched on? We're going to do some examples. We're going to do apply. We will do sorting. I'll show us that in a minute. But any questions about some of these functions so far? Good? Okay. Nice. Okay. All right, so a couple more. What's really nice, and we're going to learn in the next lesson on how to do this alternatively with Matplotlib and Seaborn and some of the plotting libraries, is DataFrames have built-in plotting that uses Matplotlib as kind of the backend to do it. But you can actually directly from a data frame plot columns, which are really useful if you want to quickly visualize something about that data frame. So if you want to actually see what is a bar graph of all the, or a histogram of all the housing prices, we could do that really quickly just with the data frame. We don't need to use any additional plotting libraries. So that's usually for quick quick plotting. We're going to see some examples of this coming up of how we could do this within this notebook. We'll see some examples of doing this, but we'll also, in our next lesson, in lesson 5, we'll talk more about plotting. Lesson 5 will be all dedicated to doing plotting with the more sophisticated libraries that are dedicated to plotting. But just for doing something quick, the data frame actually supports plotting directly out of the box. We can do something like df.plot and directly plot attributes of it, rows and columns of it, which can be pretty useful. All right, finally, data frames have the ability to drop rows or columns. So if for some reason we need to delete rows or columns, we can definitely do that. A pretty typical use case for that is maybe we load in a data frame from a CSV, like a file, and there's some columns we just don't need. Maybe there's a user ID, or there's some type of useless like extra column that's snuck in there that we don't actually need. We can go ahead and drop it. So you can drop multiple columns, you can drop multiple rows. We will see some examples of this as we go along, but pretty typical use case is dropping columns. And usually what you do is you just pass in the column argument here of which column do you want to drop. So it's like, okay, I have a user ID column. I don't really care about it. I'm gonna drop that, but doing df.drop and then go ahead and pass in that column index to go ahead and drop it. Okay. So we'll see an example of that coming up shortly. Okay. Any questions on some of these functions? We're going to jump into some examples next of some of these guys that we've been talking about, but before we do that, any questions on any of them? Okay. Very good. All right. So let's go ahead and take a look at some examples. So we're going to have some fake data here in our data frame. So we're going to build out the data frame we kind of had earlier, very similar one. We put that in the data frame, pd.dataframe, build the data frame here. Oh, you had a question on the merge. Left and right, no, those are the two data frames. So this would be merged together. So this would be df1 and this would be df2. We have two separate data frames and we're merging them together. The on is usually a label of a column that they share. Like if they share a primary key column, then that would be like a join. Yeah, Roberta, that's like a SQL join. Yeah. This would be an inner join between these two tables. And we have a join key here. That would be a column. This would be a column that we want to join on. We'll learn about that later. Yeah, we're going to have a lesson dedicated to doing that. Okay. All right, so if we were to go back to this example, now head and tail, no surprises there. We can print out the head and the tail. This gets us the first two rows. This is the last row. So first two rows should be these guys. And then the last row would be this guy. So we can take a look at that. First two rows, again, here's those. Last row, this is this. I don't think there's that much surprise with head or tail. I think we're pretty comfortable with that. Info we've already seen before. So the info about this one is that it has these 4 columns here. It's not missing any values. It only has 3 rows. It's not missing any data there. It's a pretty small data frame, only 220 bytes. Makes sense because we don't have that much data stored in there, just some integers. It's not that big of a data frame. Only has 3 rows. And the shape of it, so we can print out the shape. It is a 3x4 data frame. It has 3 rows and 4 columns. We know that. It makes sense, right? Not that surprising there. But some of these things we will see, like, now let's sort it. We could actually sort some of this. Let's sort this data frame. Let's do some additional code here and sort it. So let's go ahead and do print, and then let's do df.sort values. Let's go ahead and sort according to, this is where we pass in the column that we want to sort by. So let's go ahead and sort according to this. Oops, I'm in the wrong section. Let me sort. I want to sort this one. Let's sort according to column. Which column should we sort according to? Maybe this one, we just unsorted. Let's sort it from least to greatest, so column name. Let's use column name as the column we want to sort according to. Let's see what this does. Oops, this might need to be, sorry, this might need to be a list. Oh, I didn't run this yet. That's why. Okay, there we go. So it ends up sorted. So see how that now shifts around this guy to be sorted. Now all of the rows are sorted according to this column. So we went ahead and sorted that, which will you see how originally it started as 5, 15, and 8. Now it's been sorted from least to greatest, which is the default. But of course we could change that to be ascending equals to false, and it should now do greatest to least. So 15, 8, 5. So that's the primary sorting that's done. And so that's an example of sorting. We could also, so this is an example of sorting. And then we'll do an example of dropping. So let's go ahead and do df.drop. Let's go ahead and drop the column. Let's drop column 1. Let's say we deemed that guy to be pretty useless. We're going to go ahead and drop that one. So we can go ahead and drop that column. Now, one argument here I forgot to mention is that if we don't, the default is to not do this permanently. In other words, if I run this, it's not permanently going to be dropped. We're just going to get a copy of the data frame as if it was dropped. So we're not going to get, so I could save this result as df with, and save that as this. And what that will do is it will pretend that we had dropped this column from this data frame and store that result in this new data frame, which is a copy of the original. If we don't want to do that and we actually want to permanently drop, then we can set this argument called in place, and we set that to true. Now, what that will do is it will permanently drop that so that this data frame no longer will have this column 1. So we can do that and it will no longer have column one. Oops, I may need to have this inside of a list. Oh, I think I need to do columns equals. There we go. So now if I go ahead and do df, it no longer has that column, right? It no longer has that column in there. So this is saying I want to drop this column, and I want to do it permanently. So therefore I go back and print out the df. It no longer has that column in there. It's been deleted. I've like permanently removed that. But if I don't do in place, let me show you. If I don't do in place, let's rerun this. I want you to see the difference. If I set this to false, which is what the default is, then I do that, and then I print out. If I go back and look at the df, it still has column one in it, so it's not permanently deleted. I just get this copy when I do this, and I can certainly store that df with drop. And then I can display this, so df with drop. And now this guy does not have column one, but if I go back and look at df, it still has that column. So you have to make that choice when you do these drop operations. Do you permanently want to alter that original, or do you just want a copy with that dropped column? It's really up to you, but either so if you want to permanently alter the data frame, you set in place equals to true. It will permanently drop it. Does that make sense to us? In place equals true will permanently drop it. Any questions on that? We stopped using it earlier. So I stopped using it because when you're working with data frames, you don't need to print out everything. You can just run it in the cell and it will render the data frame directly in the cell. That's a specialty of notebooks. They render data frames for you very nicely. So you don't need to directly print everything. You can just execute the data frame and it will display it in this nice kind of like table format. So yeah, I should have called out sooner. We can do both. So like if I print this, it's just gonna display it in a lower cell. It's just gonna display it like this. It's not gonna be as nice. If I just, it's still the same data, but if I just do df, it's gonna render it as kind of a table, which is nice. That's just a feature of the notebook. All right, so this is the 4.03 notebook. So you have a moment, you want to pull this one up. This is the one we had finished last time. We had just gotten to the beginning of it. This is where we left off on. And we had skipped down to this portion of it where I had mentioned that we have the ability to convert dates that come from our data as a form of a string. We have that ability to convert those dates over to a datetime object, which is really advantageous in Pandas to do because we can extract a lot of information from that object and manipulate that object a lot better as a datetime object rather than if it was just a regular string. It's not that useful. So this was an example of doing that. I just wanted to recap that. Here we have a single column, which is the date column. And so if we were to do df.info at this stage, which is what I put there in the code to kind of do like a before and after. If we currently look at that info, it tells us that the date is an object type, which is Pandas's way of saying that's really a string. And we know it's a string because we are hard coding the data as a string, right? So it's being read in as a date string. But one simple line of code we have here to overwrite that date column and set it equal to a conversion, which is to take your existing string date column and pass it into this toDatetime function. What that's going to do is Pandas is going to convert those strings over to what are called datetime objects. And you can tell it's a datetime object because when you look at the info after doing that, you can see that now we go from a generic string over to datetime 64 object, which 64 just represents the precision. It's down to like, it can go down to the nanosecond of time. Yeah, Tim, it guesses. So there is an argument here in the toDatetime. There is an argument here to supply like a format string to say like here's the expected format of these here's the expected format of, so see how there's an argument called format, which would be something like this. We can do format equals, and we can pass in a string to say like, okay, we should have years, months, days, something like that. So if we know ahead of time what it is, we can pass that in, but Pandas will take its best guess based on what the string looks like. So in this case, it is like this, right? It's years are first, then months, then days. So it is like this, but Pandas will guess at that and take its best guess based on the underlying string. But yes, you can change the format here that is expected when you're converting the strings into the datetime objects using this format argument of the toDatetime. Does that make sense? So you can override it, but Pandas does a pretty decent job of guessing what it is. Which is the default behavior. If you don't specify kind of a specific format, it will try to guess what it is based on the string. Okay, so why bother doing that? Well, it's because once we have it as a datetime object, which it now is, we can extract various pieces of information about that date. So, for example, we in order to access attributes about the date, we use the DT property, which is short for the datetime property. So we're accessing the datetime attribute, and we're accessing the day of the week. So, or sorry, the day of the month. So this would give us like the numerical day. In this case, we know from the string it should be 1, and it should be 2, and it should be 3. But we're actually going to generate that into a new column. This is going to take every date and extract its day of the month. So this extracts the day of the month from the date object, from the datetime object. Okay, that's what this .day does, is it extracts the day of the month. So, and we should end up with a column that has 1, 2, and 3 as oh, I'm sorry, not those. Should be 1, 15, and 20. Those are the days of the week. So let's get the format right. Similarly, we can extract the month of the year. So this is going to be the first month of the year. This is going to be the second month of the year. It's going to be the third month of the year. And that's going to be the integer month. So this will extract the integer month of the year. So first, second, third, fourth, all the way to 12. And then this will extract the integer year. So we know these are all 2023, so every one of these should be 2023. But of course, if we had data that had different years, we can extract that year directly from this date object. And so in a way, you can think of this toDatetime function as kind of like parsing the date. It kind of parses the date for us. so that we can extract pieces of information out of that date that we may need to know. We may need to know specifically what is the day of the month, what is the month, or what is the year. We may care about only those pieces of the data. So if we take a look at it, you can see that these turn into integers because these new columns have the extracted information from these dates. What's great though is even when we have datetime objects and we go ahead and print or we display the datetime object, it still displays like a normal, formatted date, which is nice. Like it doesn't display as a generic object. It actually displays as same thing kind of as a string, but we know it's a datetime object, and that's what allows us to extract these bits of information out of those dates. Okay, so that's pretty useful. Now, these are not the only pieces of information we can extract. We're actually going to do some more examples with it, but those are pretty useful just to be able to extract the day, month, and year from the string. Any questions on that? Good. Okay. All right. So let us continue then. We also can extract other things from the datetime objects. So we have an example right below where we actually, instead of converting strings over to datetime objects, we are going to basically build a date range. So Pandas supports building a custom range of dates if you want to build. So this will create a custom range of datetime objects. So what this means is we want to build a range that starts on this and has 5 days essentially. So the default is how many days do you want to separate from the start? So think of this almost like a slice of dates. We want to start on the first and have 5 days worth of data. So when we first look at our data frame, it starts on the first and goes all the way up to the fifth because that is 5 total days. So if we change this to 10, that would be 10 days starting from the first. We could do 100 days starting from the first. So think of this as number of days that we want starting from this exact date. This builds a range of datetime objects using this syntax. Okay. So what's nice is we don't need to convert anything here to strings. Because we're building a custom date range, it already is going to be a datetime object. And because of that, we can extract something like the day of the week. So this is an integer. So we extract the integer day of the week. And something I should say about that is Monday is 0, Sunday is 6. Okay, so it starts on a Monday as a 0 and then goes Monday, and then Tuesday is 1, Wednesday is 2, Thursday is 3, Friday is 4, Saturday is 5, and Sunday is 6. So this just gives us the integer day of the week. Why might we care about that? Because that might be useful data to know, is what day of the week is a particular date. We can always extract that if we know the datetime object. We can extract the day of the week, which is not immediately known. If you take a look at this date, like January 1st, we don't know what day of the week that is necessarily, but Pandas can compute what day of the week that should be by just extracting that from the datetime object. It can extract that. Okay. Now here's an example where we can use that day of the week to create a new column. So we're going to create a new column called is weekend, and we're checking here if we can, if we divide by 5, if we get a remainder of, if it goes into, if the weekday if we divide by 5, if we get 1, that means that it must be a 5 or a 6, right? That's what this means. But the alternative is to do something like df date, and then we could just do .dt.weekday is greater than or equal to 5. That would probably be the that'll be the same thing, because the only 2 days that are going to be a weekend is a 5 and a 6. So if it's 5, it's a Saturday. If it's 6, it's a Sunday. So I think that would be, we could just do that. I think that would make more sense, is to just check this condition if this is a true or false. That would be the same. That should give us the same result as this. So this is a way of doing it, is checking the integer division by 5. If we get a quotient of 1, that means 5 will divide at least once into that day, which means it must be a Saturday or a Sunday, right? If 5 goes into that day fully at least once. That's right, JD. Yeah, it's a quotient. Oh, I'm sorry, I missed your question, Roberto. Are periods always days, or they can be weeks? No, they can be different. In the date range, you can change the frequency to be you can change the frequency to be like a string. So the frequency can be like a day, it can be a week, it can be a month, um, it can be a year. Does that make sense? It's a character. The default is day, which is D. So this means 5 days starting from this day. That's what this would, if that's what you read with this. But we could change it to be months. So it'd be 5 months starting on this date. Does that make sense? That's a great question. Great question. Yeah. So it's this frequency parameter, which changes, like you can change it to weeks. So 5 weeks starting on this day. I think you can even do quarters. So like 5 quarters starting on that day. You can do Q frequency. But the default is day, 5 days. You can do time. You can also do hours. So you can do like hours, which is H, or minutes, which is M. So you can do those kind of frequencies as well. Actually, I think it's lowercase m for minutes. Uppercase M is months. Yeah, we can. I mean, yeah, we can run this. So you see how we did every month. It goes to the end of the month. So it goes. See how it goes to the end of the month for those 5 months. So monthly, starting on this date. So 1 month from that then is 1 month from then is this, 1 month from then is this, 1 month from then is this, 1 month from there is this. And then just as another example, we could change it over to weeks, which should be changing this frequency to W, and running that. So you can see you get weekly values starting on the 1st. And notice that the weekday is always the same, because that makes sense. It's just 1 week from that day. It's always going to be on the same weekday. For doing hours and minutes, yeah, that's true. So our date doesn't start that way. So it should be like, it should start like something like this. That's true. Our date should be something like this in order to use hours and minutes. But we're just working at like a daily level as a simple example. Biweekly, I think you could do, you could customize it. I think there may be a parameter here to do, uh, um, starting, ending, frequency. I think there is, like, maybe a B is biweekly. I think it might. Yeah, I think it might have. I think it might have biweekly. Have to look that up though. All right. Let me ask you guys though, does it make sense how we're creating this is weekend column? Does that make sense how we're creating this is weekend column, which is coming from the day of the week? And initially, like you can either do it this way, or you can do the integer division by 5 and check and see if that's 1. The quotient is 1. Okay. Oh, it's biweekly. Yeah, it is 2W. Makes sense. Every other week. Yeah, biweekly. Let me stick with the daily for now. All right. Okay. So what I want to show you next is the ability to add and subtract periods of time from an existing date. So one of the advantages to having things in a datetime object. So here's an example where we convert the existing dates over to a datetime object. And remember, if they're already a datetime object, it's not really going to matter if we do the conversion. It's not going to produce an error, but it's not really going to do anything. It's already a datetime object, but supposing we were to convert those over, this is now guaranteed to be a datetime object. One of the things we could do is subtract or add, which does some type of shift of periods of time. And the way you do that is you use a Pandas time delta object. So we use time delta objects to do date arithmetic. So basically shifting of dates. So for example, this is going to take our current dates and subtract 1 day. So time delta gives you an object representation of a period of time. So this is shifting our dates back by 1 day. And how do I know it's 1 day? It's because the argument in the time delta corresponds to those frequencies. Basically, like how much time am I talking about? Is it 1 day? Is it 1 week? Is it 1 month? Is it 1 quarter? Is it bi-weekly? So is it 2 weeks? How much time am I shifting off of these dates? So what this does is this is going to take every single date and subtract 1 day. That's all that means. The time delta is kind of a representation of 1 day being subtracted from the date. Now, do we have to subtract? No, we can also add to shift forward. So this is going to be, the first one is a shifting backwards. This is now a shifting forwards of our dates by 1 day. So this adds a period of 1 day to every date. Now, why is that useful? Sometimes when we're manipulating our data, we may want to shift the dates around to do some type of manipulation to the data. So we may need to shift our dates forward by a week. We may need to shift backwards by a week, or by a day, or by an hour, or by a minute. So if we ever need to do any of that plus or minus of a time period, we're going to use a time delta object to do that shifting forward or backward. So you can see what the result of doing this is. We have our existing dates from our date column, and the previous date goes back 1 day. So you can see what the new dates are for that column. They're automatically computed for you. That's the really nice thing about datetime objects. It's taking our existing dates, subtracting 1 day. So we get a new date object, which represents that shift back by 1 day. So we have 12/31. Here we're taking this, we're shifting it back by 1 day, which lands us on the 1st. Here we're on the 3rd, shifting back 1 day. It's going to give us a 2nd, and so on and so on and so on. So that time delta really represents like how much time do we want to shift by. Same with going forward. You can see what the next date is. If we take the existing date and we shift forward by 1 day, we get the 2nd. If we're on the second and we shift forward by a day, we get the third, and on and on and on. And so, when we're at the end of the month and we shift forward by a day, Pandas will handle going to the next month and shifting forward into, like, if we're on January 31st and we shift forward one day, it will go to February 1st of the next month. Right. And you can even see this, like when we shifted back one day, it actually went to the previous year. So it did a good job of recognizing, okay, we're on January 1st, we're on New Year's, want to shift back one day. So we need to go back to 12/31 of the previous year. So it's doing that math for you as long as you shift by a time delta. It will do the math for you of what the new date should be. Okay. Any questions on these time deltas? Do those kind of make sense? Time delta represents a period of time, and you can manipulate existing dates by adding or subtracting time deltas to existing datetime objects. That's the thing to be wary of, is if you add or subtract time deltas, it's only going to work with existing datetime objects. It's not going to work on strings. Okay. All right. So here's an example where we have a couple more time delta examples. This creates a frequency. This creates a date range that starts at January 1st, but has 10 hours of time. So it's going to generate 10 hourly intervals starting on the 1st, which assumes that it's at 000 of the 1st, goes forward 1 hour 10 times. That's the date range. And we can shift forward that time by 3 days, or however, we can shift forward by hours. Like if we replace this with hours equals 3, we can shift everything forward by 3 hours. So time deltas you can just pass in different arguments here to represent different periods of time, like weeks, months, hours, years, quarters, those kind of things. So here's an example where we take all of those existing dates and we actually shift them forward by kind of an arbitrary amount here, which is shifting forward by 2 weeks, 3 days, and 12 hours. So you can see the starting date is the first. The starting date is the first, and then we shift forward by 2 weeks and 3 days and 12 hours. So we go 2 weeks is 14 plus another 3 plus another 12 hours. So that brings you into the 18th at 12. And this was the first hour. This shifts forward to the 18th at 1300, on and on and on. Okay. Any questions on this example? Good. Okay. So hopefully we're comfortable with time delta. How many iterations it takes? We only have to do, so we are adding to the entire column all at once. So it doesn't do any iteration. It just does it in one execution. So really just one execution to add all the time delta to all of those dates. Because we had 5 rows, right? We had 5 initial dates. So we started out with 5 dates. This is taking the entire date column, which has 5 entries, and adding this amount of time to it. Does that make sense? Like we had a column that had 5 entries, 5 dates. We produced that up here. We produced that. Actually, I realized I didn't run this. So if I rerun this, this should be the proper, yeah, there we go. It should print these does that make so sorry, now it has the proper number because we had 10 periods. This data is based off of running this cell first. That should be proper now. What is range 1020? So range, do you remember what range means? Range is a list. So a list of values that start at 10, go to 20, but doesn't include 20. And it increments by 1. So this is just a list of numbers 10 to 20. And this is a list of numbers 0 to 9. Does that make sense? That's the range function in Python, which creates a range of numbers with a starting, you just give it a starting and a stopping point. If you only have one thing, this is the same as having a starting point of 0. It's not being used in this yet. It's just here as additional data columns. These are just additional data columns that are in the data frame. It's not really being used with the dates. It's not really being used with the dates yet in this example. It's just mimicking if we had extra columns of data. But yeah, no, it's good questions. Good questions. Yeah, well, because there's 10 rows, but yeah, if that's what you mean, yes, there's 10 rows, so it'll do 10 shifting of dates by this amount. Yeah. Okay. Any other questions about the time delta? This is an example of time delta. We're using a time delta to shift forward. It's the shift forward time. So if you have a data frame, or you're working with dates, it can be helpful to generate a new column that is like a 1 week ahead of the dates, so that like maybe you can do filtering on a different collection of dates that is shifted forward in time. Okay, so it's useful for generating new dates that are shifted from your original dates. That's the purpose, is to generate new dates from the existing dates, which comes up in data analysis. It comes up in plotting. It comes up in a lot of scenarios. Yeah, I can go back. You can subtract. If you subtract, it goes backwards, right? Yeah, you can go backwards. You just have to subtract, right? Because subtract will take the existing date and go back by 2 weeks, 3 days, 12 hours. If you subtract. If you add, it goes forward, right? By that amount of time in the time delta. So I think we had an example earlier of going backwards, like here. This goes back 1 day. This goes forward 1 day. Yeah, so to go back, you just have to subtract a time delta. Okay. Now, I want to show you something really important with time series data that's actually going to show up quite a bit when we get into doing more analysis and doing some plotting of time data that is indexed by time. And thing we're going to take a look at is something called resampling time series data. So what this means is that the dates can be at whatever interval that they are. So I can have dates that are at the day level, month level, year level. I could have hourly dates. I could have time that's at the seconds, and I can have a bunch of different rows that represent data at the second level, day level, whatever it is, right? So resampling is the process of aggregating those times to be at different intervals than what I start with. So let's say I have data that is at the hourly level. So I have a record of like a temperature. Let's say I have a record of a temperature that is, and then I have the date, I have it recorded at every hour. So I have it on 01, 01, 01 on that day, but I have it at 0, 0, 0, 0, 0, 1, or sorry, 0, 0, 0, 0. So I have it at the very beginning of the day, and I have the temperature as let's say 40 degrees Fahrenheit. So I have 40 degrees, let's say. Okay, and then I have another recording at the next hour. So I have a data point that is at the same day. So 0, 1, 0, 1, 0, 1. But then I have it at the next hour, which would be 0, 1, 0, 0, 0, 0. So let's say I had a record here, and it's now 41 degrees, let's say. Okay, so and on and on and on. So I have a bunch of data that's at the hourly level. What we can do is we can actually resample this to get an aggregation at a different level. So let's say like I don't really care about what the temperature is every hour. I care what the temperature is across this entire day. So I only care about it across what is it on average across this whole day. So I could boil down all of these dates into a single record for that day. So I could just have an entry for 0101 2001, let's say, and I have now an aggregated temperature here of it's like 53.7, let's say. So now and then I go and so then I have a bunch of data that's at the hourly level for the second, but I can aggregate that down to an average for that day, which is maybe 54.2. So something like that. So this process is called resample or resampling, which changes the frequency, basically aggregates the data at a different frequency than what it is recorded at. So let me give you an example of that. Let's say I had a bunch of values that are recorded for each day, and I wanted to get an aggregation. Let's say I wanted to get an aggregation in our data frame. So you see how I have a bunch of different values that are at an hourly level currently for this data frame. What I'm going to do is pick all of my numerical columns. That's I forgot to mention this. Let me come back to this in a moment. This picks all of our numerical columns. So basically exclude any strings, exclude any objects. Let's just pick all of our integers or float columns that we have. And what we're going to do is we're going to resample those at a daily frequency. So I'm basically going to roll all that data up into an aggregate, and which aggregation am I going to choose? You can put that at the end. So you can take a maximum, you could take an average, you could take a median, you could take a sum. Any of those Pandas functions that we've seen that do a statistical operation, we can do a count, we could do a total, which is what we're doing here, the sum. We can do a mean, we can do a max, we can do a min. But what this is doing is aggregating that data at the day level. So notice that we take all of this data, which has 10 different entries for these columns. Let's print out our data frame so far. So our data frame has existing dates, it has these existing values, and it has these time delta shifted dates. But what we're going to do is basically aggregate all of this data to be resampled at the day level. So it's going to produce a single data point for this day. Does that make sense what it's doing? We're producing a single data point for the day. And we have to say, how are we doing that? How are we aggregating? Well, we're really taking a total. We're taking a sum. So we're actually going to sum all of these guys that correspond to that day. We're going to sum all of these guys that correspond to that day and get a total for that day. But, we don't have to use a sum. We could do a min or a max or an average. So we can, of course, replace this with mean. We could replace it with the maximum across that day. We could replace it with the minimum across that day. But here we're using the total across that day. And how do I know it's resampled at the day level? It is because this is the frequency of our sampling. So we are producing a data point at the day level, knowing that we already have values at an hourly level. We're aggregating them to the day level, and we're aggregating them via this function, the sum. So see how our other two columns produce totals of 45 and 145. Yeah, you can. So yes, what you would do is you have to do it in two steps. You basically would generate the resample data frame, which is just this, and then you can do an apply. So actually that might be worth taking a look at, is then you kind of do like an apply, and then you can do a lambda or an apply your function here. Does that make sense? Like you can do an apply to basically apply your function to the resampled rows that you get, to like the aggregated rows. Yeah, you can apply a function to it. But the pretty typical thing is to do some type of aggregation to it, like a statistical function. In this case, we're doing sum to get the total for each day. Something I should mention is that doing resample assumes that the dates are actually the index of the data frame. So that's a big assumption. So you can only resample if the dates are the index of the data frame. So one of the things that we do first is we actually set the index to be the date column. Now that's important because if you take a look at the DF at that stage, once you resample it, if we were to print the DF before we do the resampling, oh, because I already ran this one, so I have to redo it. Let me redo it. Sorry. Rerun this. Rerun this. Rerun this. Okay, so if you take a look at our dates, or our data frame, so what we did is we set the index to be the date. So remember, if we don't do that, the default index is, see how when I printed it out before, the default index is the positional index of the rows. That's the default behavior when you create a data frame, right? It just gives us the index as 0, 1, 2, 3. That's the default. But we can overwrite that by doing this set index function, and we purposely want to permanently, that's what the in place equals true does, right? Permanently reset the index to be the date column. So now when we print out this data frame, you can see that the index is actually the date now. That is the index. There's no positional index anymore. The date is actually our index. And once the date is the index, then we can do resample. So resample assumes your data has the index as some type of datetime object. So it's not going to work if you just have if you have the default positional index. Resample won't work. Yeah, Roberto, let me explain that. Well, I'll explain that in a second. Do we see what I'm saying by resetting the index? Where this is a way to set the index on a data frame to something that we like an existing column. So saying, okay, set the index to the date column. That's what I want the new index to be, and I want to do that permanently, which is why I have the in place equals true here. So we let me write that down as a comment. We permanently in place equals true. Set the index to be the date column. Permanently do that so that resample will work. If in place equals false, then remember it doesn't do it permanently. It gives you a temporary copy of the result. So you would have to do something like df temp is this, and then we would resample df temp, because this will, like, if this is false, then it doesn't permanently affect the underlying data frame. It only gives us like a view of the result. So that's why usually, yeah, we don't need to do this. If we just put in place is true, that will permanently alter it. And then we can just operate directly on the regular data frame. Yeah, you could set the index back. So once you're done doing that, you can reset the index. Let me show you how to do that. So you can reset the index to the default by using this, which is you can do df.reset index, and then you want to do in place equals true. Okay. So you want to do in place equals true. Does that make sense? This will reset the index to be the default. It'll just reset it back to the default. That's how you set it back to the number. Okay, let me go back and explain because it's a good question. What does this mean? So the select D types is a way in Pandas. Select D types is a way to select data. So one way to select data is to use the brackets, right? And we can put in filters in the brackets. We can have many different conditions in there that will pick out the rows that we want to return when we're selecting data. But select D types will select rows, or it will select data from the data frame according to what we include or exclude. So include, if we have an include argument, that means I want to return all data that is numerical in type. That's what select D types does. So this will return all data that is a numerical data type. So what does numerical mean? Think of int or float, right? Some type of numerical data type. So the reason we do that is because resample is not going to be able to aggregate things that are strings or other types of objects, right? Does that make sense? Like it's not going to make sense to aggregate a bunch of data at the hourly level down to a day when we have something that's like a zip code or something like an address. It's like, how do I take the average of an address? Can't really do that. So what this does is it filters the data to only include numerical values, right? Only include numerical values when we do this operation. So this is like a select D types is like a filter. It's like a shorthand. It's like a shorthand. Filters to only columns with numerical data types. Does that make sense? Any questions on that? This returns a portion of our data frame that has only the columns that are numerical data types. So if I were to read this out loud, and this might be helpful, is like if I read this out loud, what this is doing is saying, okay, take our data frame, filter our data to only the numerical columns, aggregate it at the daily level, and aggregate with a sum. That's how you read that, right? That's how you read that from left to right. Take our data frame, filter out only the numerical columns, aggregate it at the daily level with a sum. The date isn't a string. We've changed it to a datetime object. We've changed it. It's a datetime object. It's not a string. Yeah, that's what it's doing. Aggregate all columns which have numeric data. No, so that's the thing is the datetime object has been put as the index. It's not a column anymore. So that's why this code is so crucial to set the date, which was originally just another column, as the index. So it's not going to get aggregated because it's the index. We set it as the index on purpose to facilitate the resampling. And let me make a comment here that the D is for daily aggregation. Obviously, we could do yearly, we could do weekly, we could do quarterly, we could do monthly. We can do different types of frequencies there. Basically, the same frequencies that we could do earlier in the date range, we could do here in the resample. So see how the main takeaway to this is we go from data that looks like this at an hourly level to a single value for the day. We go down to a single value for the day for those numerical results. Now, that is extremely powerful. Like that resampling operation is extremely powerful to be able to aggregate time-based data at different frequencies. Really useful, right? For summarizing, for generating reports like quarterly reports or like yearly summaries. Like it's extremely useful function. Categorical data is, data that belongs to usually a distinct number of categories or discrete number of possible values that it can be. So for example, we may have data that is usually this would be like in the form of a string, and there's only a certain number of possible strings that data can be. So like, for instance, what if we had a column that had values that were like this, where the entries in that column were only things like low, medium, high, and those are the only three values we saw. That is definitely a good example of a categorical column or categorical data. Because in that setup we only have three discrete possibilities, the data points are only going to be these three possible categories, which are low, medium, and high. Pandas does support allowing you to convert objects into categorical data into a categorical data type. And the reason you may want to do that is to have a sense of ordering or be able to sort based on those categories. So for instance, we can take the values that are like low, medium, high, and we can generate a categorical data from that, which is going to be basically a series which has a categorical data type. So this goes from a string, and the data is now going to be categorical, and we can tell it what categories exist. So in this case, only low, medium, and high exist. And we can say that there is a natural ordering, and the ordering follows the order that's inside of the categories list. So low is first, then medium, and then high. And it goes from least to greatest. So low is the least value, medium is the next, high is the highest categorical value. So all of our data now can be converted into a categorical series, which can be useful for sorting it, because now instead of sorting it alphabetically, which we may not want, because if we were to sort this, it would just be treated alphabetically as strings. Now, if we were to sort this, it's going to be sorted according to these rankings of the category, low, medium, high. So putting things in a categorical type often has a benefit of allowing us to then have some natural order amongst the categories, which can help us whenever we are doing analysis or sorting that data, or grouping that data and slicing and dicing it. Okay, so let me run this. So what I want you to see is now the categorical variable is now it now is data that looks like this, and has 3 categories ordered from low, medium to high. So it goes from regular, the data starts out as just a list of strings, and it turns into basically a series that then has categorical data. So pretty useful. What we can do with categories as well is we can count how many unique values there are from each category. Now, we saw this, I think on Monday I showed us this, but showing you guys this again is you can take categorical data like we have here, or you can take data that's just regular strings. It actually doesn't matter if it's in categorical format or not. We can take data that's just regular strings, and we can compute the value counts on that column, which generates the number of occurrences of each unique discrete category. So in this case, we have data that only belongs to A, B, and C, but we can see C only shows up once, which is what this count is. B shows up twice, which is here and here. So you can see what that count is. And then A shows up the most, which is 3 times. You can see that's what that count is. Remember, you can pass in a normalize equals true argument here to create percentages. So half the data, this is signaling that half the data is category A, which makes sense. There's 6 entries and 3 of them are A. And then 1/3 of them are B, because 2 out of the 6 are B, and then 1 out of the 6 is C. So you can produce percentages. The default behavior is just to give you the total count of how many are each category. Now, this is extremely useful. Like when we get into modeling, this is going to be extremely useful, because often we're going to care about our data from the perspective of like, how many examples do I have of things that are like pictures that are cancer or not cancer. And maybe it's we run this value counts function on it, on the cancer column, and we see that most of the data is actually not cancer, which would be a pretty typical scenario. And then some of it, like some percentage of it is, but we can see that the majority of it is not. So this is a good way to kind of figure out what those relative amounts are between the members of the categories. So this looks like, there's mostly it's A, but there's a few examples of B and 1 example of C in this data. So value count is an extremely useful function on a column. Usually you run this on 1 column to kind of see what the categories are. So not only does it give you the counts, but it also will give you the unique categories within that column. Here we have an A, B, and C. We know that because we can see it. But if you imagine you loaded in this huge spreadsheet, you may not know all the discrete values that are in a column. You may not know that right away, but if you run value counts, you can actually get those. And not only that, you can get a frequency of how often those show up in that column. So pretty useful. Okay. Any questions about value counts? Okay. Yeah, so normalize equals false is the default behavior. That's just going to give you the raw count of each category. So this tells us that there's 3 A's, there's 2 B's, and there's 1 C. So normalize is false. Normalize equals false is the default. So you don't even really need to put it in there. It's the default. And this means that we get raw counts of each category. So if we set it to true, we get percentages. So if we set it to true, we get percentages. So see how it changes to where A is now 50% of the data. So this means that of this column, 50% of the entries are A. 33% of them are B, which makes sense because 2 out of the 6 are B. And then 0.1677, that's the ratio of C. So there we have 1 out of the 6 examples are C. No, Tim, value counts is really a function on a series. So you should only be doing it on a single column because remember, what is a column? It is a series. So really should only be doing it on a single column at a time. Certainly you can do it on more than one column, but you're only accessing a column at a time and then doing it. Yeah. It's because it's a function on a series of categorical data. And that's the use case anyway, is typically the use case is to zoom in on one particular column or maybe a couple and do the value counts on those, the columns of interest. All right, cool. So value counts, we'll see again. We're going to use this quite a bit here and there as we progress. This will be a really useful one when we get into modeling. Okay, really useful function for us as we will see later down the road. Let's talk about another really useful thing for modeling, which is to convert data from categorical into numerical. Now, this is an extremely, I really want us to understand this because this is something that is going to be extremely useful as we get into modeling, is machine learning models are going to not really be able to make use of these categories as they are, because it's not going to know how to work with strings out of the box, right? So because they're mathematical models, they're going to struggle to make sense of, well, what is an A string? What is a B? What is a C? What is a D? It's not really going to know what those are. So what we want to do is convert those into a numerical collection of data. And the way that we do that is we actually generate new columns which indicate the presence of that category or the absence of that category. Let me give you an example. So if we have this original data here, so let's just say we had a column called data and it took on these values like we see here. We have an A, we have a B, we have an A, we have a C, we have a B, we have an A. Okay, let's say we had that. Now, what we are going to do to convert this to numerical is generate some new columns that indicate the presence of each one of those discrete categories. So, for instance, we're going to create a new column that is basically going to be do we have data underscore A? Do we have that value? Do we have data underscore B? Do we have B? Data underscore C? Do we have C? Now, in this first row, do we have A? Do we have the presence of A? And we take a look at it and we see that, yes, this entry is A. So I should have a 1 here and a 0 here and a 0 here because I don't have a B, I don't have a C, but I do have A. So this is going to indicate the presence of A. And this is going to indicate the presence of B, as you can imagine. And likewise, this is going to indicate the presence of C. So in this first entry, I have A in our data. That's the first entry in our data. So I have presence of A. So I marked down a 1 for that column and a 0 for presence of B and a 0 for presence of C. Let me ask you guys, what do you think presence of A column is going to be for this next entry? So if I look at this entry, what's going to be the presence of A? It's going to be 0. Yes, perfect. You guys are right on top of that. This is going to be 0. Now, what is going to be presence of B? And how about presence of C? Perfect. So presence of C would be 0. Perfect. So now, does this process make sense how we are converting? So look at what we're doing. We're converting our categorical data into numerical data because now this is all integers, which is great from a model perspective. That's fantastic. I actually have numerical data I can work with. So that's fantastic. Now, what was the cost of doing that? I have 3 new columns. It's not for free. There's a cost to doing that. And you are going to always have that scenario where when you are converting your data over from categorical to numerical, you are going to get as many columns as you have discrete categories for your data. So this data here only has 3 possibilities. So I need to make 3 new columns that represent the presence of those 3 categories. Does that make sense? The presence of those 3 categories. So I have 3 new columns. Yeah, Roberto, I'm gonna give you a real world use case in a moment. I'll give you one in a moment. Let me explain again, because this is incredibly important to understand because we are going to do this procedure all the time. By the way, this procedure has a very special name in machine learning, which is called, it's this name called one hot encoding. So one hot encoding is the name of this process of turning categorical data into numerical data. That's called encoding, one hot encoding. Why is it called one hot encoding? Because you're using 1s and 0s to indicate the presence or absence of categorical data. Okay, one hot encoding is this process. turning categorical data into numerical data. That's what we're doing. And that's just the terminology. one hot is like hot is like that. It indicates presence. Like it's there. You can feel it. It's hot. It's presence. That's all it means. Yeah, it's live. It's active. That's the category that's active. You can think of it like that. Yeah, it's hot versus cold. It's like cold is kind of the absence of temperature. Okay, so let me walk through that again because it's really important that we walk through this and understand it. So this data example has a column called category. Okay, it has a column called category, which only has 3 discrete values. It can only be A, B, or C. And you can see the data here. The first entry is A, second entry is B, third entry is A, fourth entry is C, fifth entry is B, and last entry is A. That's what I have here with this data, right? I have that data there listed in a column. So for any time we have categorical data listed in a column and we're going to do modeling with it, we want to do one-hot encoding. We have to do one-hot encoding. The model will not be able to make use of the string. We have to do one-hot encoding. So we have to turn this into numerical data. So the trick to doing that is to generate 3 new columns. These columns represent the presence of those unique categories. So we have a column for presence of A, we have a column for presence of B, and we have a column for presence of C. Let me pause there. Does that make sense so far of the setup? So in order to convert our data to numerical, I'm saying let's create 3 new columns which indicate whether or not we have one of those categories, A, B, or C. The presence of A, presence of B, presence of C. That's all I'm saying is we're going to set up 3 new columns to represent this one column of data. We're going to generate 3 new columns called presence of A, presence of B, presence of C. And the way we're going to fill out those columns is we're going to look at our data. We're going to look at our data and we're going to say, what is the value of that data? It's an A. So therefore, presence of A should have a 1 because that means, yes, we have presence of A in that first entry, in that first row. Presence of B, no. We actually have absence of B. So we should have a 0 there. There is no presence of B. There's 0 presence of B. And there's no presence of C. So that also should be 0. So we have converted A into a 3 different columns, presence of A, presence of B, presence of C, where there's a 1 in the presence of A spot and a 0 in the other 2 spots. Okay. And we go down to our next entry. We look at B and we say, okay, how about B? It does not have presence of A, so that should be 0. It does have presence of B, so that should have a 1. And it does not have presence of C, so that should be a 0. So we have this, we have 0, then we have 1, and then we have 0 for that second row. If you have, so you're thinking correctly that if we have 10 discrete categories, we have to generate 10 new columns. It's going to be 10 new columns that we have to create to indicate presence of those 10 categories. Yes, they have to be 10 new. And we're going to have a pandas function that's going to do that for us. So if you're asking, is there a shortcut? Pandas will do it for us. Yeah, Pandas will do this for us. I'll show us the function. Luckily, Pandas does this for us. We don't have to do it manually. I'm just trying to show you the procedure of one-hot encoding and what it does so we understand it. Okay. Should it be a categorical variable or any data? So technically you can one-hot encode any data. Now, do you think it makes sense to one-hot encode numerical data? Do you think it makes sense to do that? Like, would we want to do presence of 2.3, presence of 3.5, presence of 4.7? Like, would we want to do that if we have a lot of, because what's the issue with floating point numbers? What can they be? What can floating point numbers be in general? Like, what's their range? Or even integers for that matter. Like, what's their range? Yeah, so the issue is that, yes, floating point values can take on any number. There's an infinite possibility of what those values could be. So we don't want to end up doing presence of 2.3 because we can have presence of 3.67521, right? We end up having to do an unlimited number of new columns to represent each one of those floating point values. It doesn't scale. So you really should only be doing one-hot encoding for categorical data. You should only be doing one-hot encoding for categorical data, like strings that have discrete number of possibilities. Does that make sense? Like that's when we want to use this, is for discrete number of options, which is what categorical data has. Okay. Um, yeah, I saw a question. 1 or 0 are constant with these numbers, no matter how many yeah. And does it make sense that only one of them is going to be a 1, and because you're only going to have presence of one of them in every row, and then every other one has to be 0. So you're only ever going to have a 1 once, and then every other entry has to be 0. That's what it has to be, because you're only going to have presence in one place. You're only going to have presence of one of these categories, and then every other entry is going to be 0. Is there a limit? And basically until you run out of memory, that's the only limit. So technically Pandas doesn't enforce a limit. Basically you can, if your data frame grows too big, like if you have too many unique values and your data frame grows too big, you are injecting too many new columns, that's when you would hit the limit, like the memory limit of the data frame of your machine. But like technically there's no limit. Okay. So let me do two things. Let me give you a real world example. Okay. Let me give you a real world example, and then let me show you the Pandas function that will do this for us, the one-hot encoding. Okay. So I'm going to give you a real world example first. So in the real world, there are a lot of categorical features that are, or I should say variables that are going to be useful for predicting something. So, for example, there's a lot of things that are discrete when it comes to recommendations. So think about something like Netflix. The genre of a movie is a discrete categorical variable, isn't it? So a movie is going to be something like horror, comedy, adventure, action, thriller, right? It's going to be one of those strings. So if we were to build a model off of that to do a recommendation, which is what they do, they generate recommendation models to recommend movies to you. the models are not going to understand those strings, but they are going to understand the numbers, which we can do the presence features like in the one-hot encoding. So a realistic example is to take like a movie genre that could be a unique category like comedy, action, romance, whatever it is, and convert that over to a one hot encoded column so that a model can use that for recommendation. So movie genre, and then we could have genre. We could have a new column that's genre comedy, genre action, and then genre romance. And then we have, but these are like our presence. These are like our presence features, right? Or I keep saying the word feature, which I haven't taught you guys what feature means yet. But let's say column. These are presence columns. So genre comedy, there's going to be a 1 here, 0 here, 0 here. Action, there's going to be a 0 here, 1 here, 0 here. And romance, 0 here, 0 here, 1 here. So now a model is going to be able to work with these numbers. So a model is going to like a recommendation system is going to like that data a lot more than it likes this. It's not going to like strings. And we're going to see that when we get into machine learning. When we actually build our own recommendation systems, we'll see why. The numbers are so much more useful to the model than strings. So that's a real world example. And that's not just for recommendation, it's for a lot of different predictive models. A lot of predictive models care more about the numerical data rather than strings. So it's in our best interest to convert any categorical data into numerical data prior to building a model. It's really important to do that. So we haven't learned that yet. We haven't learned how to model or do anything like that yet, but we will. Give us some time, we will. Can Pandas use drive space as memory like R? What do you mean by like hard disk space? It can cache things, yes. Yes, it can cache things to the disk. Yes. So you will add those features to each. Yes, we will add those to. We will replace the strings with that and basically get rid of the strings. We will just have this and completely drop this because it represents the same data. We could put the values in an array, run a loop, and then use that to update the counter of each genre, like genre comedy. Yeah, like we could get a count, but a count doesn't tell us presence of that data in a row. Does that make sense? Like it's important to know that this row is comedy. This row is action. This row is romance, which is why we use a 0 or a 1. Right? It's because we're using it as a variable like presence of comedy, presence of action, presence of romance. We use a 0 or 1 for that. So you're thinking more about like counting the total number that we have, which may be useful for analysis. But I'm thinking more about it from identification, right? Yes, exactly. Very good, very good. Okay. Before I show you the Pandas example of converting things into the one-hot encoding, any other questions about the mechanics of it? Conceptually, does one-hot encoding make sense to us? Like what it's doing? Any questions on it? I'm going to show us the Pandas example of how we can do it in the code in a moment. Okay, very good. Okay, so the way that we can do this in Pandas automatically to do the one-hot encoding is a function called getDummies. So in Pandas, there's a function called pd.getDummies, and all we have to do, all we have to do is uh, pass in this column of your numerical data. And actually, what getDummies can do, getDummies is a very flexible function. You can pass in more than one column at a time. So you can pass in multiple categorical columns and it will convert all of them into their one-hot encodings, which is pretty useful. But in this case, we only have one column. So we're just going to pass in this category column. And now you can optionally, you don't have to do this, but you can specify a prefix, which is the prefix is for the new generated column name. So that the prefix is the new generated column name during the encoding. So when we do the encoding, we could name this whatever we want. We can name it presence. We can name it. Typically, the default behavior is just to name it the column. So the prefix is just the column name. In this case, it is category. So, for example, this means that our new columns are going to be category prefix and then the whatever the category value is. So category A, category B, etc. So whatever the discrete options are for that column, we can have the prefix. Now, one other important part of this is by default, the getDummies is going to use Booleans. It's going to use true or false to indicate the presence or absence. But we want to use numbers like 1 or 0. So the way that you do that is you change the D type to be an integer. So we want it to be integer result, which will change the true or false into 1 or 0. So we want to purposely end up with numerical data, right? We want to take our categories and end up with numerical data. So when we run this, you can see what we get. We get the, now this should make some sense to us, this result, because what we're getting here is the first entry is an A. So we get presence of A, 0 presence of B, 0 presence of C. That makes sense for the first entry. If you go to the next entry, it's a B. So we should have a 1 here in the category B column, which indicates presence of B. And so then the next entry is A. We get presence of A. That makes sense. The next one is a C. So we get presence of C there. The next one is a B. We get presence of B. The next one is an A. We get presence of A. So getDummies does the one-hot encoding for us. And the only thing we generally want to remember is to put in this data type of integer in here, which will ensure that the results end up as 1s and 0s, which is what we want. We want to convert those strings into numerical values. How it is used. I was kind of describing how it's used. I mean, so let me ask you this, like from a mathematical perspective, if we're building a model, how does a model that does mathematical equations, excuse me, how does a mathematical equation know what to do with a string? This is the fundamental issue of why we have to do this, is it's not going to know what inherently to do with a string. It doesn't know what to do with B. It doesn't know what to do with A. It doesn't know what to do with C. It doesn't know what to do with B. right? There's no way to really incorporate that as a number into a model. It's not really a way currently. Now, do we think that we can incorporate ones and zeros? Yes, we should be able to incorporate ones and zeros. So it's to our benefit to turn this data into this data. This is the same data. It's the same data. It's just represented differently, but it's the same data, right? It really represents the same data, just in a different format. One is one hot encoded and one is the original categories. Models are not going to be able to use this format. Models are not going to be able to work with that. Models can't work with these strings. But it's not like now they can't work with the strings, but it's not like we should ignore it. It's still useful information to know that, okay, this data is category A, this next row is category B, this next row is category A. Let me give you an example. In the house prices data set, do you remember how we had data that was number of bedrooms, number of bathrooms, and square footage? Those were all numerical. There were pretty useful categorical columns as well. So there were things like the neighborhood or things like the zip code, things like the address that are important categorical features as well that give some meaning to the house, like what state it's in. The state is a discrete categorical feature that may be really useful to tell what the average, like the price is going to change based on the state. So that is a useful variable to know, but we can't use the state as a string, but we can use presence or absence as ones and zeros. So that's where it's going to be used, is in our modeling. We haven't learned modeling yet, but this is where this is going to be an incredibly useful Pandas function. Get dummies, right? Get dummies is going to be an incredibly useful Pandas function to do one hot encoding. Okay. Any questions on the get dummies function? By the way, the get dummies returns a data frame. You can see that here, that we generate our new columns, category A, category B, category C. Those all get generated based on this input categorical data. So it spits out those. And of course, we're going to get as many columns as we have discrete values for this data. So if we had 10 different values in here, we're going to get 10 different columns that get produced. Any questions on that? Okay. All right. So as an alternative, something that we can also do that is going to be useful when we are doing modeling, and we want to, instead of doing presence or absence, maybe we want to assign each unique category with a numerical label that increments. So for instance, we could have a mapping here that says, well, A should be assigned to 0, B should be assigned to a label of 1, and C should be assigned a label of C. Oh, poll came up. Okay, thank you. C should be assigned a label of 2, let's say. So we can encode this way, which will also change over those strings into numbers by assigning a label to every unique category. So what we're going to do is assign A to 0, assign B to 1, assign C to 2, and on and on and on. Like if we had a D, we would assign that to 3. If we had an E, we would assign that to 4, and on and on and on. So we can do this, and then it instantly maps our data to a new column that would be like 0, 1, 0. It's exactly this data here that you see, right? All of those values get mapped into their labels. And so this is called label encoding versus one-hot encoding. This is just a slightly different way of doing it. When we do modeling, we'll always do one-hot encoding. Label encoding is useful when we want to assign a label to a category for the thing that we are trying to predict, but not for the input variables. The input variables, we usually will always do one-hot encoding. But for the independent variable that we are trying to predict, if it happens to be a category, I'll give you an example. So for like, let's say we were trying to predict fraud, and we had we had fraud. We had a column called label, and it was either a string that was fraud, not fraud, fraud, not fraud, and on and on and on. So there's only two possibilities. We could label encode this to have a new label that would be like fraud is a 1 and not fraud is a 0. Fraud is a 1, not fraud is a 0, and on and on and on. So label encoding is useful for the thing that we're trying to predict. We can assign a label to it that is numerical, because again, a model is going to struggle to predict a string. A model is not going to be able to predict a string, but it can predict a number. It can generate a number. So it makes a lot more sense to convert the thing we are trying to predict over to a number versus keeping it as a string, like fraud or not fraud, or cancer, not cancer, cat versus dog. We could assign a label of 0 or a 1, or maybe if there were 10 categories of animals, like cat, dog, leopard, panther, cheetah, wolf, we could assign like 0, 1, 2, 3, 4, 5. Like we could assign a bunch of numbers to those for the thing we're trying to predict. Okay, so one-hot encoding will be used for modeling for our basically our variables that go into the model, and label encoding will be used to convert what we are trying to predict, right? The actual outcome label over to something numerical, so the model can have an example of how to predict that, like what number should it result in. Does that make sense? Any questions on that idea? I'll show us how to do it in the code. It's not hard to do. Which part? Which part, Roberto? It is, but if it's mathematical, how can it generate a string? That's the issue. It's like if I give you an equation and I put numbers in, how am I going to get a string out? Do you see the issue there? If I'm putting numbers in, how am I going to get a string out of it? Yes, exactly, JD. So one-hot encoding is used for inputs. Label encoding is used for outputs because we need to convert those strings into numbers. Yes. Yeah, it is. It is, Roberto. So label encoding is also generating numbers, the same as one-hot encoding, but it's for a different purpose. One-hot encoding is specifically to say do I have presence of this variable or do I not? Right? But the label encoding is just assigning a label to something to directly convert it over as a mapping. So think of the fraud, not fraud example. I'm going to relabel that to a 1 and a 0. It's not about presence or absence. It's about relabeling it into a number so that when I'm predicting something, I have a number to go off of as an output. Yes, they go off. So the default behavior is to assign them to their index. Yes. Yeah, exactly. But high-priced house from a mathematical model perspective is likely going to be mapped to a 2, and medium would be a 1, and low would be a 0. Yes, in label encoding, you can have multiple values. So look at this example here. It has A is mapped to 0, B is mapped to 1, and C is mapped to 2. So yeah, you can have more than 0 and 1. With label encoding, you can have as many as you have possibilities. So if you're predicting 10 different animals, you're going to have 0 through 9. Like 0 could be dog, 1 could be cat, 2 could be fox, 3 could be giraffe. Do you see what I'm saying? So yeah, you can absolutely have more than 0 and 1 in label encoding. You're never going to have that in one hot encoding. Never going to have that in one. In one hot encoding, you're only going to have 0 and 1, which indicates presence or absence, which is important from an input perspective. This label encoding is only useful for describing the outputs of a model, because we generally want those to be a number, and we don't want it to be like presence or absence. We want it to be a single value, right? We want it to be a single value. So fraud would be mapped to 1, not fraud could be mapped to 0. Or like in the case of animals, cat could be mapped to 0, dog mapped to 1, fox mapped to 2, turtle mapped to 3, on and on and on. Okay. Let me show you how you can get the labels. It's actually not that hard to do. There's actually multiple ways to do it. We're going to see a different way to do it down the road that involves the Scikit-learn package. But for right now, we're going to just use Pandas. So the way we can get the label encoding is we can first convert our data to a categorical type. We've actually already seen this using the pd.categorical is an alternative to convert to categorical. But once we convert to categorical, we access the categorical attributes by using, so we access .cat to get the categorical attributes, such as the label encoding, which is from the codes. Codes gives us the mapping encoding values. So .codes gives us the unique label encodings that we have for those different categories. So for instance, as I was telling you earlier, A gets mapped to 0, which we extract from these codes. A gets mapped to 0, B gets mapped to 1, A we already know is 0, C gets mapped to 2, B gets mapped to 1, and A gets mapped to 0. So in essence, we have converted our categorical data again into something numerical. It's just this is a different strategy than doing one-hot encoding. It's doing what we call label encoding, which is going to be done for a different purpose. Usually it's done for model outputs. One-hot encoding is done usually for model inputs as data going into a model. And label encoding is usually done for data that would be the output of a model. Again, we haven't learned about modeling, but hopefully that is reasonable why those would be different, why we need a different strategy to convert from string to numerical, depending on if we're dealing with inputs or outputs. Any questions on this? That's a great question. It's because some of the functions come from Pandas. So the functions that come from Pandas are going to come first. Like this is you know that because it's from the PD package, right? So get dummies is a function from Pandas. The things that come after are functions on an object, like a data frame or a series. Like a series has a value counts function, or like a data frame has a sort values function. So those come after the data frame because they are methods or functions of that object. Whereas this is a function coming from the Pandas library directly. So pd.getDummies comes from Pandas and we pass data into it as an argument. Versus like if we already have a data frame, we can operate on that data frame by sorting it, by doing value counts, whatever the case is. Does that make sense? Yeah. So that's now you as you practice more of this, you start to remember which things come from Pandas and which things are inherently done on a data frame once I have the data frame. Like there's a bunch of functions we've already seen that operate on a data frame like head, tail, info, describe, right? Those are functions on a data frame once we have the df. So usually you see it as df.describe, df.info, df.head, all those things. But this is a function that is generically from Pandas, and we pass in a column or maybe a collection of columns to do the one-hot encoding. But it's a great question. All right. So there is some extra practice here that, again, I will leave to you guys. Feel free to do this between now and next Monday. This is just extra practice for you to work through doing some converting of existing columns in the this is, by the way, this is for the housing price data set. So you're going to be doing some practice with the house price data set to analyze the year built and year remodeled ad, to convert those to datetime format, and extract things like the year, month, or day, because these are dates. Calculate the difference between when the house was built and when it was remodeled. So you can subtract those dates, calculate the difference, which will give you a time delta object. Count the number of categories in the categorical features. So some of that data, if you remember, is going to be categorical. So those are going to be things like the zip code, the state, the address. So sometimes we want to know how many of those houses are from Massachusetts, how many are from New York, how many are from California. We should be able to do value counts to determine those numbers. And then we also I would encourage using something like the states to do the pd.get dummies to get some practice with building one-hot encodings of the data. So I'd recommend picking one of the categorical features or categorical variables and doing the get dummies with it. Yeah, the house price is CSV. That's what this wants you to practice with. This is with the house price CSV. Housing data set, which is the house price CSV. Yeah.
So this is going to be our last notebook in Pandas, so inside of lesson 4. But as I said earlier, by no means will it be like the last time that we work on Pandas. We will be working on it quite a bit as we continue because most of the time, anything we do is really going to be working with Pandas in general. So this definitely won't be the last time we work with it. But I wanted to wrap up with some additional topics in Pandas. One is going to be working with text data. There may be sometimes a need to work with strings, like some of our columns could be strings and we need to manipulate those strings. So I wanted to basically describe how we might do that and see some examples. I also wanted to show us like different methodologies for iteration over all of the rows inside of a data frame and kind of caution us to those methodologies and what the proper way to basically apply a function is to every single entry in a column. As you can imagine, that's going to use our apply function, but there are other ways to kind of iterate through every single row if for some reason we needed to do that. It would be very rare. I'll point that out, the kind of the syntax that we would need. I wanted to briefly describe sorting. We've kind of already done that, so I won't spend too much time on it, but we can definitely sort a data frame according to different columns. We can use those as kind of our sorting columns. And then just briefly talk about how you can plot things with pandas, knowing that, we have additional plotting libraries that we're going to learn about in lesson 5 coming up that will take care of plotting for us. But Pandas actually does have built-in plotting support to quickly do plotting without having to go to those other libraries and explicitly build out plots. Like if you just want a really quick one, like if you want to plot a column and figure out what the trend of that column is, you can easily do that within Pandas without having to use another plotting library. So it does support built-in plotting. I'll show us that. But let's start with text data. So if we have strings, kind of just like with series, we can access string attributes by using the .str attribute of that column. So this data is all string data. So we can access the str, which gives us access, kind of like how dates are the .dt. They give us access to things like day of the week. And month, day, year, those kind of things. If we do str, we can do different operations on the string and access different attributes of the strings. So for instance, we can uppercase everything, we can lowercase everything, we can get how many characters there are in that string. So for instance, like the hello string has 5 characters, so its length is 5. World has 5 characters, its length is 5, and on and on and on. You can do different operations. So this finds the length. Um, and notice that we are getting that from the str attribute and then doing different operations on it. So if you're ever working with strings, you're likely going to find yourself using the str attribute and then doing functions on that to kind of operate on that whole column. As I said, you can lowercase everything. So here we're creating a new column called lowercase, which takes the existing column of data we have and lowercases it. So it removes all those uppercases and lowercases everything you can see there. We could uppercase everything back, which would do upper. So you can see how that like that uppercases every single character. Um, but we can also lowercase every single character, which is what we had before. So pretty straightforward. Like working with strings isn't something we'll do that often. Most of the times when we're doing data science and modeling and we have strings, we normally won't work with it too much. We'll actually just convert it over to one-hot encoding to use it with models. So it'd be very rare that we have to do operations like this, but just pointing them out to you that we can operate on strings if we need to. Okay. Um, So another one is like we can check and see if strings contain any other substring. So this can be like checking if this data is within this existing string. So the only one that would return true on, this is something that's going to return a true or a false, is going to be that last one. So data science definitely contains data as a substring of that full string. So it returns true. So you can check and see if certain strings contain certain elements, which would be like certain characters. Like we could see if it contains an O, if it contains an L, if it contains a P. So we could do things like that. So we could check and see if things contain the P. Um, of course, Python is the only one that does, so it returns true in that example. Okay. Pretty straightforward, I think. Any questions on these kind of things working with strings? There's more functions. I'm not showing you all of them, mainly because again, it's going to be very rare that we would ever really need to work with strings. Usually, we're just going to convert them over to one-hot encoding because the strings are usually going to represent some type of categorical variable for us when it's in our data. Identify space? I think so. Well, we can check that out. So I have a single white space here, and data science contains a space. So yeah, the substring of just a single space character. Space is a valid character, like white space. It is a character, so it is. This is the one that has space, right? Okay, cool. Any other questions about working with strings? An old term, yeah. Yep. All right. So what I wanted to get to next was something more important, which is going to be how we operate on collections of rows at a time from the data frame. And data frames actually support a couple of objects that allow us to iterate through the entire data frame if we need to. However, we should be really cautious if we find ourselves looping over the all of the rows using something like a for loop. It's generally discouraged because it's very slow as an operation. So it's very rare that we should ever find ourselves having to do a for loop where we work our way through every individual row. For one thing, most of the data that we work with will have lots of rows, so that will be incredibly inefficient, looping through every single row, and we generally don't need to do that when we have something like apply, or we can do direct operations on columns that will do a calculation to every single row all at once. There's not really a need to loop over every single row. If you find yourself doing that, you're likely doing something wrong, and you should rethink what you're doing, just because it's going to be incredibly slow to do that. But Python does support um, a couple of functions on the data frame that give you an access to every single row in the data frame, and you can see what they are here: iter rows and iter tuples. I'm going to show you an example of those. But it'd be very rare that we would ever need to use these. So let me show you an example of what I mean by this. So notice that we have a data frame built out here with two different columns and only three rows. So we have column one and column two. So really we have data that looks like column one, which is column one, which has data that looks like one, two, three. And then we have column two, which has data that looks like A, B, C. So a very simple data frame. Now, what this code here is going to do, this df.iterRows, it's going to give us the ability to access the index and the row as a tuple. So essentially what it's going to do is loop over the entire data frame, all rows, one row at a time, and give us access to the entire row. Not only that, but the index, which is index 0, this is index 1, this is index 2, and it gives us that in a tuple. So the first time through the data frame, you can see what the index is. It's 0. We actually print that out, print out the index, and we also print out the value at column 1 of the row and the value at column 2 of the row, of the current row in the iteration, right? So on the first loop, on the first pass through the data frame, we are on the first row, so we have index 0 and we have a 1 and an A as the two values from column 1 and column 2. That makes sense. That's what this is. Then we go to the next iteration, which goes to the next row, and that gives us index. We are now on index row index 1, and we have column one's value is now 2, and column two's value is now B. So we can have access to those elements of the row by doing something like this. Okay. And then on that final iteration through, we are on row index 2, and the data that's in column 1 is a 3. The data that's in column 2 is C. So you can see that here. Okay, so iterRows gives us the ability to access the entire row at once, and then we can access particular items of that row based on the column name, just as we would like in a data frame where we put the bracket and put the column name. So we can access that elements of the row in that way. I should caution you that this is very slow. So, unless there's a very specific reason why we need to loop through every single row, we generally shouldn't be doing this. You could argue like one of the reasons we might want to do this is to manipulate this row element, um, or this row element or whatever. Like maybe we want to add them together or multiply or do some operation. And there's going to be different ways to do that that are much faster and do not involve an explicit loop over the data frame. I'm going to show us those. So it's generally going to be discouraged to do a loop like this. If you find yourself doing it, try to not do it. Try to think of a different way to do your operations. You really shouldn't be looping over every single row. It's generally discouraged. Okay, but there's the code to do it. Um, any questions on that code? Does that make sense what we're doing? We're iterating through every row in a for loop, and we have access to the index and the entire row as we loop through that. As we loop through that. But you know, we really should think twice about doing that because it's going to be a pretty slow operation to loop through every single row. There's much faster ways to do manipulations that we may want to do. Any questions there? Okay. All right, so let me give you an alternative. So like if for some reason we wanted to go through every single row and multiply everything by 2, well, we have a way to do that that does not involve looping through every row. That's going to be much faster, which is using the apply function. So we've already seen this with a series. Remember, what is a column? A column is just a series. So of course we can do apply to any column in the data frame, and that will allow us to manipulate that column and multiply every element by 2, square it, take the logarithm, whatever we want. This is a lambda function that we are applying to every entry in this column that will take the entry, which is what this argument is, x, and multiply it by 2. That's what this lambda is doing, is saying take your value and multiply it by 2. So when we apply that to this existing column, we are going to get a new column that has every element multiplied by 2. So we have a 20, we have a 40, and we have a 60. So pretty straightforward, but if you ever want to generate a new column with a mathematical function of an old column, generally you're going to want to use apply. Now, could you do this with the for loop? You could. You could iterate through each row and take the value that's at the existing column and multiply it by 2. That's going to be slow. That's going to be slower than if we just did apply and did an apply function to this entire column, which Pandas has an optimization to do apply. It does it so much faster than manual kind of iteration through every row. So again, like if you want to do an operation to every element in a column, use apply. Use you pass in that function to apply, and that will apply that function to every row of that column. Okay. So we've seen this before. So nothing that new. But just showing you again, and it applying a function is going to be faster than if we looped through here. So like what we could do, let me show you the alternative. So the slower alternative is to do something like for index row and df.iter rows, if we did row and we generated a new column equals row, and we access the existing column, and we took that and multiplied it by 2. Now um, that will do the same thing. It will take whatever is in the existing column, multiply it by 2, and set that as the new column element. But this is going to be, there's no reason to really do it this way. It's going to be slower. It's less readable than if we just did apply and took this existing column and applied this function to it. This will be faster. Pandas has optimizations for doing apply. This will be slower. Don't generally want to do this. All right. And then let me show you another alternative notation. So if you're doing something really simple, you're doing something really simple and you don't need a complex function here, like multiplying by 2, I would argue is really simple. You don't need anything that fancy. Like something simple could be like adding 2 columns together, or multiplying 2 columns together, or dividing 2 columns, or subtracting 2 columns, those basic arithmetics between columns, or even with a column and a constant, like multiplying everything by 2. You can do what is called a vectorized operation, where you actually take that whole column and you do arithmetic with it to another column. And Pandas will optimize this. Pandas optimizes this operation to be really fast. Now, why does it optimize it? It's because it uses NumPy under the hood, and it turns out to be an incredibly fast operation that would be so much faster than looping through every row and adding this row element with this row element. Like we could do that and get the same result, but it would be so much slower than if we did it this way. So taking the entire column of A, adding it to the entire column of B, We don't need to loop to do that. We can just directly do it. We can just directly do that arithmetic between the columns, and that will give us the new result, which adds those together. So that is called doing a vectorized operation because we think of the whole column as a vector, think of the whole other column as a vector, and we're adding two vectors, which is a really simple, it's like adding two NumPy arrays. It's a really simple operation. Okay, so you can do a lot of vectorized operations. You can do, another example would be instead of apply, we can actually do um, new result, or let me actually call this double result, would be df, take an existing column, so let's call it column A, and multiply that by 2. Okay, or multiply it by 3, whatever your favorite constant is. And that will generate a new column that takes the column A and multiplies it by 3. Okay, so 3, 6, and 9. So this is an example. We could use apply for this, which would be like df column A dot apply and then lambda x times 3. Like we could do that. But the doing it this way is actually going to be faster. And so when you have something really simple, we can just directly operate on the column most of the time and avoid doing apply, avoid doing for loop for sure. We never want to do that. It's going to be incredibly slow. How would you average a set of columns? So that would be using the built-in mean function. So you pick a set of, like, you pass in a list of column A, um column B, and then you do like np dot mean. You could do it that way. Does that make sense? Like you pass that into the average, like a NumPy average, or you can um you could do it that way, or the alternative would be to do dot mean like that. You could do it like that. So we can't forget our statistical functions, right, that we have on our data frames. Could we do this by looping through every row? Sure, but it's going to be so much slower and inefficient. I would never recommend doing that. Okay. All right. So, just like with now we mentioned this example here to say you can also iterate over a series, um, just in the same way. So as an alternative, um, as an alternative to iter rows, you can loop over an individual column. You can loop over an individual column because remember, every column is a series. So you can grab the what are called the items, which gives you the index of that series. It's basically the index of that row and the corresponding data point in that column. So you can iterate over an individual column instead of all rows, which is a little bit better, but still there's very rarely a need to do that. Very rarely a need to ever do that. Yeah, so that's a good question. Is there any specific condition where only looping is useful, even if it makes the program bulky? So I would say only where you're doing something that is so complicated that cannot be put in an apply. that you need access to only specific, like you're doing a transformation that involves elements of the row, like maybe you're concatenating strings, doing some transformation, then doing like math with it. You're doing something so complex that you actually have to loop through every row, and it can't be encapsulated in a simple lambda. That'd be the only scenario I could see. Just something really complex. Yeah, just something so complex that you can't get away with doing it in a lambda and you really have to do it. Or sorry, you can't get away with doing it in an apply. And you have to iterate through every row in order to apply that operation because you're doing something really custom. That's the only scenario. But again, like that's going to be something so complex, which would be very rare that you would do something that complex that you couldn't do in just an apply. Okay. All right. Any questions so far about iteration or doing operations kind of on the at the column level? Hopefully, so your options. So just to recap this actually, your options when you're working with columns is your first choice. If it's something simple like doing arithmetic or multiplication by a constant or applying a simple function like an exponential or a logarithm, you can actually just do that directly to the column like this. So if you can do that, that's actually going to be the fastest and most efficient way is to just directly operate on the column. If you can do that and your operations are really simple, you can get away with doing that. That should be your first choice is directly operate on the column. If you need to apply a more specific function, you can use dot apply. That should probably be your second choice, is to think about if I have a custom function, can I apply it to every entry in this column? That is going to be maybe you need to do that because you have a custom function you want to apply, and it's not so simple to just operate that on the entire column like a basic arithmetic here. So that would be your next choice is apply. Last resort, last resort, something so complex that you can't use apply and you can't use direct arithmetic would be looping through every row. That would be last resort. Iterating through every row, and then utilizing those row elements to do some custom operations with. Okay, that should probably be the last resort. Okay. Any questions on that though? Okay, very good. Let's go on to sorting. So let's talk about sorting the data frames. We've kind of already practiced this a little bit, so I won't spend too much time on it. But we do have the ability to sort data frames, which of course will rearrange it according to a column or maybe a collection of columns, and it can be, either greatest to least or least to greatest kind of sort. So you can see in this picture, like in this example, we are sorting based on the height column, which will rearrange it from least to greatest and kind of shuffle those rows according to the sorting. And so let's take a look at that with this example. In this case, we are going to take this data and sort it according to the age column. So one of the things we need if we're going to sort is to specify what column do you want to use to do your sorting, and that you can pass that in the by argument. Um, so we are sorting by the age in ascending order. So ascending order because the ascending argument is going to be false by default, which indicates that we are sorting according to the age from uh, uh, sorry, ascending is true generally, which means it will be a least to greatest sort um, by default. So ascending equals true is the default behavior. So if we don't pass anything in there, that will be what we get. We get a least to greatest. So you can see this gets rearranged where the age is now least to greatest. This is like in a spreadsheet, right? You take a spreadsheet and you go into a column and you sort your spreadsheet according to that column. It's kind of the same thing. Taking our data frame, sorting it according to this column. If we want to do descending, so if we want to do descending, we could do df sorted equals df dot sort values, and then we can do the same exact syntax where we pass in our column, except now we do ascending equals false. So this will now do the greatest to least sort. So it reverses that. Okay, so ascending false does a greatest to least sort. Okay, pretty straightforward, I think. Nothing, terribly interesting going on there. Oh, the other thing I forgot to mention is if you do sort values, it will not do it permanently to that data frame unless you do the in place argument. So if you want to permanently sort the original DF, you need to use in place equals true arg. So what that means is you would do something like df dot sort values. You could use the by age column, but in this case we would do in place equals to true. And this will permanently sort this data frame so that going forward, its values will be permanently sorted. Notice that we didn't do that. We just did sort values, which return, it's just like all those other things that return a copy of the data frame that has been sorted, and we store that into this df sorted variable that we can work with going forward. So when we do this, this original data frame is not permanently altered underneath, right? It's not permanently sorted until we do in place. So if we do in place equals true, then going forward, this DF will be permanently sorted. Okay, so just like a lot of it's true of so many data frame operations. They're not going to be permanently altered until we do in place equals true. It's just how it is. Okay. All right. So the other thing is you can sort according to multiple columns. So all you have to do is in the by argument, just pass in a list, and it's going to go in order of the list. So what that means is it's first going to arrange the data frame according to this first column, which is the age, and then it's going to secondarily sort according to this, if it can, right? So. Um, the age is the primary sorting because it is first, and then the salary would be kind of like the secondary sorting for any like tiebreakers. For instance, like if the age was tied, then we would sort according to the salary from least to greatest. However, you can change the greatest to least or least to greatest as your primary or secondary sorting. You can actually change that in the ascending argument. You can pass in a list. So what that means is the age here should go from least to greatest because that is ascending true, but the salary would be kind of reverse sorted. So the salary should go from greatest to least if there was any tiebreaker of the age, right? So if any ages were tied, we would then sort according to salary, but that would be actually a greatest to least sort. So whatever is greatest would be first. Um, does that make sense? Like multiple columns could be used for sorting. Think of this as just here's your primary sorting, here's your secondary. You can have as many as you want. You can actually have as many as the number of columns that you have. You can sort according to those. Any questions on that? Okay, pretty straightforward then. Um, let's see. You can also sort according to the index. So this is useful when your index is something interesting other than the default index. So this will kind of reverse the data frame because the index is of course 0, 1, 2 by default. And if we do an ascending sort false, this will kind of like uh, reverse it in effect, right? Because now the it's now a greatest to least index sort. So the index 2 would be first, index 1, then index 0 is last. So you can also sort according to the index. This is useful when you have things like time. Like if your index is a date, you could sort according to like earliest to latest in terms of the dates. That may be useful. So when your index is something interesting, you can sort according to your index, which is pretty useful. So notice the syntax is a bit different. It is sort index rather than sort values. So sort values is used for any column you want to use to sort with. Um, Whereas sort index is, of course, just going to use the index. So when your index is something interesting, that can be helpful. Like if your index is a collection of dates, you can sort that, which will go like earliest to latest. Okay. And we've already seen an example of sorting a series, so I won't really spend any time on this. We know we can sort a series. We've already seen that. The reason we're calling that out again here is because, again, what is every column? Every column is a series, so we can go into an individual column and sort it if we need to. And that may be useful to extract the values out of a particular column and sort it so that we can manipulate it if we need to. So we can always take a column and sort values just as we can an entire data frame. So no surprises there. All right. Any questions with the sorting at all? Feel pretty good about that? I think it sounds like we feel pretty good about sorting. I think it's pretty straightforward. Again, it's just like if you had a spreadsheet and you were to sort your data according to specific columns. It's the same exact concept in Pandas. Okay, very good. For large data sets, do you know if our data set or Pandas is faster overall? It depends on what you're doing to it. What did you have in mind? Like, if you're doing basic arithmetic, like if you're doing operations like this, like multiplication or addition of columns, I actually think Pandas is going to be faster because Pandas is backed by NumPy, which is pretty fast for doing those kind of things. I think Pandas is going to be faster for doing like basic vectorized operations, but anything beyond that, it could be slower. Yeah, I think for doing basic vectorized operations, I think it's going to be faster. I think you get in trouble with Pandas when you get outside of that. At that scale, yeah, it's going to be. I mean, there's other, by the way, there's other things that can work with data that's that big, right? There's other frameworks that can work with large data. Something like a Spark or something would probably be more ideal. Not that we'll cover that in this program, but yeah, generally for dealing with data at that scale, we probably would move outside of Pandas altogether anyway and be working with some other big data framework. Okay. Um, all right, so let me finish up Pandas by telling you guys a little bit about some plotting. So if you have a data frame, you can actually quickly plot the column data by just doing df.plot. So a very simple function which will generate the plot. Now we haven't learned about Matplotlib. That's going to be in our lesson 5, which we're going to get to next. But suffice to say that df.plot uses Matplotlib in the background. Pandas will use that, but we don't have to explicitly go into Matplotlib and build an entire plot to quickly generate one off of a data frame. So df.plot will build a simple line graph of each column. So it's plotting A and B, where we have the x-axis is just the basically the row index. So I should mention that here, the x-axis is the row index. So that goes from 0 to 4. And then the y-axis is the data. Y-axis are the column values. Right, so it's plotting. If you take a look at it, it's plotting 1, 2, 3, 4, 5, and then 5, 4, 3, 2, 1, which are these two lines here. And you can see they even get labeled A and B. Something we're gonna learn about how to make plots. So I'm not too concerned right now about like how do we get this legend here? How do we make these different colors? We're gonna learn about that in a few minutes. But again, Pandas has the ability where we don't really need to do anything that fancy. We could just quickly plot a data frame if we need to do that. If we need to quickly plot it and we don't want to spend time setting up an entire plot, we could just do df.plot. One thing that I'm going to talk about in a little bit is this plt.show. So this code is the equivalent of print. This is basically the equivalent to print when working with graphs. So it's yeah, why not write that? It's because this is Matplotlib's way of doing the print function to say, okay, I'm ready to display the graph. It's like it basically is like a display function that comes from Matplotlib. So I'm gonna show us why in lesson 5. So hold on to that thought. I'm gonna show us why this is important in lesson 5 when we actually talk about Matplotlib. We haven't covered it yet, so I don't want to go too down that road. But it's in the next lesson. It's gonna be in lesson 5. Yeah, this PLT part is Matplotlib, but this is not. This is just the dataframe.plot, which is what I want us to focus on. This part is from Matplotlib, which is basically the print statement of Matplotlib to like display the graph. So it's nothing that interesting other than saying, okay, I'm ready to show the graph. So go, it's like print. It's like print your graph that you have available from df.plot. df.plot generates the plot. So this code generates the plot uh in the background. And then we don't actually display it until we do plt.show, which will print it out. So this like renders the plot data and gets it all ready to be printed. And then plt.show is kind of like our print function that will actually then display it. So this code kind of generates the plot. This actually prints it out. So we're going to see if that doesn't make sense now, that's okay. We're going to see plenty of examples of plt.show coming up of why we want this to be here. Right. So Pandas isn't responsible for displaying the graph. No, it's responsible for building the graph with this basic DataFrame.plot function will generate the plot. But it's not responsible for displaying anything. That doesn't happen until we run this code. And Roberto, I would encourage you to try this. Like in your VS Code, try running this, try creating this and leaving out this and see if it actually prints it out. Okay. So this won't do anything until we do plt.show to actually render and display the graph. Okay. So I wanted to show you a couple other types. Again, not going to focus too heavily on this because we're going to get into building our own plots in Matplotlib coming up in lesson 5, which is going to be next. But we can do a bar graph as well. So we do df.plot and we pass in a bar parameter. This will create a bar graph that looks like this. So it takes our indices 0, 1, 2, 3, 4, and it generates a bar graph of the values in our data. So we have A in the data, which column A has values 1, 2, 3, 4, 5. Column B has values 5, 4, 3, 2, 1. So we display kind of a bar graph of that data here. And the only thing we really had to do is do df.plot and then change this over to bar. The default is just a line graph. So if we don't put any type in there, so like what we just did with bar, it's just gonna build a line plot by default. Okay, it's just gonna build a line graph by default. Okay, and it turns out that there's other types. I'm not going to get into them really because we're going to explore those in Matplotlib in 5.01. But there are other types that pandas can do out of the box. I will say that it's rare that we would actually use this as our plotting methodology. Generally, we will build the plots directly in Matplotlib code, which is what we're going to learn how to do next. Okay. That's what we're going to learn. But it's just to show you that Pandas does support doing like really quick plots on data frames if we need to. Like if we want to get a quick view without having to go into Matplotlib and write some Matplotlib code, we can actually quickly plot some characteristics of the data frame if we want to. Okay. All right. Any questions on this notebook? PLT is the industry shorthand for Matplotlib. Again, we haven't covered that yet. We'll cover that next. We'll cover that next. Yeah, Roberto, I was afraid of that. I think it's because the notebook the notebook plugin in VS Code automatically renders graphs. But if we were to run this in a script as well and we didn't include this, nothing would display. Like if we remember when we talked about running code as a .py file, if we have like plotting code in there, it's not going to render until we do plt.show. It's the print statement of displaying graphs. So if you're running in a notebook, the notebook may have built-in support to automatically render the graph. It's kind of like when we can do, you know how we can display a data frame without actually doing print? It's because the notebook kind of can render that for us, right? So the notebook can render this for us without, notice how we didn't do print? It's the same concept. Normally we should be doing plt.show to kind of print the graph. Um, Yeah, so like it kind of like this where we don't like I could put a print here and it would display the information as well. PLT.show is how we would ensure that we display the information if we were running that code in like a PY file or in a notebook backend that didn't automatically render the graph.
And with that, we have come to the end of this course. If you have any doubts or questions, you can ask them in the comment section below. Our team of experts will reply to you as soon as possible. Thank you and keep learning with Simplilearn.